for joining us as we open our workshop on the convergence of high-performance computing, big data, and machine learning. This is really a product of the Networking and Information Technologies R&D program and the confluence of two different working groups under that program, the Big Data Working Group, for which I and Chetan are co-chairs, and the High-End Computing Working Group, for which Sandy, Barry, Laura, and Randy represent. So I really want to thank you all for coming today to talk about this very important problem for all agencies as well as different sectors of industry. NITRD includes 21 agencies that have interest in IT R&D for a total of approximately $5 billion annually. So it's a really big part of our federal budget. IT R&D includes computing, networking, software, and big data. As part of both of these working groups, we have a joint interest in these problems. The focus of the workshop is to discuss the evolving landscape of high-end computing software paradigms in a world where data and AI become more and more predominant. The workshop is really about opening with landscape talks on where we are right now to set the stage in these areas, and then includes 3 different discussion areas, including software challenges, hardware challenges, and modes of operation. Day 2 is really a chance for us to do a deep dive into each of these areas to hear what you feel is important, where are the challenges, where are the opportunities, and then we'll report out. We as NITRD co-chairs, we look forward to your thoughts, your considerations of this important area as we plan for our future needs and opportunities. We're open today, excuse me, with a talk from Dr. Lynn Parker. So I think Lynn is here. It's really a pleasure to introduce and welcome Lynn. Lynn received her PhD in computer science in 1994 from MIT. Her work in artificial intelligence and heterogeneous robotic systems is well known to many of us. And she continues to make important and very, very significant contributions as she served at NSF, DARPA, the National Research Council, and now at OSTP. And it's really a pleasure. Thank you so much, Lynn, for coming today and opening our talk.
Thank you so much, Susan. I appreciate that. Well, good morning, everyone. And I appreciate the opportunity to speak with you and tell you a little bit about the Office of Science and Technology Policies activities as it relates to the subjects of this meeting today. So let me just start with a couple of remarks. Our investments in AI and data and how we use cutting-edge technology and advanced computing capabilities are certainly among the most important areas of emerging technology at work for both inside the government and outside the government as well. And second, hopefully you are aware that using the power of AI and data is a priority of this administration. It's also a priority of our lawmakers and leaders across all of the federal agencies. So there are a number of activities that can illustrate that priority, including defined investment priorities in the budget process, the formation of the Select Committee on Artificial Intelligence, revised regulations to accelerate the use of AI technologies by industry, policies to improve opportunities for STEM education and workforce reskilling for adults, cross-agency priority goal for data in the President's management agenda. There are a lot of executive orders in this space, and of course Congress has gotten involved as well with a recent white paper by Congressman Hurd and Congresswoman Kelly. So I'll touch on a few of these in a little more detail, but I want to emphasize that this really is a bipartisan area, a bipartisan topic, and leadership across the federal government is very interested in this space. So let me just share a few details in some of these areas. Certainly, you're here today because you recognize that AI and machine learning is transforming applications across the gamut from healthcare to transportation to manufacturing. Complete AI systems, of course, consist of many parts. Certainly, there's the fundamental core technologies that enable the computer to see, to hear, to learn and reason through models and data analysis. But these AI technologies also rely on the cyber infrastructure, systems, and data that provide the complete foundation for these AI systems to operate. So realizing the full potential of AI for the nation requires the combined efforts of industry, academia, and government, of course. And so there have been a number of policies under development in the administration and a number of strategies to implement those to accelerate AI innovation across the nation. So let me start with mentioning the White House Summit on AI for American Industry that was held back in May. And at that workshop, a number of key priority areas were emphasized, and these are the areas in which the administration is actively pursuing directions for AI. So let me just quickly outline those for you. The first is to prioritize funding for AI research and development, including designating AI R&D for autonomous and unmanned systems as an administration R&D priority. A second area is removing barriers for innovation by, for example, streamlining the safe use and introduction of self-driving cars to our nation's roads. A third is training the American workforce. There was a memorandum signed about a year ago that promised about $200 million in grants for STEM education, focusing on computer science education. And industry also matched that with $300 million. Fourth is adoption of AI into the President's national security strategy and the national defense strategy, noting in particular that AI is, as pointed out, and there is an important area. And then, of course, leading international AI negotiations by working with the G7, G20, ITU, OECD, and others international organizations to talk about potential AI benefits and R&D. And then, of course, there's the sixth area, which is leveraging AI and data itself to improve government services that are provided to the American public. And so that's looking at maximizing federal data sharing in particular. So these are all areas of active work across the federal government. Let me just focus first on a little bit on the R&D part of the equation. So I mentioned that the Budget Priorities Memo emphasizes the strategic importance of AI R&D. So helping to guide and inform these investments is the new Select Committee on Artificial Intelligence, which was created in May at the time of the White House AI Summit. This Select Committee represents a whole-of-government approach to AI R&D planning and coordination. So the Select Committee, their mission is to improve the coordination of federal efforts related to AI to ensure continued U.S. leadership in the field. It operates within the Technology Committee of the National Science and Technology Council. It is made up of the most senior R&D leaders, officials from across the federal government. This includes Dr. Cordova from NSF and Dr. Walker from DARPA. The Select Committee also provides guidance and direction to the reconstituted Machine Learning and AI Subcommittee, which serves as the operations and implementation arm of the Select Committee. So as we prioritize AI R&D, we also want to emphasize that we need to invest in the areas of most strategic importance, particularly given the fact that industry invests significantly in this space. So the National AI R&D Strategic Plan, which was created in 2016, still provides the guidance for those investments across the federal agencies. Of course, given the rapid pace of AI research, it's critical that our R&D investments remain at the forefront of science and technology. So about a month ago, NIDARD released a request for information to the public to seek input on whether the strategic plan should be revised, and if so, the ways in which it may be improved. This includes suggestions such as to the addition, removal, or modification of the strategic aims in the AI strategic plan, along with comments on existing strategic aims, as well as their past or future implementation by the federal government. That RFI closed on Friday midnight, and we were beginning to look at those responses and a lot of very well-reasoned, very helpful, insightful feedback. And so we look forward to digging into that. And those responses then will be informative as the NIDARD and the Select Committee update the National AI R&D Strategic Plan. So by updating the strategic plan, then we help ensure that the United States continues to lead in cutting-edge AI innovation that addresses the most pressing challenges of today. So, germane to the emphasis of this workshop, let me also note that the AI R&D Strategic Plan also discusses the importance of hardware and cyber infrastructure needed for the effective use of AI technologies. In particular, it talks about the need for R&D for hardware for AI, as well as AI for improved hardware. So, as you all very well know, hardware advances can improve the performance of AI methods that are highly data intensive. For instance, neuromorphic processors could be optimized for the operation of neural nets. New methods could also be used to turn on and off data pipelines in controlled ways. Research advances could enable machine learning algorithms to effectively learn from high-velocity data, including distributed algorithms that simultaneously learn from multiple data pipelines. More advanced machine learning methods could allow AI systems to intelligently sample or prioritize data from large-scale simulations, experimental instruments, and distributed sensor systems, such as smart buildings or the Internet of Things. New methods might also enable dynamic I/O decision-making, in which choices are made in real time to store data based on importance or significance. As you know, there are also ways for AI to improve the hardware itself, and specifically the performance of HPC systems by increasing hardware efficiency. For example, AI can make online optimization decisions based on prediction of HPC performance and resource usage. AI could be used to create self-reconfigurable HPC systems that can handle system faults autonomously when they occur. So certainly the design of HPC systems is that are well suited for AI is accelerating. As I know you're aware, in June of this year, the Department of Energy and Oak Ridge National Lab unveiled the Summit supercomputer, which provides unprecedented computing power for the integration of AI and scientific discovery. Summit's AI-optimized hardware will provide the ability to analyze massive data sets through the use of intelligent software to accelerate the pace of discovery. So let me now focus a bit on the data part of the equation. I hope you're aware that the nation is undertaking many efforts now to leverage data as a strategic asset. So this goal is defined in the President's management agenda as cross-agency priority goal 2. The government is now in the process of drafting a federal data strategy. This strategy is an integrated set of actions that will deliver the necessary standards, capability, and governance that will result in quality data. By that, we mean data that's discoverable, appropriate, and properly protected. Getting the data equation right will lead the federal government to deliver the outcomes that our country deserves. The data is the way we empower the advanced technologies that can benefit the nation. Of course, managing the government's data is difficult, and getting it organized and accessible for use by AI technologies is not a simple task. The challenges include the volume of data, the stovepipe sources of data, the implications of privacy and confidentiality, and the myriad laws and regulations governing access and use of data. In government, we also have the very important challenge of ensuring that we maintain and continue to build a workforce that has the right skills for empowering AI, big data, and advanced computing. The government's also exploring the creation of policy for government use of AI, as noted in the federal data strategy. It's also been suggested by Congress and in discussions across various CIO councils. You can find more information about the federal data strategy online at strategy.data.gov. So let me close by thanking you for your investment of time and intellect in this workshop at the convergence of HPC, big data, and AI and machine learning. Certainly, the United States has leading-edge expertise in advanced AI technologies, leading computing capabilities, and some of the most valuable data in the world. We also have a world-class research ecosystem, which itself is a convergence of industry, academia, and government. So this powerful combination gives me confidence that you and your colleagues will continue to generate cutting-edge ideas and solutions that will solve complex challenges, advance science, and certainly benefit our nation and the world in myriad of ways. So thank you for your hard work in these areas. I wish you a productive and impactful workshop. and I look forward to hearing about your key outcomes and recommendations. Thank you.
Thank you so much, Lynn. That was really delightful, and hopefully Lynn will be able to join us for the rest of the workshop so that if you have questions, you can certainly touch base with her. It's really a pleasure to welcome Dr. Jim Caruso to our workshop and as our keynote speaker. Jim is the Assistant Director for Computer and Information Science and Engineering, SISE, at NSF, well known to many of us. He's also a Distinguished Professor of Computer Science at UMass Amherst, and he is a fellow at ACM and IEEE. His research includes networking, modeling, and performance, and I really appreciate your ability to come and tell us about what's happening in high-performance computing, big data, and machine learning, not maybe at just NSF, but what you see more broadly. Thanks, Jim.
So I like to say I can't talk to my kids without slides, so I actually have some PowerPoint slides here. I'm really happy to be here, and actually I want to take, Lynn and I had chatted a little bit ahead of time, and we're touching on some of the same topics, but a slightly different projection on them. And so I want to talk about, again, what this workshop's about, the confluence of high-performance computing, big data, and machine learning. So as Susan and Lynn and others will say to you, first of all, welcome. We all know how precious our time is, and to see this looks like an all-star game to me here, looking out and knowing people here. So it's really great to have people like you to come together to really talk about what's happening at the confluence of all of these areas. So welcome, and again, thank you, and thank you for being here. So I always like to figure out, why are we doing what we're doing, right? So we all sort of share this common understanding and a belief that when we think about high-performance computing, big data, and machine learning, it is going to enable really truly revolutionary advances in science and discovery. So putting on my NSF hat, all of NSF is thinking a lot about what's happening at this intersection: health and welfare, national defense, and national security. Now, Lynn, it's always great when someone has already sort of taken a cut at what you wanted to talk about. Lynn mentioned actually that the work in this area sort of fits right in with administration priorities. So I will tell you, so I've been a faculty member for 30 plus years, and now I almost feel like an old timer having been in government now for 4 years. You know, when it's the case, either as a faculty member or, you know, in an agency leadership position, that you look up and you say, hey, the kind of things that you think are really important, machine learning, big data, high-performance computing, you think they're important, and the administration comes out and says, hey, these are really important things. That's really, really, really good, right? And so Lynn mentioned both the federal 2019 and the federal 2020 R&D budget priorities memo. So for those of you who don't know, I'd never even heard of this until I came to NSF. The OSTP, the director of OSTP and the director of OMB, put out an annual memo and say, hey, here are really important areas that agencies should be prioritizing. So you see, actually you see up here, this is from the 2020 memo that came out at I think the last day of July this year. So you see machine learning, research and infrastructure to maintain U.S. leadership in strategic computing, embedded sensors, data analytics, and machine learning. Hey, that's what we're here today talking about, and there it is in a, you know, a 4 or 5 page, I can't remember exactly how long it was, 5-page budget priority memo. This is what the administration would like to sort of flag for agencies as important. My understanding is that every administration puts out a national security strategy and also a national defense strategy, and you see those up there. All of these are available online: the national security strategy, data science, advanced computing, artificial intelligence. In the national defense strategy, there it is, all 3 of them in one sentence together, right? So advanced computing, big data analytics, AI. That's what we're here. Oh, and actually, it didn't call out machine learning, but we all know what the relationship there is. So I think it's really wonderful that what we're talking about here And the confluence of these three areas is exactly what the administration is talking about. So I just want to take a very quick cut across this equation of HPC plus big data plus machine learning. And let me start with high-performance computing. So Lynn mentioned Oak Ridge and the Summit supercomputer. I would also mention Blue Waters and activities going on. So you see sort of there's the, on the left-hand side, there's something from the Summit website. If you look at both what's going on at NCSA and the collaborators there on Blue Waters, one particular example is on AI and gravitational waves. If you look what's happening at TAC, these are just several of the capabilities that the National Science Foundation funds, AI and supercomputers helping to alleviate urban traffic problems. Actually, there's a whole set of examples of AI applications bringing HPC together to solve challenges there. So from an HPC standpoint, we can see that all of this is sort of fitting together really nicely. I wanted to make a comment about cloud also because I think that's a really important part of the equation. At the National Science Foundation, this solicitation came out last Thursday, so I wanted to flag it for people. And there's a meta story behind this that I'm going to tell you at the end. But this is enabling cloud access to computing resources for science research and education. And the idea here is to it's looking at creating and experimenting. This is a pilot we're going to be running with a cloud access entity that's got a community-facing side so that you're interfacing. Again, this is with SCIES. We're starting initially smaller within NSF, within the SCIES Directorate, which actually historically has used the most, made most use of cloud, and also building on the big data collaboration that's been going on between Amazon, Google, Microsoft, and IBM. So we've got sort of a community-facing side where it can be a center of expertise, where we can enable sharing, and then on the provider-facing side, multiple cloud providers working together with this cloud access entity. So I'd encourage you all just to take a look at that. We're really excited about that. I'd note that NIH, for instance, has STRIDES, which I think is very much trying to do the same thing, maybe a little more data-oriented, but as we all know, data and compute go together. So I think, you know, seeing both NIH and NSF doing pilots and looking at what's happening here is a really great sign. Okay, so that's all I wanted to say about HPC. Again, this is just an opening talk, and I want to return things to you folks because that's where the real work is going to happen. I have to put in a plug for the National Science Foundation since that's where I'm working. You know, we have this notion of the big ideas. So these are 6 big research ideas sort of for long-term investment, you know, minimum 5 years in 6 different research areas. So harnessing the data revolution. So many of you have heard about that. Work at the human technology frontier, navigating the new Arctic, windows on the universe, that's multi-messenger astrophysics, the quantum leap, and understanding the rules of life, and bioinformatics is there. So here's what my boss, Franz Cordova, says. Okay, bold questions, driving our long-term research agenda. So when these, well, all the directorates were involved in putting these together, when I think, well, what does this mean? You know, which of these are really important when you think about high-performance computing, big data, machine learning? Well, actually, all of them. And I won't go through them one by one, but pick any one of those, and it's very clear that computing is going to be central, data is going to be central, and machine learning is going to be central to these. So actually, my boss, Franz Cordova, was here a little over a year ago, and I don't know if you know how it is. You sort of help your principals with their talks, but this was one where I helped, and then when I saw the final text, she wrote this section, so I thought, wow, this is really great, right? So AI being the universal connector that interweaves all of our big ideas, data science. So already the tie between machine learning, data science, and the application of these so right at the intersection of where we are today. So we have these big ideas, one of which is harnessing the data revolution. I'm not going to go into the details here. Actually, this builds on a number of activities that have been going on within NSF and in the SCIES Directorate. I want to give a shout out to Chaitan Baru, who's here somewhere, who just timed out after 4 years at NSF as a science advisor for data science within SAIS, because a lot of these things got started with his and other people's leadership there. But everything you see in red has to do with solicitations and activities that are out. Let me say that the big ideas are being launched in 19, so all of this is foundation and prelude to what we're going to be doing this year. So I know there are some people in government here, and so I want to say one reason why the big ideas are different and you want to take a look at it, and that has to do with the budget model. So at NSF, one of the things when we do these cross-directorate things, you know, I as an AD might go to a directorate with my tin cup and say, oh, you know, we're all going to do this thing. How much would you like to put in? And how much would you like to put in? And sometimes directorates say, yeah, we're all in. And other times directorates say, well, let's see what comes in and we'll figure out how to do it. So we've committed $30 million a year on top of all of these investments across all the foundation, sort of took that money, put it in a lockbox, and it's there for that. And in each of those 6 big ideas areas, there's that much. So I think that will be great. And as a way of moving forward, we can really plan over 5-year plus time horizons. And I think that's something that you'll be seeing coming out this year. We also have the notion of convergence accelerators. So harnessing the data revolution is one of the big ideas. There are 2 big ideas that also have this convergence accelerator that we're associating with it. And these, again, are $30 million chunks of money that have been set aside, particularly and in addition to the big idea basic research for translational, use-inspired convergence research. And the way I like to define this is as being DARPA-esque, since I've worked with DARPA program managers as a faculty member for a long time. I get what it's like to be a performer rather than a PI. I mean, that's a big difference, right? That's what DARPA calls their folks, right? So the convergence accelerators will take on projects in harnessing the data revolution that have clear goals, milestones, directed deliverables. And when you think about infrastructure broadly construed, when you need to build things, those are the kinds of things that I think we envision happening here. Okay. When we talk about data, I'm almost done with data, and then I'm going to go really quickly through machine learning. I think there's a tendency, which is unfortunate when we think about data, to think about you know, sort of the lowest level of data that's coming off of sensors, that's coming out of surveys, wherever the data is coming from. And I want to remember, and matter of fact, I remember being actually standing literally within centimeters of where I'm standing here now a year ago at this workshop right here. That was at NIH, actually the 3rd in a series of workshops on the Open Knowledge Network. So think now, yes, you've got data, but you've got to be able to make sense of it in an NLP and in a semantic sense. And so there's this notion, several workshops here and elsewhere on the Open Knowledge Network to design and actually prototype an open semantic information infrastructure that, again, is open and folks can contribute to so that we can do that higher level reasoning. Okay, I'm going to not spend, I think, hardly any time here on machine learning and AI. Anyway, you are all the experts in all 3 of these areas, so what could I possibly tell you here? I want to say I borrowed this concept and simplified it a little from Andrew Moore because I love this stack, right? Because a lot of times, you know, especially when I talk to people who sort of aren't working in these areas, you talk about AI and they think machine learning, right? But what this workshop's about, and as all of you know, sort of at the lower levels, we have the sensing, the data acquisition. We have to know how to manage that. So data discovery and access, that actually ties into some open science activities that are going on across government. We know the challenges of security and privacy. Okay, there's machine learning. You're going to talk about that a lot today. The models that you build on top of that, some of those are domain specific. There's something that looks like an open knowledge network there over on the right-hand side. Okay, so we've got data, we've got machine learning, and we need infrastructure also. So that infrastructure is going to be HPC and cloud, and of course things need to be tied together. So there's networking, there's the instruments that generate data. There's the higher level sort of semantic content of the information. And then I was really, really happy to see that you've got sessions here on software, and that will touch on the people, organizations, and communities that are needed to sustain this. So I think this, I should say what we're doing in size. Okay, we're doing a lot of things, and Henry Kautzar, Division Director for IIS, is right there, and he could tell you more about this, core research programs, and then, if you will, sort of the application of AI, the big data program, Smart and Connected STAR, as we like to sometimes call it, some large-scale center activities in expeditions, and this notion of AI plus X, machine learning, as a new horizontal. And that's something you actually saw in the NSF director's comments about the big ideas. So our overall investment, just because money matters, because it's a way to, it's a mean towards an end, just in these core areas, if you will, that you see listed above, about $120 million a year from the National Science Foundation. When you think now about infrastructure, when you think about, for instance, the architectural work that Lynn mentioned, you think about the application of AI, this more than triples across the foundation on a yearly basis in terms of investments in AI. Okay, Lynn talked about that. I'm not going to talk about that. Let me finish up by saying, okay, so here we are. We're here at the confluence, talking about the confluence of HPC, big data, and machine learning. And if it's going to happen, and we all believe this is important, where else in the entire United States are we going to be able to bring people together to identify the challenges here and identify directions forward? That's what you folks are here for today, right? Because you've got folks from the high-end computing. So this is all under the aegis of NIDARD, an interagency working group on high-end computing, an interagency working group on big data, and an interagency working group on AI and machine learning, right? And so you folks in the room are coming from these different areas. You folks in the room are the type that are the people that can make this happen. Okay, so what's going to happen here? How do I want to say this? After 4 years on the job, I sort of know what I can say, what I shouldn't say, and what I can maybe get away with saying, and it's still okay. So let me walk a little bit more towards that line, right? So you're going to be here. I want to talk about reports and what you can do in this workshop and how you can speak to government in this workshop and to agencies, right? Sometimes we have workshops where people get together and they say, oh, here's the context, here are the challenges, okay? Well, it's great. That's absolutely needed, right? We need to know what the challenges are. But you folks all, you're going to come together, you're going to figure out the challenges, you figure out the new challenges because of intersections, but actionable items are important. So this is not a FACA, Federal Advisory Committee. You can't make official recommendations, but you could certainly make suggestions, right, about technical directions, about how do you think the federal government should achieve integration between these areas? How might we do partnerships between academia, industry, and the federal government? So I have a believe it or not here. Sometimes, I don't know, I've run workshops for NSF and other places when I was a faculty member, and I often wondered, we're all afraid we're going to write a report, it's going to go on a shelf, okay? So this obviously can sometimes happen. This will not be the case here. I want to promise that to all of you individually. And I want to give you an example about why workshop reports really do matter. So I want to come back to the cloud solicitation that just came out. There were some new things in that NSF hadn't done before. And when we were trying to push that through, the question came up, well, what does the community think about this? Well, that was great, right? So when I heard that question, I'm like, okay, that's a softball, and I can hit a home run here. Sorry, I come from Boston, Sorry. I know there are probably some people. I know there are some people from Southern California here. Sorry. But that's a softball. I could hit a home run, right? So what we did was we said, hey, look, we had a workshop in January of this year. So, right, the solicitation just came out now. So it's a little bit longer than we'd wanted, but it's still within the same calendar year by quite a bit. We said, hey, look, the community came together, produced this report, made these suggestions, and look at what those suggestions are, and look at what we're trying to do here. And then the response came back like, oh my God, this is great. Why haven't we done this sooner? And like, as soon as you sign off, we're ready to go. So reports really do matter, right? They matter because you represent the community, NSF, and other organizations. I mean, it's all about the community, right? That's where the work happens. So we need to hear from you. We need to hear why it's important, but we also need to hear what your suggestions might be, because you're the community voice into us within agencies and more broadly within the federal government, setting priorities and defining what the activities are going to be going forward. So again, please remember your workshop report is really important. It gets read at the highest, I can tell you, at NSF, it gets read at the very highest levels, on the very toppest of all the floors in our new building, and actually throughout the building. So they really do matter, especially in areas where we want to move forward and we want to move forward quickly. Okay, so with that, I'm completely done. And again, I want to just end with a word of thanks. I want to thank all of you for being here, because I know time is your most precious commodity. I want to thank NIH folks for hosting us here. This is always a great place to meet, and of course the people who made this happen, the NIDARD staff, Wendy, G, and Faisal, who are the NIDARD staff leaders for these 3 working groups, and Cami Roberts, who's right there, who leads the NCO for NIDARD, and also the IWG leadership. I put Chaitan there. He's not actually at NIDARD anymore because he's not at NSF anymore, but he, along with Susan and Henry and Sandy and Barry, who were mentioned before, and Jeff Allstat, the new co-chair, with Henry of the AI working group within NIDARD. I mean, these are the folks. Everybody I just mentioned has a day job, right? And they do this on top of their day job. And you should all know that, I mean, it takes volunteers like that who care, who are knowledgeable, to make things happen. So thank you to all of you for your leadership here and for the hard work in bringing this community together. And with that, I'm 1 minute late, but that's okay. That's not too bad going forward. So again, thank you all for being here. And if it's not obvious, we at NSF, and I know throughout the agencies, really do look forward to what's going to come out of this workshop, because it's in such an important area. So I think with that, I'll say thanks and turn things over to Susan. Okay, great, thank you.
Thank you so much. So I do have a few slides, and while you get those up, I'll just reiterate what Jim said. You have the ears of not just NSF and NIH, and we're here because we have the facilities, but also DOD, Commerce through NIST, Department of Transportation, NASA, NOAA. You have the ears of all of the federal agencies who participate in NIDARD and who are interested in what you have to say about this very important topic, the confluence of high-performance computing, big data, and machine learning, and AI. So I hope that you do take advantage of your lucky seats and tell us, because we are listening. How does it go forward? This one, okay. So when we worked with our panelists who are listed here to come up with some important topics that we thought would help frame the landscape of where we are in these 3 areas, we thought that given what we know today with what's happening with Summit and Blue Waters and TAC, as well as what's happening at NSF, both internally with our Beowulf system, as well as what we're doing in Strides in the cloud computing architectures, we thought that perhaps what would be most important was to talk about what is possible now in these areas. I suspect that there's quite a bit possible, and so this is not a problem that is going to be necessarily hard to solve, but it is going to take some thought in terms of where do we want to go scientifically and where do we want to go in industry in these areas. So what's on the horizon architecturally and algorithmically that has you the most excited? Where do you see the bottlenecks? Certainly, we are interested in real-time smart algorithms and smart computing, and how do we deploy these types of architectures and algorithms in different sectors? Biomedicine, autonomous vehicles, where are we going with physics and physics instruments, and where are we going with instruments for biology? Where do you see challenges in creating these systems that will merge high-fidelity, high-performance throughput simulations with on-demand analytics calculations from data science? Where do you see unforeseen security and privacy challenges in streaming and pre-computing data from devices and sensors? This is certainly something that's going to be of interest. And are there opportunities for human-computer interactions that enhance our performance and our surveillance and our forecasting and predictions? Certainly, when we look at pandemics, this is something that we're very, very interested in. So we really do want to hear from you on these different types of topics, as well as others that we haven't thought of, because there are many things that we can think of and many that we cannot. So I'm pleased to have an all-star cast here. Each speaker will speak for about 20 minutes, and we left about 5 minutes for Q&A, and then we'll have a half-hour panel afterwards to address these questions and more. And I think that Wendy is our timekeeper, and so each speaker has about 20 minutes with the 5 minutes Q&A. And I want to introduce our first speaker, Tony Hay. Tony is probably one of the most recognizable names in computing and actually in data science as well. He serves as the vice president, or he did serve as the vice president of Microsoft Research. He is now serving in many different capacities, including the head and chief data scientist of the Science and Technology Facilities Council at the Rutherford Appleton Laboratory in the UK. And Tony is here to tell us about where are we going in this area and the science domains that he has seen over the years. So thank you very much, Tony. It's a real pleasure to welcome you here today.
Lab with all the accelerators and things like that, and that's what I want to talk about. Right, okay, so I'm going to run through some slides. First of all, I should just go back to when I used to work with Jim Gray, as you all know, and Jim saw that nowadays you needed more than just knowing how to program a supercomputer. You needed to know how to manage data, how to know what a schema is, how to manipulate it, how to do analyzing with data analytics and so on. And so Jim recognized that a long time ago and called this the fourth paradigm. And nowadays, he used to look for people, scientists who are drowning in data. Well, that's certainly the case nowadays. This was in 2009 we produced this tribute to Jim Gray. So because STFC looks at particle physics and astronomy, I'm just going to quickly look at particle physics and astronomy before going on to some of the other data challenges. So particle physicists are always leaping ahead, as you know, and this was done some time ago. This was the Higgs challenge, where they produced a simulated data set, and they challenged the Kaggle challenge. Computer scientists, it was a toy challenge because the data could fit on your laptop, and it was all in CSV format, so computer scientists could handle it. All right, so it was slightly simplified, but it came up with. It was before deep neural networks, so it came up with neural networks and boosted decision trees. This is a more recent one. This is when looking at these events come in, particles collide, and these quarks come out, which then dress themselves as ordinary particles that we know and love. And the question is, what was the original quark? And that's what they're trying to do in this, one of the LHC experiments, the CMS experiment, which involves many US universities as well as European. And so this is an example. They have convolutional neural networks, recurrent neural networks, fully connected neural networks, large numbers of parameters, and they've been playing around with these, getting some. You want me to stand still? Oh dear, okay. I'm not very good at standing still. I'll do my best, all right. Sorry about that. I could do that, yeah. That works, okay. Right, and then this is the sort of the initial stages, and what you see here is that they're claiming that these deep neural networks with some physics input. I'll stand here. Actually does best. So this is another chart. I mean, we were talking about the analysis of the final analyzed events, but you actually have to get there by analyzing the tracks, and you get large numbers of tracks. And so this is the latest challenge on Kaggle. This is what the astronomers are doing. They also have petabytes of data. So these guys have lots of data, rather similar types of data. And this is, for example, from the Dark Energy Survey, which was completed some years ago. And it's looking at various types of challenges, as you can see, classification, search for planets, and so on. And this is just an example of the sort of things that they've been doing. Again, prior to deep learning, they've looked at various different types of models, and then they've looked at how different machine learning algorithms, naive Bayes, K-nearest neighbor, support vector machines, neural networks, boosted decision trees, and then you can see which ones. I think it's boosted decision trees is the most effective on this type of data. So that's what they've been doing. What they hope to do, this is the latest Kaggle challenge from the LSST collaboration. They haven't taken data yet. It's a few years off. But this is simulated data, and they're now giving a Kaggle challenge where you can see if you can look at this time-varying astronomy. So you survey the night sky tonight, and you look at it tomorrow, and you see what's changed, and so on. A new horizon for astronomy. This is even more ambitious. This is a global collaboration. Europe and other parts of the world like Australia, and it's the Square Kilometre Array will be the largest radio telescope, and these are just to show you the sort of numbers they're talking about, and I don't think they've got real yet in their simulations. Terabits per second, hundreds of petaflops, many hundreds of petabytes per year. And I think we'll see they won't have enough money to analyze all that data. So they've got some way to go before they get to as realistic, I think, as the LSST collaboration. But that's going to happen probably by about 2013, 22.3 is what I meant to see. Okay, so this is where I work. This is the Rutherford Appleton lab, and we have a synchrotron, which isn't quite as big as the advanced light source, the advanced photon source at Argonne. We have a neutron source. We have a laser facility with petawatt lasers and so on. And we also have where I work, which is, does this actually work? This? Yes, it does. I work in this building where they have the particle physics tier 1 computing, so they regularly transfer petabytes from Geneva to here and then distribute it and analyze it here. And also, there's also this other facility, which is an environmental data center, and I'll talk a little bit about that. This is just an example from Diamond, looking at, there the revolution has been caused by actually not so much increasing the beam intensity, but it's actually the detectors have changed from things like CCDs to silicon. And so instead of, megabits per second being generated, you went then to, hundreds of gigabits per second, and now hundreds of gigabits towards terabits a second. And so the experimentalists now go back to their university, if they don't use the network, with armfuls of terabyte disks, and they don't know what to do with it. Right, and so they're drowning in data. This is an example of what they're trying to do, where the bottleneck here is a human bottleneck. So they're looking at tomography, looking at slices of a cell. This is the nucleus, this is the cytoplasm, and what they're looking for here are organelles of humans. This is actually not a human cell, but that's what they're looking at, and they're having difficulties actually tagging the data. So what the solution they've come up with at the moment to speed up the process from manual tagging is actually to do a halfway house. So this is the nucleus, this is cytoplasm. So they ask the user to annotate a small subset, and then they use a random forest classifier, then having got some input from the user to classify all the rest. And then they're trying to use other methods from machine learning to refine and get to the final data. But again, it's the human bottleneck. And this only speeds it up by about a factor of 5. It's difficult to use things like deep learning because you haven't got a tagged data set in order to learn on. And that's one of the problems with these. This is one from the Central Laser Facility, but it's actually looking at what's called super resolution microscopy here, which it was a news to me when I found out about it. Nobel Prize, you can go from 400 nanometers, which is what the wavelength of light would tell you, and by doing clever techniques, by putting on tags, you can get it down to 10 nanometers. So it's this sort of thing here. And then they have very ambitious goals where machine learning and AI can play a huge role. So this is the sort of thing they're using. It's called FLIMP, which stands for Fluorescence Localization Imaging with Photo Bleaching. Really attractive name. And what they're trying to do is identify, they have to do segmentation, and then they want to find good regions of interest to get data, then they can do an analysis. And here you can see the individual molecules here, and that's what they're tracking. And this is part of a much bigger vision where here we're just using, if you like, the picking of the things to speed up the processing because you can't do it manually fast enough. And then it will actually feed into a database, and you can use classifiers, machine learning with the patient database, and use research. So that's the vision. Machine learning and AI is all through that in this particular one. From the neutron beam, you have much less data because neutrons, you get fewer neutrons in X-rays. And this is a different type of, I've chosen this example, which is about extracting data from the machine readable literature. So you have scientific literature with tables and in it you have chemical equations and so on. Can you construct databases which are reliable, which you can then use? And this is a tool that's been developed by some collaborators in Cambridge, Jackie Cole and her team. And it's chemistry aware. So you use natural language processing, you use machine learning to improve the text mining, extraction gets better as the system goes on. And what you actually try and produce at the end of the day is an output where you have numbers, chemical names and things. So you can produce tables. And that's what they've been doing here. Again, this is part of a much bigger vision where you have, again, machine learning and AI playing a big role. So what I've talked about here is this little bit here, but they see also data enrichment where you have chemical calculations with machine learning, enriching data, and doing prediction and validation. So that's the sort of vision, and again, AI and machine learning are all through that. A quick thing about environment. So this is what they've called a super data cluster. It's an example of a high-performance data analytics architecture. What it is, you have a series of processors. This is out of date. It's probably about 8,000 cores now, and it's, I think, 16 petabytes of data. 16 petabytes, it's gone up to about 24. So these are all on fast storage, solid-state disks, and you can access them in many ways. So they're all connected by a CLOS network, high-performance, low-latency network, and you can either do an MPI calculation on some of the cores, or you can go to the processors that hold the big data, and so you can do parallel data processing. So it combines, the data isn't over here and the machine over there, it's all integrated together on the same network. And it's an interesting example. So what are they going to use this for? Well, this system stores all the climate change modeling data that you heard the latest results. So it stores all that data, but it also stores data from satellites. This is the Sentinel series of satellites, and they keep on launching them, and they generate petabytes of data a year, and they need to be processed before you can give them to users. And just to show you the predicted rise of data, this blue data is the satellite data rising from where we are now. It'll go up to hundreds of petabytes by 2030. And this is the simulated modeling as you get more sophisticated modeling, including ice sheets, including topology and all this sort of stuff, and biology in your models. So a lot of data, and I'm just going to talk about this data. And one of the problems that we're looking at is actually detecting clouds. And what you can see here is that the existing cloud algorithms to identify what the clouds are there are rather complicated, expensive, and don't produce very results. They often misidentify clouds and identify clear sky over land as clouds. So there's a real problem there. Can you do that? And that's what these guys have been doing, and we're now trying to do something better. But this is when they've actually used, for ground truth, they've looked at, this group have actually painstakingly labeled millions of pixels as to whether they're water, snow, or whatever. And this table shows you these are the correct identifications of clouds, and this is the machine learning variant that they've used, and they do pretty well. And of course, these are the misclassifications here, and again, it does better at detecting land, roughly the same as water, but we need to try and improve that. So the idea is that they're trying to produce label samples, and they're trying to use the community to do the labeling for you, citizen science type thing. So this is a major issue for detecting forest fires and all the sort of pollutions that goes with it. And lastly, I should get, because my title had engineering, I should just give an engineering example. So this is something that I'm doing with the University of Warwick. They have a remarkable organization called the Warwick Manufacturing Group. And this is something that I think concerns not only the UK, but also the US. We're going to be moving more towards electric vehicles. And one of the problems is the batteries of electric vehicles are very difficult to make. There are lots of cylindrical lithium-ion batteries, and it's very difficult to make them each identical. And so they age at different rates, and you can see the sort of spread of data here in the aging of the capacitance and so on. And it's therefore you have a very complex energy management system on it, and it's very difficult to predict how long this battery will last before it blows up or isn't any use or whatever. And that's the problem we're trying to attack here. And so what they have at Warwick Manufacturing Group is a rig to set up to do battery aging, and that's what they're trying to do. Previously, we've done it on rather short things, but we're trying to look at predictions which are, say, 10, 15 years, and so you'd like to be more realistic. So they're looking at telemetry from real cars using, but also aging rigs, where you'll combine data, modeling, and machine learning to actually find if you can predict the lifetime of batteries. So here's your modeling, a very detailed multi-scale modeling example. Here's your data which we're generating, and what we are trying to do is add probabilistic machine learning to make progress in predicting the lifetime of electric batteries for cars like Tesla and things like this. I do have some concerns about this exciting topic, and I'd just like to finish with those. One concern is I seem to remember it was Bill Gates, but I couldn't find any record of Bill saying this, so it probably isn't. But it was about how all the advances, despite the efforts of Jim and Size in NSF, are going to be made by companies like Facebook, Google, Amazon, Microsoft, IBM, and the Chinese equivalents, Baidu, Tencent, Alibaba, and so on, for three reasons. One, they have large amounts of data on everybody here, and unless they're Facebook, they won't let that out to anybody, and they do it by accident because it's their business, all right? So it's a lot of data, and that was the big breakthrough in deep learning, going to big data sets and big compute. Oh, yes, they also have unlimited computing power, and yes, whereas a university, even like CMU, has a department of machine learning, I don't know how many people are in the department. How many? 20 faculty. So, I mean, they probably have hundreds at CMU because you have them all over the place. But you know, Google, Facebook, Microsoft have thousands, and they also have people who can write good code. So how do we compete with that? And that's one of the reasons why I want to actually stress that the data I'm talking about is really, we can make it open, and we can use it to go and develop new algorithms. And this is an example that Jamie Sethian's been doing at Berkeley. This is the traditional convolutional neural network with different length scales, and he's proposing what he calls a mixed scale, fully connected network, where you don't need so much training data, because as I've said, the problem is having tagged training data. And this is a way of doing machine learning with very much less data. And so this is a new technique, and I believe by studying some of these things and how our existing algorithms, how well or badly they do, we can make some improvements. The other concern is the robustness and trustworthiness of this stuff. It's no use having a black box if you don't know where the results come from. And also, you know, how robust. This is an example from ImageNet. You've trained it to recognize a panda by showing it
thousands of images, tens of thousands of images. You sprinkle a bit of noise on it, looks the same to me, but now the system you've trained to recognize panda says it's a gibbon. Right? So these are a serious concern. They're being looked at by the computer science community, and correctly so. This is a similar example. This is a recent paper called The Elephant in the Room. So this is how you can detect things. So this is a person, these are books, this is a cup, this is a couch, and so on. And then you insert there, you'll see in here they put an elephant floating in space. All right? So it really is the elephant in the room. And now this system you've trained to do this recognition thinks this is a chair, all right? It doesn't recognize as a cup here, and so on. So the question is, how good will you be at recognizing real unusual events if you trained it on something that hasn't got there? So again, I have concerns about that, and that's good because that gives the community things to go work at, and we've got some interesting data that you can go play with. The last concern is about career paths. So this is a slide from a friend of mine, and this is how the professor writes proposals. Most of the time, the work is done by the postdocs and the grad students, and that's how research has been done in many fields. But increasingly, you're needing to have sophisticated software, scientific software of all types to support the experiment. And nowadays, with the data, you're having to have sophisticated data analytics. And so you sort of need semi-professional research software engineers and data scientists floating down here. And the question is, these guys are never going to be the PI to get proposals from NSF. So how do we support them? And I know that NSF is looking at these sort of issues, and I think it's an important one as we train people for the future. These people can have careers in science, but they can also have careers in industry. And I think that's an important element of training. So I would claim that the data, I think I'm done, yes. I claim that the data we're producing at the facilities is interesting and can be used and made open and could be a good, interesting area for people to experiment with different types of machine learning and AI technologies. Thank you very much for listening. Yes, sure. Yes.
So in your challenge about engaging academia versus private sector,
That was an observation. Okay. It wasn't a challenge. I think it's true that they will do things like natural language processing better than we can do in academia.
Well, so I take it one step further. What role can the government play, given that we are even less
No, the government have provided really some cool machines. I was really impressed having a presentation on Summit. You know, in the UK, I don't think we have 27,000 GPU cores on a machine, right? I know we haven't. I think providing sensible research infrastructure, as we heard from the two previous presentations, is really an important component. And I think the government has got that message. And so I do believe it's hopeful. I think what we're missing is the data sets to go play with. And that's what I'm proposing, that some of these data sets could be interesting to computer scientists. And I should also say applied mathematicians and statisticians, because it's not just computer science. Yes? Absolutely. So I'm forming a scientific machine learning group at my lab. And one of the challenges is, can we support the biologists, the chemists, who don't know all about Docker containers and singularity containers and things they don't want to know about. They want to do it at a higher level. And I'm not sure. I think that's rather difficult to do, but that's what we're going to try and do. The other thing I should say is here, these are meant to be somewhat generic. There are enthusiasts in both this continent and also Europe and Australia who are trying to do research software engineers. And the idea is these guys know about scientific software, they know about elements of software engineering and documenting and testing their programs, which scientists are not that good at, right? And so the claim is that they can be generic. And one of the propagator of this is a guy who used to be in particle physics. He's worked with biologists, he's worked with computational fluid dynamics engineers. He really is very portable. I'm not sure how generalizable. I don't think most people can move so easily from software in one area to software in another. But that's one can look at. I think it may be easier in the data scientists that we can create a generic set of data scientists. And that's one of the things I'm trying to do at the lab with these data sets, to see if we can produce some, if you like, some scientific machine learning benchmarks which can be trained from different areas where there is some commonality. But again, it will all depend on the user interface and whether we can make it for real users to find it useful. And the answer is not clear at this moment. Yes?
Ian Foster from Argonne in Chicago. So you emphasize the importance of having lots of data.
Yep.
Results, data from both unsuccessful as well as successful experiments. So as you now work at a national lab, have you thoughts about how to alter practices at national labs to get that?
Well, I do think that the attitudes to data are changing. It's taking time, but I think actually the 2013 memo from OSTP to all the research funding agencies in the US was, to me, a landmark, because it talked about the scientific results, not only in scientific publications, but also the data and the software. And I think that's a change, but we're not there yet. And it's true, when you look around, you'll find that some of the papers, the data sets that they claim to be based on, are not available, not visible, and so we have a long way to go. But I'm optimistic, and I'm also optimistic about the adding semantic information, as we heard. I think things like schema.org, extended by community vocabularies, are probably easier than the sort of RDF and OWL and these type of technologies.
Thank you. Well, thank you again, Tony. We will have a panel, so we'll have additional opportunities to ask questions, perhaps questions that span all of our speakers. It's a real pleasure to welcome next to the podium Dr. Warren Kibbe, who is the professor and chief of data officer at the Duke Center for Informatics and Institute for Informatics, and he's also the chief translational biomedical informatics at the Duke University School of Medicine. But I know Tony better when he served here at the National Cancer Institute as the director for the Center for Informatics and Information, CBIT. So thank you again, Tony, so much for coming to talk to us a little bit about the confluence that you see in biomedical and cancer research.
Maybe I'll take this too. I'm going to do my usual trick of having a very chaotic set of presentations. Usually I'm a little bit more organized when I talk, and I'll try to bring cohesion to it. However, I'm back to being now in academia. I'm putting a proposal in tomorrow, so I was up very late last night, and then I got a call at 4:18 from my wife that I couldn't understand because our internet went off and somebody was parked in the driveway with their headlights pointed straight at the house, or so she thought. So I had a rather short REM sleep last night, so I'm going to try to bring it all together. And what I think is interesting is one of the points I wanted to make is, I'll come back to this in a second. This was actually sent to me by one of our oncologists who was on safari in Africa. He took the picture, he had 4G network out in the middle of nowhere, uploaded it and sent it to me. So he made the comment that actually his cell phone reception in the middle of Africa was better than it was in Durham. So again, I think this is really changing the way we think about our world, the way we think about healthcare in particular, and the way we think about medicine is that, in fact, data itself is accessible everywhere. And I think what came home last night at 4 a.m. is that we didn't have a backup when our internet went down. That is our cell phone. That is, everything goes through our fiber system. And when a car crashes down on the local road and takes out everybody's fiber connections, we were really, frankly, having a struggle being connected. So thinking about robustness is a big deal, and that wasn't one of my topics, but now this morning I'm realizing that robustness is a really big deal. What I do want to talk about is that cancer is a grand challenge. So being one of the members of NCI, I really came to appreciate how complex cancer can be and how fundamental we have to understand biology in order to solve cancer. Something that's already been talked about a lot this morning, I'm going to probably skip over most of those slides, is that frankly, data generation isn't the bottleneck it used to be. And in fact, that's really changing the way we do science. The fact that being able to craft and copy down the data you're generating is no longer the right way to think about data generation really has changed us, but we haven't caught up from a workforce development standpoint. I want to highlight two different technologies that I think are really interesting. One, they generate an enormous amount of data, and then two, they're giving us a much more dynamic view of biology. And that's something, again, I think that if we really want to understand biological problems, we really need to do a lot more of. And then I'll go through a couple of vignettes, one of which involves NCI and DOE. And I see a number of my colleagues from the DOE here, and it's great to see you all. So just so you understand when I say cancer is a grand challenge, what I really mean is it requires deep biological understanding. And I'll go through some very specific examples of that. And of course, along the way, we have the need to really advance a lot of scientific methods, instrumentation, technology, the way we think about data and computation, and of course, generating mathematical models that we can, in fact, prove or disprove represent the real world. And again, I think just to echo what Tony already said, it's really, the data is crucial for all this. So this is the poster child that drives a lot of people wild. When you think about genomics and sequencing, the cost of sequencing has dropped so incredibly dramatically. And so there's Moore's Law. If it just kept having every 18 months or so, that's the line we'd be on. And you can see that it has dropped dramatically, way faster than anyone had predicted. And of course, that's driven then the amount of data we can generate. So just to put this in a non-semi-log form, you can see essentially the cost of generating data now on a genome level is about $1,000. This is a little aggressive. I think it's more like $2,000, generally speaking. But at the same time, that's really enabled now consumer genetic testing. So we've gone from having a few thousand people, few 100,000 people with genomic data of some sort, or actually genetic data of some sort, done 2 decades ago to now more than 24 million. And that's driven a lot by Ancestry.com, so folks that want to know where they came from and were those family stories really true, and 23andMe. I can tell I'm definitely a little confused this morning as I can't figure out where to put my hand. So this is just because everybody needs an XKCD slide. But I want just to focus that actually DNA is only a small part of biology. It's an incredibly small part of biology, but there's been all this focus on it. And so I'll try to stay away from just talking about genomics. Really, biology is this wonderful machine. And if you think of DNA as the source code, well, every cell is a different processor, a different set of hardware, and you can't really predict what that hardware can do just by looking at the source code. This is a slide, and actually, I think this goes back now almost 15 years ago, that I put together just thinking about the different size scales and time scales that we have in biology. And what's not in here that I've come to really appreciate is incredibly important is really all the networks that connect molecules to organelles, to cells, to organisms. And of course, then at the social level, we all interact every day. And I think, again, the way we now have data and social media, we can start to understand some of those social aspects, but we really don't understand the complexity of biology. So this is one of the technologies that I think is really exciting and is changing our ability to look at basic molecules. Cryo-EM, and it allows us to get down to X-ray crystallography size scales, but do it in ways that weren't possible. So if you have a protein that's bound in a membrane, that you really can't crystallize that, but this is a technique now for flash freezing a membrane, being able to look at atomic level data coming from it. And of course, as Tony mentioned, it generates huge amounts of data, and nobody knows how to manage all that. So data management is a big deal. Likewise, single-cell technologies, and again, sequencing is there, but it's about proteomics, it's about metabolomics, it's understanding the microenvironment, so what around a cell is actually allowing it to respond to the cells that are around it. Those technologies are now really changing our understanding of basic biology. When I first moved to NCI about 5 years ago, I had a chance to see someone doing real-time imaging of vesicles budding from a membrane, and this has been around for a while for vesicles in neural cells, but watching that every cell, in fact, at a different scale, is releasing vesicles, and they come off in a very coordinated fashion, and they go back onto the cell, and that there's these waves of communication between cells in our body all the time. Was just it's obvious in retrospect that that's what happens, but it wasn't obvious until you actually saw it. And we still don't really understand how to harness that. So again, I think one of the things that's really changing in biology is this focus on dynamics. And we need people who can both understand the data that's being generated and how to analyze it and how to put that in a biological context. So now I'm going to switch to a basic science problem, and this is the joint collaboration with NCI and DOE on looking at RAS. So for those of you who don't know, RAS is a very frequently mutated set of genes. One of them, KRAS, is mutant in most pancreatic cancers, and in fact, that's one of the reasons why pancreatic cancer is so hard to treat. We don't really have targeted therapies that hit cells that have KRAS mutations, and in fact, that's one of the first things you look at in lung cancer is if the patient has KRAS mutations, you don't give them the normal therapies because they will not work. So, and you can see that KRAS mutations roughly cause 1 million deaths every year across the world. So just to give you a little bit of biology about it, though, it's a GTPase, so that means it binds, RAS binds GTP, it converts to GDP, and while it's bound, it's in its active state, and it's a signaling protein. It spans a membrane, and then there's a cascade of events that we believe, again, in this cartoonish way, that's the way it works. So back in the 80s and 90s, pharma spent an awful lot of time and money trying to come up with molecules that would target KRAS, and they failed. So fast forward 2 decades, and the NCI said, well, maybe now that instrumentation has changed, this is a good time to try to target KRAS again. So they started the KRAS, or the RAS initiative, and I was very fortunate to get the chance to interact with a lot of colleagues at DOE and say, can you help us with this problem and understand the data that's coming out of looking at actually this one molecule plus a couple other molecules and start to really model that at a much deeper level than we ever have before. To make that happen, and I won't go through this in a lot of detail, because actually I think Fred, you may go through some of this more, so Fred Streitz at Lawrence Livermore. Can I show the right one here? So again, one of the reasons I mentioned cryo-EM is that's been critical to understanding KRAS because it is a membrane-bound protein, and we really didn't have a lot of detailed atomistic level data on KRAS. But building up this multi-model experimental data was difficult, but then knowing what to do with it has, again, required a very different way of thinking than the biomedical research community typically thinks. Being able to then create these predictive simulations and then feed that back and see, well, let's do the next experiment, and does that really work? And in the interest of time, I won't go through all of these aspects, but it's really about now trying to use machine learning and deep learning techniques to really speed up that whole process. So I'm just going to build that. Whoops, I built that too fast. So you see, here's all of the problems that need to be solved around just understanding these few proteins bound to a membrane. So it's understanding the membrane itself, understanding what those proteins do, how they interact. And that requires a tremendous amount of computation. So again, Summit and Sierra have been instrumental in getting some of this to actually work. But at the same time, really what this is all about, it's really about team science. Right? It's about bringing together computational expertise, modelers, biologists, the data scientists, and people who understand what's relevant in the clinic as well. So I think, again, this team science piece is incredibly important, and it goes back to workforce development. Just to give you at least a little bit of math today, there's some very nice equations that help you understand how a lipid bilayer may really work, and I won't pretend to understand all of the ramifications that has when you're actually trying to show how two proteins interact or a protein and a membrane interact. But it's critical that there's, in fact, machine learning in thinking about how do we optimize all that computation. So, and just to highlight that team science piece, here's a list of some of the people, not all the people that were involved in this collaboration. And I don't have time to thank them all or even do more than put them up here on the slide. But again, I think what's really important is as we're solving some of these problems, we can't solve them alone. We really do need to have teams of people. And that, again, is very different in biomedical research today than it was 20 years ago. So I want to give you one last example. And how am I doing for time, Susan? Wendy, I'm all right? Good. Ooh, okay. So the other challenge, thinking about this from a healthcare standpoint, is really how do we go from individuals to healthcare teams to the population? And those are very different views of the world. So really looking at that basic science side of things, we're looking at individual cells inside of an individual. And that's very different than trying to look at the behavior and the implications both from a policy and from a healthcare delivery standpoint. Well, how do you do this now reproducibly so that you can provide better care across a large population? And one of those questions is, and this is surprisingly a difficult question. So we're sitting here in the National Institutes of Health, and I think we all have an internal definition of what health is, but that's not really a focus for us as biomedical researchers. We're really always focused on what's disease. So it turns out that because of that, or actually not because of that, because of biology, measuring normal is really difficult because we all have different normal set points. And we, right now, don't do enough measurement across the whole population to understand what's normal for each of us. So that makes it very hard then to be able to understand, well, when I see a change, is that a change because now I'm measuring someone that I haven't measured before and that's normal for them, or is that actually a disease process? So something that I appreciated when I first lived in Europe is I was given, the first day I went in to see my primary care physician, they went through and did a ultrasound scan of my entire thorax. And I asked them, why are you doing that? He said, well, if you come back in and you have some symptoms that are around an enlarged liver or prostate, we want to know, well, what was your normal before you had those symptoms? And that's something that, again, in this country, we don't really think that way often enough. We don't think about, well, what's normal for the person, and how do we accomplish that? Or how do we measure that, rather? So again, I think we have a lot of hard work to do in just thinking about what's normal. And at the same time, we have these enormous opportunities across all these healthcare systems to start to do really interesting machine learning on images. So these are some CAT scans of brain CTs, looking at pathology slides, and then looking at actually just a normal photograph of moles. And in each of those cases, machine learning approaches have really transformed the way we think about handling these data at scale. So we can throw as much data as we generate across the whole country at these algorithms, and now they're better than most of the radiologists and dermatologists and pathologists in classifying them. But of course, classification is only part of the challenge. So I don't want to say that machine learning is going to completely remove the need for pathologists or radiologists or dermatologists, but that part of them doing their job in classification, we can do it better. So just to kind of bring this back, and this is a conversation that Bob Hanish and I just had very briefly, is that in fact when you look at EHR data across the country, we throw away all the metadata about the labs. So it never ends up in the electronic health record, which makes it really hard for us, again, to do that detailed measurement of, well, was that difference because of a difference in instrumentation? Was it the protocol that was being used? Was it a bad batch from that vendor? We don't capture that and move it forward. So in fact, we can really make more effective use of machine learning. So I think that has to get solved. At the same time, now that EHRs are in place, we have an enormous opportunity to leverage data that we've never had access to before. So this is, I went in for my physical recently. These are actually my tests, so I can show them. I'm allowed. And it's that was me logging into my Epic MyChart portal. What's interesting is I can then go to my health app on my phone, and I can see all the same data. And what's really cool is, of course, it's all exposed through a JSON FHIR API. So now that's all exposed, and we should be able to learn from that. And again, I think that's where the world has changed in some really positive ways in a very short period of time. Again, biomedical research and healthcare need some help catching up with that. So these are just some of the opportunities I guess I see right now in the world, is that in healthcare we really don't consistently make data accessible. It's often not structured. Again, NLP can help. Deep learning approaches can help. But again, a lot of what we generate from a NLP standpoint was actually captured in a structured way somewhere, but it didn't get pulled forward. So this is my second to last slide, so I will finish here. So outcomes aren't connected to care. So my wife had surgery on a dislocating shoulder, and the surgery went beautifully. She's never dislocated again, but the clinic never called her to say, did that work? Because in fact, it's known that it fails in about 5% of the time, but they never asked. So is she on the 95% or the 5%? So we often don't connect the things that we need to connect. And then along that line, we really don't understand trajectories. And so this is, again, that health disease trajectory. And we all come in and out of different disease states with time. And we really don't have the infrastructure necessary to compute on those trajectories. And again, I think that's a lost opportunity. It's something we really need to do. And as I said just now, more and more data is really digitally first. So we're generating it as digital data. Then we ask a pathologist or a radiologist or some other person in the healthcare system to jot that down as a note. And then we use that, and that's what ends up moving forward. And again, I think that's something that we clearly have to fix. And I think you all are in a good position to say, well, that's not the right way to do machine learning. We should have access to the raw data. Along the same lines, once we have the data, clinicians need decision aids. And they need to be functional, and they need also to be exposed and not black box. And good user experience and responsive design are critical to all this. Again, I think there's some really interesting workforce development pieces there where we really do need to have those professional software engineers, data scientists, and then, again, the clinicians working hand in hand. So with that, I will just close with what precision medicine means to me. And really, it's about understanding all these different pieces, everything down from how do individual receptors on a membrane interact to create this enormous complexity of biology, this beautiful complexity that's human beings. And then, of course, when we're diseased, how do we properly intervene and solve those disease problems? So, thank you. I don't know did I chew through all my time? Great. So I think that was because there was a new platform that came out that a lot of people bought. That's kind of an artificial bump. It was trying to reflect the cost of that investment. But the actual cost of the sequencing never went up. It's just the investment. Sure.
So on the same thing on the sequencing chart.
Yeah. Yes. No, so that was actually a change in technology. So it moved from old gel-based, lane-based sequencing to what's called next-gen sequencing, which allows multiplexed sequencing. So you can have a single capillary, and you can do tremendous amounts of sequencing in a capillary. So it's really about the chemistry. Chemistry changed, and then it was also about the change in the detectors. So both of those were responsible. Yes? So right now, and I'm not, so just to be clear, I'm not a sequencing guy, so I should be careful what I say. But right now, at least, those long reads are incredibly important for us to understand parts of the genome that short reads can't read through because they're too similar. Understanding things like structural rearrangements, they're wonderful for that, but right now they don't run at the same scale as if you will, the traditional 2006 or so next-gen sequencing. So I think it'll change our understanding of biology in fundamental ways, but I don't see it actually changing that curve. Yes. I'll say absolutely. I have a great story that I can see. I don't have time to tell. So I worked actually. So although I'm not a sequencer, I did do a lot of bioinformatics and worked with sequencing cores. And I had the pleasure to work with Ann Yoder, who's a lemur basic scientist, and she was looking at lemurs, both the modern population and then the population that lived in Madagascar about 50 million years to present, and had ancient DNA samples that she had been sequencing. After I'd been running all the bioinformatics for a number of years, I realized there was a stack of CDs, this is a while ago, stack of CDs from her sequencing. And I said, Anne, I know these are incredibly valuable samples that you can't ever replicate. Do you want me to hold on to those data? And she thought for about a millisecond and said, no, throw them out, because the technology's changed so much that I can replicate all that if I need to with a much smaller amount of sample, and it won't have all of the issues that the old technology had. It'll have new issues, that's absolutely true, but they'll be different and they'll be hopefully better. We'll be able to better generate those. So I thought, here's an absolutely a set of samples that you cannot recreate, and she was just thrown away. So again, I think that's an important part of this. If there's no reason to maintain the data from either from a legal standpoint or from a care provisioning standpoint, I think there are lots of data we can throw away. Sorry, that was a long answer. Yes. Actually, I'm. Yeah. Yep. So I think that's an incredibly important question. I'll say that having been involved in NLP for probably a decade and a half at this point, it was fascinating for me when we first started looking at reading through pathology data, and this was actually around pulling out the concepts in those pathology reports and then de-identifying. And we could come up with about a 85 to 90% accuracy of both de-identification and pulling out the concepts. Tried running that through an IRB, and they said, well, you're wrong 10 to 15% of the time. We can't allow that. However, from a human standpoint, the folks that actually do that review are wrong about 20% of the time. So again, I think it was fascinating that just from a policy and a human perspective, we'd much prefer to point at a human being than point at an algorithm as a source of error. I think again we're right now still in a place where we're comfortable with human error, but when there's a single car crash like Tesla had back about what was that? Almost a year ago, I was thinking the one where the car hit a barrier. That people stopped buying the car for a while. Fortunately, I had my Tesla order in, and I got my car much quicker because of that. But it was interesting how again we're just really we need to have a better intuitive feeling for where errors happen and how to interpret that as a society. Again, I think that's more of a society question than it is just technology. But again, it is science and technology and society. So I know I'm way over now. Thank
you so much, Warren. And again, Warren will be part of our panel directly after the talks. So next, I'd like to welcome Pete Beckman.
Oh yes, of course.
That will be important. Pete also is a well-recognized leader in high-end computing and computing systems. He is the co-director of the Northwestern Argonne Institute for Science and Engineering. And his research areas includes all aspects of exascale computing, as well as architecture, runtimes, and basically how we make data systems work. So thanks so much, Pete, for coming in and giving us your perspective on this important topic.
Thank you. And got the slide advancer. Thank you, Tony, for debugging the lapel mic because I have to walk around as well. And thank you. And I think it seems like the goal today is to sort of outline some of the interesting spaces that we can then have more further discussion on. So I'm going to try and just present some of those concepts, things that we should look at. And I really liked the panel framing questions. And so I'll try and touch on some of them, but I simply can't have time, don't have time to get them all. But let me start with a little bit of a guilty admission. So, for years, there have been some workshops working on big data and extreme computing, BDEC. Jack D'Angara, myself, Dan Reed, others, Michaela in the audience, and others have been working on that. And this picture here came from a 2015 article that D'Angara and Reed put together, and it sort of shows, big data and extreme computing. And one of the things that is striking about this kind of approach is it reveals our biases, which are, oh, it's a software stack issue. In other words, all I have to do is boot your software on my supercomputing, and then I've solved big data for you. And so, you can see where that comes from. I mean, it's easy. Here's computer science, computational science, HPC. Over here, data analytics. We boot these things and we supply them, and then we've tackled big data. Recently, just earlier this year, this was a meeting over here from the French who are participating in this BDEC2 effort that we're working on. Also has this similar picture. Oh, here's HPC stack, here's the big data stack, and oh, now there's a deep learning stack. We just add this stack on, and now, again, we're good to go. Now we just went from 2 to 3, but we're good. And what it's missing is something that actually people who work in the accelerator community and the microscopy community and other communities, which are the place where the data comes from, and the end-to-end problem is really what's driving some of these issues. And it's not just get all my data to the supercomputing and then pick a stack, 1 out of 3, and I'm good to go. So I'm going to be talking today about one of those sort of end-to-end pieces. It's this computing at the edge. And again, it's something that we didn't really consider several years ago. And in fact, this term edge computing has only recently come up, even though we've been working on it for several years. People had all sorts of other names for it. But this idea that we want to run code, I'll say on the left-hand side, and on the right-hand side where we have all of the HPC and cloud stuff, that we have to actually run these in union, and they're together. And it's not simply make one code over to the left and one code on the right and get a TCP/IP connection between them, but they're iterative. They're actually refining and improving each other. Now, initially, we look at these things as thinking, okay, on the left are all of the new sensors and everything from LiDAR that will be in self-driving cars and other things. But also, we have large experimental facilities. And it's really the same problem, which is that we have all of this data, and we have to move computation to the place where the data is generated, because we can't possibly move it all through the network to where we want to crunch on it in the cloud. So there's crunching that has to go on at both ends of the spectrum. So that then leaves us with this new computing method, which is very interesting, which is that we will do deep learning and analysis on the large, on the global, and then we'll do inference and lightweight machine learning out at the edge. And so I'm going to now run through a couple of examples of this just to motivate and explain where this is happening and how the convergence, this workshop on big data, AI, and machine learning come together. So the first question that people ask is, well, look, I could just move all the data out to the cloud. I don't really need computation at the edge. But there are a number of very good reasons why you have to do this. Now, I gave a talk at Johns Hopkins last week, and Tony, I don't remember his last name, from the Large Telescope in Chile, says, well, actually, we have, 300 gig fiber links from Chile all the way to NCSA, and you're crunching the numbers for them. Well, so that's an extreme case that, okay, they actually have all the fiber necessary to get from their experiment to the place. But most of the time, you're crunching on the data, and you need to crunch on it locally because there's just too much data. And that's the case for DNA sequencers. It's the case for every device. So we have more data than bandwidth. There are times when latency is important, when you actually have to make a decision and you can't wait for it to go across the country. There are privacy and security concerns, and that was one of the panel questions, and hopefully we'll have time to talk a little bit more about that. Resilience is important. So being able to run a city or run an infrastructure, even if part of it is down, is aided by having computation out at the edge. And of course, there's also an energy savings by doing this. Okay, so I'm going to give you some examples. And the first among these examples comes from the NSF project, the Array of Things. So it's an NSF-sponsored project, and it's putting sensors up in Chicago. I lead the team at Argonne that had developed the platform that they're using for the Array of Things. So that platform we call Waggle, but it's an edge computing platform. It's an edge computing concept. I want to run parallel computation where the data is generated. And so they're going up in Chicago, and the unique edge piece, the piece I'm going to talk about today, is that in that platform there are several two single-board computers with GPUs, and they're doing computation using computer vision live in real time on the data, and that's really the unique edge piece that links this AI to the cloud. So that lets us, sort of the way to think about this now is rather than software stack and, show up and now I move from 2 to 3 software stacks, is really there's a computing problem that goes across the spectrum, that I need to run code and run data analysis all the way from these lightweight devices that some of them are doing simple FFTs, right? All the way to the middle piece where I might be doing lightweight machine learning or audio analytics or machine vision or something like that, and then learning out at the end in the cloud. And back and forth this goes. So an example is from transportation. This is a very simple example trying to understand pedestrian movement. And the purpose of this is to be able to predict and understand when a human-car interaction is about or could cause an accident. So there is a real-time component. There's a privacy component. We can't ship all of the data all the time to the cloud. No, this is a decision that should be made locally, looking at the data and being able to analyze where humans and cars are interacting in a dangerous way. Also, looking and classifying images. This is on Lakeshore Drive in Chicago. There's actually snow on the ground, as you can see. And being able to do that and make models, again, without transporting all the data, but computing out on a physical device as part of that AI and big data stream. The same is true for flooding. In fact, we just received some NSF funding to Northwestern University to continue this project. In this project, we're using cameras and sensors and looking at extreme data. And so this is the cloud to the edge. So in the cloud, on an HPC system, are weather forecasts. And they're running in this what people call nowcasting, the ability to look at the weather within the next minute, 2 minutes, 10 minutes, hour, maybe 3 hours, that sort of range, and then looking exactly what's happening on the edge in the neighborhood. And in fact, here, looking at water, this is a famous building at a park, looking at water that's accumulating and using computer vision to automatically link those two and make a prediction about homes about to be flooded. So again, a computation that links cloud computing and forecasting with edge computing. The same for disaster and fire. So we just have recently had a postdoc from Australia visiting. They want to deploy these concepts to handle management of fires and floods. And he just returned, and here he is down here, Nickel. And they have a set of tools which they can use to predict. Over here, sort of a dashboard, they can predict fire and flood risk, but they really need the computing, so that's the cloud computing part, but they need the edge computing part to actually look at data in real time and tell, is there a fire driving the kangaroos and wallabies to the other side? Is there a flood that's actually going to break up and cause a problem in an urban space so we can't transport vehicles from here to there, rescue vehicles can't get from here to there. So this kind of processing, linking, and this is their picture, linking real-time information and doing remote sensing, live scanning, sensor networks, this is their problem, right? Machine learning, computing, and computing at the edge. We have people who are doing the same thing, even in ecosystem modeling, wanting the same sorts of answers. This picture here is looking at a green roof and analyzing which plants grow better on this particular green roof. And the way this is normally done is a grad student goes out with a camera, a digital camera. They measure the distance between the camera and the ground. They take a picture. They come back several days later. They take another picture. They come back. They set up a camera. They might set up a webcam, but still the relative plan is that a grad student will draw and annotate the images and then decide which one is growing and at what rate. Using computer vision and machine learning, you can do automatic segmentation. These are the kinds of things that, whether it's particle physics or it's biology, that are linking the incoming data and analysis of that data with modeling and simulation in the cloud. And finally, one more example is from manufacturing. And this is flame spray pyrolysis at Argonne, and they're creating nanoparticles. And there are many, many knobs to turn in order to to actually have the device work as intended. And those knobs are based on what's happening in the device. So you have a whole bunch of sensors, and you're essentially monitoring what's happening, but then have a prediction and a simulation that can give them some feedback, but there has to be local computation immediately on that data. That's this linked edge cloud computation. So as I mentioned earlier, we sometimes think of small devices when we think of this computing that's moving out, but it's the large facilities as well. And so at Argonne, in fact, Ian, Tekken, Beiser, and others are working on applying computing right at the cat, right at the place where there's a experiment being done, calculating based on the data coming in off the experiment, what's happening in the experiment, and is the experiment, first off, is it right? So people, waiting several weeks or waiting even days before you know is painful when you have a limited beam time. So they want to know immediately, can we analyze the data and am I on the right track? But second, can I adjust the parameters in any way in order to improve the experiment sort of in real time, or even stop the experiment when I've gathered the data so I can move on to the next experiment? So the science community is not necessarily the only pioneers in this space. And so Amazon and other companies are readily adapting to this linked model of computing and machine learning from the cloud to the edge. And Amazon released this as a developer kit several months ago. This is the one that's in my office here at the lab. And it is designed to run a machine learning edge inference algorithm in the device, and then with a Lambda function, which is one of these Amazon services which can cause a trigger, can trigger something and cause an event to happen back on the cloud. So here, in this case, it's loaded up with the face detection algorithm. Now, again, the intent is not, this is a privacy issue, not to send all the data back, but just to recognize, like you do when you pull out your cell phone and you take a picture and there's a little yellow box around your face, right? This is the intent, is just to identify there is a human in the room, right? As opposed to your dog or panda who thinks it's a gibbon, I don't know. So that counts, and then if that's detected, it triggers this Lambda function, which you can then write code in the cloud, which says, oh, I'm going to text something, I'm going to run a function, I'm going to open a door, I'm going to do whatever it is. But again, these are linked components which require machine learning and training on the new device and computing, coupled computing out at the back. And because of this new environment, companies are racing to develop hardware for this. So, I come from the supercomputing space, so most of the hardware over the last several years that we've been looking at are all big server chip machine learning, and we'll talk about that, I guess, some more this afternoon. And, Fujitsu is in that space, and Cerebras is in that space, and NVIDIA, and many other companies are working on that. But there are now a bunch of new starts for very lightweight, low-power inferencing in order to match the heavyweight server-side learning that's happening. And so there are companies, Google just announced that they have a small piece. It was supposed to be out in October, and I think they have another day, but I don't think they're going to make it. They will make that chip available via the cloud initially, but then they've promised, they've said that they would sell them, that you could actually buy them separately, and they would be disconnected from Google, which that sounds like a strange thing, right? Disconnected from Google. But selling those chips and getting them out, and there are other companies doing the same thing. And so this is a very interesting advancement for our big data and extreme computing space. So now wrapping up, going back to those questions, what's possible in our field now at this confluence of HPC, cloud, big data, AI? I would say that right now we have a lot of hand-built solutions. So one of the problems that I see is that we don't have a theory of computing. We don't have a way in which we're thinking of this problem as a single problem that has machine learning and cloud pieces and edge pieces, and these are linked. There's no way for me to, for example, propagate error like Tony mentioned earlier. I can't reason about how many iterations in the learning space I need in order to improve my piece at the edge. Those pieces are very disconnected at this point. It's really like completely disconnected distributed computing. I get an IP address here, I get an IP address here, and I'm sending some messages. But from a computer science perspective, that's very weak. What's on the horizon in terms of architecture and algorithms? Again, this computing continuum, being able to address this as a single research problem, I think is on the horizon. There will be edge hardware that evolves that will make this more interesting. What are the bottlenecks in creating these smart algorithms? Right now, I think it's a programming model. As I said, we have a very sparse view of how these glue together. The Amazon view is actually one of the most cohesive, but it's simply stringing together a bunch of web services. That's not really a programming model yet. That's, again, just a linking of call chains. And do you see do you see security and privacy challenges? Absolutely. One of the issues here is we're comfortable running very large computation in supercomputer centers. We're pretty comfortable running software on our phones in our pocket. We know sort of, okay, when Apple is updating it, and in the background some apps get updated. We have a handle on that. The notion that we run software in our city, in our infrastructure, that someone can write a piece of code that lives in the network, in the highway network, in the buildings, that the codes are interacting and gathering data and processing it, analyzing it. We're not comfortable with that. We really have not built the models and structures, the equivalent of virtual machines and Docker containers and all of these things. How does that apply to when I want to program a city? What is the simulation model that I use for that? When I want to change how the traffic lights respond. So just one example of that I'll give you. We were talking to folks from Detroit. We're deploying some nodes there. And they said, I have this question. If we write the right kind of algorithms to look at the street, could we tell if someone's trying to cross the sidewalk who has mobility problems, maybe in a wheelchair with a cane, and if they're not going to make it across before the light would normally change to green and send traffic their way, should we, could you do that? Could you, think about how would you write code to do that? Well, that's a fantastic problem, actually. It's a really, you love problems like that people just hand you and say, yeah, we could do some analysis. And they even came back and said, all of our new traffic lights have this new interface that allows the city to remotely program and control them. So you can start to imagine how this looks. But then, of course, from the cybersecurity and the privacy and how we feel about this, there's a bigger question about safety and real interaction between edge computing and what we compute there and what happens in real life. That's a big question for us. So I think that is a fantastic challenge for the group to consider. And with that, I'll wrap up.
With 10 seconds left?
All right. So do we have time for questions? Okay. Yes, Tony.
Tony Beasley was
Beasley, thank you.
He's the director of the National Radio Astronomy Observatory. They have a big ALMA facility at 1,500 feet in the Atacama Desert.
Yeah.
Where they have actually a petaflop correlator machine up at 15,000 feet. And the question is, I think it might be worth interesting to see if you can do some edge computing up there, as you've got a big machine.
Yeah. Yeah. It's a good, and there's a real-time component too. I'm sure that Bill is aware of this and the other Bill, because of the computation, but they want, if something interesting happens in the sky, they want to, text every astronomer on the planet within 10 minutes, where to look. So 1 minute. Okay. And apparently even normal people like me who are not astronomers can sign up for the alert message, but I'm not sure what I would do with it. Questions? Yeah, Sandy.
So I like your question on privacy and security. Do you see the communities, and I'll say you've got the cloud providers, you have the states as you work with in the federal community. Do you see people coming together to address these challenges? Because it's not going to be us in high-performance computing. It's going to be the lawyers and some cybersecurity experts and things like that. Do you see enough movement in this area? Because I think that's going to bite us.
Yeah, it has been hard. Now this is where, so Charlie Catlett is the PI for the Array of Things project, and he has spent hours and hours with the city of Chicago working on public documents, public comment periods. Every time, if we want to change a comma in one of these documents, it goes out for public discussion. And, the public has interesting opinions about what happens with data that's collected, right? So I think we've made some progress by going slow and having public discussions and meeting with officials, and even meeting, like, Charlie has met with aldermen and, these public meetings where it's open mic, and anyone can come to, and again, when you open the mic, anyone can say stuff, right? So, but we still have a long way to go, I really believe. And also, we don't have yet a sort of a cookie cutter model for how to take sort of that small success and say, all right, now some other city wants to do something. Where do they start? And there's, we of course give them everything we've done, but they're really sort of starting from scratch with that opening, handshake to a city saying, hello, we're your local university and we want to do some science, So, but we have several cities, Portland, Seattle, Denver, Chapel Hill, who we're partnering with on this. Yeah.
So I see you have the edge, the cloud AI, and what's possible now. What about the other direction, cloud to edge? Do you have any ways of pushing things that you've learned in the cloud out to the edge?
Yeah, that's a very good question. So we are doing that. One of the things, in fact, here's a small technical challenge, is that right now in these computer models, these machine learning models, the model is huge. These standard vision models can be, megabytes and, hundreds, right? And in fact, with the deployment we have in Chicago, we opted for the cheap route of a gig a month data plan per node. And so we can only afford right now to update the model, just the inference model, a couple times a month, right? So there's a lot of math that will be happening. I'm confident that people will work on compressing those things, but that transfer the other way is absolutely essential. And the other thing that I should mention real quick is that global view is required for local view too. So we don't talk about this too much, but when you see something globally, whether it's weather, traffic, that should inform the local, because that changes the algorithms that you might run at the edge. You know that bad weather's coming, so now I'm going to turn on this other detection, this other processing, because I know what's coming, right? And so that loop has to work well too. Yeah. Yeah, so it's a good question. So one thing I worry about is the open source, open framework that we need. We don't have anything yet. Everyone's going to come out with new hardware. We usually build stuff on top, but that end-to-end, programming framework is lacking. And so everyone has to do their own thing. And if I were to come and say, hey, who wants to volunteer to write that Detroit code? Well, what would you write it in, and could you run it on your platform and on someone else's platform? So we have a lot of work, I think, there to open that up.
Sorry about that.
Was that
Okay, one last question, then we have to move on. Great, thanks. And thanks so much, Pete. All right, so we've had some really amazing talks from each of our 4 panelists. And I just want to open it up first with a thought and a question. So you've heard a lot about different types and different forms of computing. There's an emerging paradigm of computing from edge to high-performance computing and just almost everything in between, and how that matches to our ways of scientific and industry models for algorithms and for software. And I just want to ask you, now that you've heard all of the talks, panelists and colleagues, what sort of strikes you as things that are challenges, and where is our greatest opportunity, if you don't mind addressing some of that? We can go in any order.
Okay. Well, I tried to give some indication that, we're just scratching the surface of the possibilities of optimizing and applying machine learning to a whole pipeline of data generation to data analysis. And I think that will have huge impact in a lot of fields. Obviously, biomedicine is one, but also material science and stuff like that. So the applications will certainly generate some new innovation in science, but also I'm optimistic that if we can get the computer science, applied maths community looking at some of these data sets and looking at the scale of the data sets, that we can do some advances in some areas of machine learning where we're not going to compete with industry. So I think we can actually make progress on the challenges in the open space, if you like, of the engineering and health challenges facing the world in the next decade or more.
Warren?
So just to follow up on that a little bit, I see it, there's 2 sides to a lot of these questions. One is that, if you will, it's a data representation question and how we think about data. Something that's been very exciting for me to see is that, again, I brought up dynamic biology, but it's frankly thinking about the temporal aspect. And again, I think Jeff had in almost every one of your movies, there was you were asking the cars to predict where different things were going to be, and thinking about biology, that's incredibly important. But the other side of it is thinking about it from a trust standpoint. So how do we build things that are both trustable, and then how do we build trust? And that's really a people question: is how do we build trust in these systems? How do we build trust that, in fact, when we put a prediction in front of a clinician, that they can see the evidence behind it and trust that, in fact, the algorithm's done what they expect it's done. So, and I think potentially there's some user experience pieces to that. So how do you expose the data behind it, the evidence behind a given prediction? And then there's how do we build it from a human standpoint? How do we actually trust that the systems we're building are really trustable, and how do we enable that?
But that also means you have to have, the algorithms have to be understandable, that you have to understand if it's going to predict that I'm going to get pancreatic cancer in a month's time. I'd like to know why and how it came to that conclusion.
Absolutely. So there's again, I think that's the evidence behind the prediction, if you will. And maybe that, Jeff, thinking about the two models you presented, the reason the second one's much harder is it's, in some sense, it's more of a black box.
Thank you. Pete?
Yeah, so, in computer science, we love our abstractions. Think of something once and reuse it as many times as you can. And one of the things that we're, I think, still lacking are how we're going to program and these abstractions for this big data infrastructure and machine learning infrastructure. And if we look at this, we've done pretty well at fielding supercomputers. You have Jasmine. The Oak Ridge has Summit recently. Argonne is working and has machines. What is the equivalent infrastructure for this sort of end-to-end science? What does that look like in a generic way? Not solving it just for biologists or just for astronomers, but what is that that infrastructure that we can all share? And I think that remains a pretty big challenge for us. It's not a matter of us just jumping up to the whiteboard and saying, okay, well, let's build one of these. There are real new ideas and concepts that we need. And then we have to figure out how we share infrastructure in that space so that we can build things and have a national, what is it? We know sort of what it looks like to have a national supercomputer. What does it mean to have national infrastructure that supports this kind of end-to-end computation on data? And how do small players participate as well as a few large facilities?
Fantastic. Jeff?
Great, yeah. I was going to talk about trust as well, which was already brought up, so I'll just I'll skip that. The other thing I would mention is I think it's fascinating that we often think of our compute resources and our data in terms of utilization. Well, okay, look at all the processors. Are they full? Look through your data. Has anyone tapped it lately? I guess that means we should keep it. But really, we're entering a regime where the question is much different than that. Yeah, you burned a lot of electrons and you kept everything busy, but from a utilization point of view, were you computing useful stuff toward the end goal that you're working on? And that's where I think we've really got a long way to go in terms of being able to specify what is the problem we're trying to solve here, and then what is the right decisions to make in terms of resource allocation toward that problem. If we're trying to test our self-driving car, what's the best way to test it? How should we burn those cycles? If we're developing new materials, what is the best part of the design space to actually spend your cycles on? I think many of us, in hindsight, if we look back at our compute systems and where those cycles went, we would say, oh, wow, well, actually, a lot of those cycles didn't really need to happen, and we could have done some more useful stuff. So getting AI support for that, I think, is a huge next thing.
Excellent, great. I want to check to see if there are certain questions that you would like to pose to the panel. If you're loud, you can just say it, or there's a mic here. I can run the mic. Go ahead.
Yeah, I guess I would say there's a lot of sort of application-specific things there. I mean, certainly things like the cars, right, that have a certain real-time component, right, things that really need to happen in real time are going to have to run in the trunk there. Whereas anything that we have enough time to get off the car, we're gonna get off the car because it's so much more efficient that way. But I think that story will be it'll be a different story for every application, I would say.
So I'll bring up a specific example that I've seen at Duke where we're trying to build machine learning based algorithms for predicting sepsis. So for those of you who aren't familiar with sepsis, about I think it's 1.5 million people a year in the United States die of sepsis complications. It's a big number. I didn't recognize it was so big. And the national algorithm for detecting sepsis is remarkably inefficient. So brought together a number of computer scientists, statisticians, and they came up with some pretty interesting algorithms for detecting sepsis that really seemed to work. But it was a long ways, and it was very interesting how much verification, validation, and infrastructure to do that validation and verification was required for the healthcare organization to build trust that, okay, we can now really start to use the output of this. So as a specific example, it retrains once a month because retraining is an expensive process, as already discussed. And we run now 5 versions of that training model in parallel, and we're always using the middle one. So, and we run through, and again, this is where for sepsis it's a little bit different because it's a much smaller data set. But we run through basically every scenario and see, does it do at least as good a job as the previous version at predicting sepsis? But getting that in place and then having the whole organization trust that it was reproducible and it wasn't introducing new errors was really difficult. So again, I think that's going to be one of the really, both the exciting part of this and then the challenge is, how do we think about a framework for doing this reproducibly? Because again, we've done this now in one particular setting. I think we actually have a framework for doing that for other kinds of similar decision support. But I think one of the questions I'd love to hear us talk about is, well, is there going to be one framework for doing these kinds of verifications or validations, and is that the right frame? Does it require different kinds of validation and verification?
Just to comment, I mean, I think we're nearing the end of Moore's law, and so you no longer get free performance gain. So you're seeing GPUs, TPUs, neural network chips, and so on, and there'll be a whole variety. So I'm a little skeptical that there will be a generic thing, because the particle physicists are looking for the next upgrade of the Large Hadron Collider. They're going to get, order of magnitude more data, more particles in the intersection, and they're going to have to make decisions very quickly. So they're thinking of FPGAs, which they encode, and that's one solution. And then the experimentalists we talked about at the DOE labs, for example, they want real-time feedback on their experiments as they're collecting data. So there's a whole mix of stuff, and I don't know how generic it will be. It could be a sort of Wild West post-Moore's law field.
Just like we like it. And let me say just one last thing about so, we're comfortable with publishing source code. We do that all the time, and everyone has sort of GitHub, sort of thing. And we've become better as a community at publishing data and having DOIs, not as good as we probably should be in being able to do that. But with the way things are happening with machine learning, people will be taking the model and using that for a variety of scientific explorations and endeavors. And so that becomes the published piece that gets shared, because they can't bring all the training, they can't do all the training. And so the model for the car, whatever is running in that car, that becomes something that people will reuse. And so, we'll have to come up with a discipline as well on how we reference those, how we publish those, how we provide small updates to them, and then still have the basic platform and the basic model so that you can find your quark or whatever Tony's looking for.
Excellent. Let's take another question, I think, here, and then.
Yeah, I think I would just, some of this transition's happening already, but it's just it's not happening fast enough. I think in the universities and other places that do training is just that all of the algorithms, all of the methods that we're talking about today are increasingly becoming not a specialty, but are becoming a part of a core curriculum that everyone's going to have to study. And I think we're moving in that direction. Of course, one of the problems academia has is the brain drain of professors, and so that presents a challenge. But I think it's a good kind of challenge for the field to have. It's the volume, right? We're anyone at the universities can say that they field continuously emails and calls from people like, we want to hire your students. So like, well, what can we do to hire your students? And it's a little bit frustrating conversation because you just have to say, well, yes, you and everyone else wants them as well. So it's really it's just a volume thing to get more students with that skill.
But statistics and applied math is now hot again, right? And for a while in Web 2.0, it was about turning out code and web technologies, and the mathematicians didn't really find a niche there, right? But now, if you have a background in statistics and math, this is the best place to be in terms of understanding large data sets. Yeah.
Great, let's take. Oh, go ahead. Sorry.
Just to say something again that I've seen happening in academia, and I guess I'm happy that Duke's been involved in this. Is there's a movement toward how do we make sure that data science is embedded in everything, in all our trainees, the whole workforce across the organization, and of course that means different things to different people. We're not turning out, and everyone's not going to become a mathematician or a statistician. I'm in the Department of Biostatistics and Bioinformatics, but I am not a statistician. I'll never be one, and that's okay. I mean, but again, it's about building those teams and building that awareness of what does it take, in fact, to usefully bring those disciplines in, and I think that's part of the discussion. Even in industry, when they say, "Well, I want a machine learner, and I'll pay X amount for that machine learner when they graduate." Well, what do they really mean, and what are they really going to end up doing, and are we training those people the right way for that job? And I don't think we know the answer yet.
No, I agree. I think there's a variety of things. So for the technical community, applied maths, statistics, and computer science is right, but they do need to have access to big compute, which you have, but you also need big data. So one of the projects I funded, Microsoft Research, among others, was with Fei Li, ImageNet, which actually started a lot of this deep learning and really focused the computer vision community. So I think we need some data sets that actually you can train people on realistic scale problems. Just doing toy problems on your laptop is not sufficient. And so that's a challenge. And the other challenge relates to what Warren said. I mean, I've got lots of scientific users who are chemists, biologists, and they don't want to know the detailed guts of these algorithms, but they need to know enough that they won't make stupid mistakes in applying them. And that's another challenge, and I don't have answers to that either.
That's great. Okay, I think Sharon, and then back there.
I agree it's impossible, but I have to say I copped out because I'm deliberately choosing data sets where I don't have to worry about ethics. But that's a serious problem.
Yeah. Partnering at an academic level, the NSF has been very supportive of proposals that have social scientists and computer scientists, applied math together, and that has helped quite a bit. Then we actually have those conversations where we say, "What? Of course we should be able to do that," and there's a long conversation, right? But it also opens up new places, new research avenues. Yeah.
I know our colleague in the back in the checkered has a question. Do you have a question still? No. Okay, go ahead.
Yeah, I think the heterogeneity and really just managing a complex system that's evolving over time, I think these are big challenges. And sometimes people attribute the rise of sort of AI and big data and those kinds of things to causing those challenges. I would actually flip that around, and I would say that it's probably the solution to those challenges. And the reason I would argue that is that I mentioned that you can't make a self-driving car without learning. But what you could do is try to envision that software system that someone did make without AI, without big data. They typed in a lot of code, and somehow you got an army of engineers large enough to try to do that. You would have a problem with heterogeneity and with a changing system over time that was already so unmanageable that you wouldn't be able to build this system at all. So I think it's a valid problem, but I actually count the AI as the solution, not the cause of that problem.
Well, I think I heard a couple other things in your comment about heterogeneity. And one of them, and this is, if you will, the classic IT problem, and that's it, when you have multiple systems that are all interacting, they have different life cycles and different times. And so that means that different parts of those sets of interactions are maturing at different rates. And so one of the challenges, and I completely agree, is how do we mesh those things? And you know, I guess coming out of the agile software world where continuous deployment was the holy grail, that only gets us now just so far. And we realize, okay, well, now we need to have essentially the next phase of that. How do we not just think about the piece that we have control of, but how do we mesh with all the things that, in fact, we don't have control of, and how do we rely on them, and how do we build reliable and reproducible systems? So I think your heterogeneity comment is right on target. At least that's the way I was interpreting it.
Yeah, and let me just say two quick things on it. So most of you remember years ago, Intel bought a compiler company in order to run good code on their chips. And initially, people's response is like, well, why, you're not a software company, you make chips. But it makes total sense in that the first layer up, you have to generate really good code, and it's got to, and if your CPU is going to make it in the marketplace, you have to have good code, and it's important. What's happened in the machine learning space is that similar approach is happening, hasn't been purchases yet, but there's hardware, and then all of the companies are packaging up their basic machine learning code and making it run very well on that hardware. And the unit of heterogeneity, the unit of measure, what we get is then all of these different frameworks. And they've been customized and improved for that hardware, but none of them are standard. So back when the compiler example I gave, we actually had standard languages. In this space, we don't. So that problem of heterogeneity is made worse by having packages and frameworks that the only one company can really optimize for their hardware well, and then we're left in the shifting space. The second part of that is the end-to-end problem, and that is, Amazon gave an example, right? They have a solution for end-to-end, but I can't use that solution if I show up and I have a cool piece of hardware on my desk and it's made by NVIDIA and I want to connect it to this telescope over here, and it's part of their ecosystem. And so, so getting that heterogeneity such that in the open components such that I can take that framework like we do with scientific codes, do that same thing for anything from the instrument to the edge. As science, we have to push that. The vendor space is not going to be pushing that right now at this point. It's very important for us to be leading in that area.
Just one comment. Jim Gray was a magician with relational databases, so that was the technology he knew. But when he was communicating with scientists and trying to understand what their problems were, he asked them to specify what are the 20 questions you want from this data, and that was a helpful way to start the conversation. The other thing which relates to your heterogeneity and how we move on, Jim was very insistent that if you're going to work with real users and going to use something, you have to go to create a working system and then create another working system. You go from working system to working system rather than have everything fluctuating and not being consistent. For real users, you need to have some stability.
I think we can do one more question way in the back. Wait.
So Pete, in particular, you mentioned sort of it's an end-to-end problem. You talked about that there's other aspects. Several of you did. I kind of have two questions, but I'll state them both. You can choose to answer whichever one you want. So one is this fact that we've got a sensor, we've got an answer we need. Since the name of the panel has been about machine learning in there, nobody's really talked about where does the machine learning start and where does it end in that path? What's missing overall, right? Because it kind of implies that you start from the sensor and then machine learning looks at it and it comes out with that end answer. I'm not sure I quite believe that is the whole answer. So one would be talking about what's missing in that space. Actually, I'll stick with that.
That's a good one. Okay, so.
Bill, I'll just say one point. I agree with you. I think there are actually many opportunities in these, for example, experimental pipelines from your facilities to actually getting the data you want to find the answers from. Opportunities for doing machine learning in many of these places. Optimization, replacing humans, all the way along the pipeline. So I don't think it's just one point.
I think there's another side of what you're bringing up, and that's that data management through all this is critical. And again, that's something I guess I see really clearly in the biomedical space is that we don't do a good job of data management. And that's part of it is we often remove really important features of the data before it moves forward. And that makes it actually really hard to do the next step. So you're absolutely right. It's not just machine learning. There's all kinds of pieces that go along with being able to actually, I would say, use machine learning. And I'm listening to this and I'm thinking we almost don't have the right vocabulary yet to describe some of these problems. And I think we're struggling a little bit to come up with the right, we can call it a framework, we can call it an architecture, but it's actually what's the language we have for even describing some of these things. Or maybe it's just I don't have that language, and maybe it's because I'm sleep deprived, but I feel like I don't know how to describe some of these problems very well, but I can see the gaps.
And I agree, Deb. We don't want to move from generalizing from one place to compute to generalizing to two. We want n, right? So we like n, and so this idea of computing across this pipeline and going both directions, and it was asked earlier, is a bigger problem. It's the harder problem. A simplification of that is making n a small integer, but clearly, if you look at something as complex as ESNet and where data is generated and where it can be computed on, it's going to be a big tent, right? And also where that machine learning and where things are updated as well. Especially if you look at experimental data, often in physicists they make 3 or 4 tiers of different copies of data, right? So it goes to the first tier guys, and then goes to the second and the third. Well, what's going to happen in that same space with learning? Will each of them create their own learned set and go from tier to tier? And then how do you compare those learned sets? I agree. Now you're in trouble.
I agree.
Ability of the single leg table and
Thanks. Well, these are great thoughts, great discussion. I don't want to cut too much into your lunchtime, and we've very strategically chosen 11:30 because it's only 2 cash registers in our cafeteria up over there. So it's a great option of hot and cold food. I really look forward to hearing more when we come back at 12:30, and we'll have a session on software challenges.
Chetan Baru and I are running a session on software. And what we asked our panelists we gave them a set of questions to get them thinking, and this is a summary of some of the topics, those questions. One is sort of how do we form a more, what interesting models are there that form a tighter connection between the different modes of computation. Here I say simulation and data analytic based, but you can insert other modes too, that there's more of a loop going on rather than just a pipeline, a unidirectional pipeline. What are the opportunities there? What are the challenges of doing that? Another would be the big topic of developer productivity. In other words, how can we make it so that software development is not so painful, both in terms of platform independence, being able to express computation at higher levels and have more automated optimization and mapping onto different classes of machines or different platforms. Another, which is promises to be an interesting discussion, maybe over drinks this evening, is the sort of very divergent ideas about software and software stacks, open source versus not. How could we meld what have become a set of divergent software stacks if we're trying to now integrate all this software together into a single system? And then the general purpose of this workshop, which is to think ahead, it's NITRD. So what are the research topics? How can the federal government best be investing on these to make the sort of dreams that we all have become realities? So we'll start with a set of panel presentations by our panelists. We have a mix from industry and academia. One thing we'll do in this panel, because our time is a little bit more compressed than it was in the first panel, is we'll do all the presentations, and then we'll do the Q&A at the end, and so that we can sort of collectively have a discussion that crosses the whole group. And also, of course, a big part of the real discussion will take place tomorrow with the breakout sessions. So a lot of this should be sort of you all thinking about how will I participate in the breakout session? What kind of contributions do I want to make to those sessions? So we're doing it in the amazing idea of alphabetic ordering. And so our first speaker is Alex Aiken of Stanford.
So that's probably on. So yes, my name's Alex Aiken. I'm a faculty member at Stanford. I also have an appointment at SLAC and have been spending some time there, so I think I know a little bit about at least the DOE side of the government piece of this. And of course, I talk to a lot of my friends in industry all the time. A lot of my students have gone off and worked on various things that we're talking about, so some exposure to the industry aspects of it as well. And so I wanted to talk about, trying to address the charge to the panel. My particular take on it, I view this as really two different software worlds. On the one side, you have the HPC software world, where people have traditionally written in things like MPI and OpenMP. And on the other side, the big data world, I'm just going to use the term big data. I'm going to encompass machine learning in that, and I'll just drop machine learning. But whenever I say big data, it includes any kind of big data-driven thing like machine learning. And the various software stacks that have grown up there, mostly in industry. Some of that work has come out of academia as well, or at least started in academia. And I think, when you draw these pictures, it really helps, to think about, well, what is really the relationship between them today? So, are they really that separate? I mean, is there really, how big is that gap between them? And if there is a gap, what are the barriers to some kind of convergence between the two? So what would it take to meld these two stacks, or to get people, so what are the expectations and what differences? A third thing is, well, maybe there really isn't a gap. Maybe there already is some overlap, and then we can understand a little bit about where things are going by looking at what's in that intersection. And I'll have some thoughts on that. And finally, I think we ought to recognize that it's not a symmetric relationship. I mean, the investment going into the big data side of things, the machine learning side of things in industry, is a lot larger than the current investment in the HPC software stack. All right, so I'm going to take these more or less in order. So let's talk about what are the barriers to convergence. I mean, so why are they separate? Is that just historical, or are there actual technical reasons that these are different? And I would say that the communities have different priorities. Okay, so if I look at the HPC world, what do they care about? Okay, they care about performance, all right? And they care about cost, and they care about whether the software works. All right, now the good news is, in the big data world, they have almost the same concerns. In fact, they care about the same three things, but the order is different, all right? I would say that cost is the top driver, and by cost, I mean not just the cost of running the computation, but the cost of writing the software, the cost of maintaining the whole package. Okay, so everything that goes into getting a piece of software to work and sustaining it. All right, And then performance, yeah, performance is important, but not at the expense of 10 times the programmer effort or something like that. All right? And finally, correctness. Well, everybody says they care about correctness, but usually it's down there on the list a little bit. And I say this as somebody who's paid a lot of attention to software verification my whole career. All right? So, okay, now, so this is what I think the priorities are. If you were to go around and ask, this is what people would say that drives them. And what differences does that lead to? Well, I think it leads to significant differences in platform performance. All right, so if you look carefully at the performance of systems written in MPI and say systems written in Spark, okay, I mean there's at least 1 order of magnitude difference there, maybe 2 orders of magnitude difference depending on how you measure it. Now, you will see all kinds of point measurements of this in the literature, all right? And people will say one thing or another. And actually, talking about point measurements doesn't make much sense. You have to talk about some kind of a curve and what kind of scaling you're talking about. So what I really mean when I say the platform performance is off by that order, by that much, I mean when you have relatively fine-grained things, when you're maybe in some strong scaling regime where you're trying to manage relatively small amounts of computation and data movement on some very large machine, then the big data things just do not perform well at all, okay? And that is the regime a lot of the computational scientists are in. They want to run their computations on very large machines. They care about, getting a problem size out to a very large number of processors, and where there isn't very much for each processor to do in the limit. Okay, because you're spreading the computation so finely. And again, the big data systems are really far off the mark there. Programmer productivity, though, because of the priorities, it's the other way around. I mean, if you look at how easy it is, relatively easy it is to write, say, a deep learning model, okay, versus what you have to do to write even the simplest simulation in the current HPC stack, there's orders of magnitude difference there. And how do you measure productivity? Okay, this is something nobody's ever figured out how to do very well. Okay, but there's another measure you can use, which is size of programmer community, which is a good proxy for how hard it is to learn. Okay, if things are hard to learn, you will find a small specialized community that winds up being able to do it. And if they're much easier to learn, even small differences in usability will result in many, many more users. And you can see the huge disparity in the number of people who can get these systems on the big data side of things to do something, and the set of people who can get something to work on the HPC side. All right. So on the HPC side, you have very highly trained specialists. They're essentially performance programmers. They know a lot. Okay, even if their training is primarily in some science discipline, they had to learn this somehow in order to get it to and it was a big investment. That level of investment is a lot lower on the big data side to get things going. All right. Scale of computations. How big is big data? Okay. Some of it's really big, but some people throw this word around rather loosely. So I would say that most of the HPC computations that I see are actually of a scale significantly larger than most of what we call big data computations today. If you look at the sweet spot for machine learning, if you look at the sweet spot for a lot of those calculations, yeah, you're running on multiple GPUs, you're running on multiple nodes, but you're not running on tens of thousands of nodes. Okay, and that's where the HPC people, tend to want to be anyway. They don't always running at that scale, but that's always the aspiration, is to be out there. All right, and then finally, these things I think lead down to even differences in economic model. All right, so the fact that cost is the main thing you're optimizing for, on the commercial side, on the big data side, they actually pay for their computations in dollars. Okay. That sounds normal, but if you look at how people pay for their computations, say in the DOE, you're not paying in dollars, right? You're giving credits at the beginning of the year. You give a number of core hours. You apply in a grant, and you're actually highly incentivized to burn all that to the ground by the end of the year. You won't get that number next year, okay? And the whole system is actually set up to reward people who run bigger computations rather than smaller computations. You get better access if you ask for the whole machine than if you ask for only 10% of the machine. You are really pushed, the incentives, the economic models are just completely different. If people had to pay in dollars for time on the leadership class machines, I think it would change things very radically with what people actually do. Okay? And again, this is about the incentives. I mean, what has traditionally been incentivized in HPC is pushing the limits of computation, trying to get things out there to work at that scale, and the whole system is set up to encourage that. And that's a valuable thing, but that's more important than cost. Okay? And it just shows in how the whole system is structured. All right. Okay. Now, is there overlap today? How would you even understand this problem? So the way I think about it is, well, if there are users who could use either one, who are sitting in that overlap area, what would they do? Which one would they pick when they started a new project, say? Okay, that's one way of understanding this. And so you can think about who would switch from the big data stack to the HPC stack today. Okay, and I thought about this for 3 or 4 seconds, and I concluded that within rounding error, it's about 0%. Okay? And why is that? Because they don't have the skills to use the HPC stack. They couldn't sit down and write a program that worked and was anywhere near useful. All right? They're just not there. Okay? They're not those kinds of programmers. Now, who would switch from HPC to the big data stack? Well, we saw this morning some people are actually sort of doing that, right? They're incorporating machine learning into their computations, but they're not doing it by rewriting it in MPI. They're doing it by using the tools that are provided. Okay, so people will do it. If your performance actually went up by switching, everybody would switch. Okay, if it stayed about the same or was not overly harmed, some would switch, but there's a friction there. There's switching costs, so not everybody would bother. All right, and if performance is 10x worse, then nobody's going to switch. Okay, clearly. All right, so I think it's not clear. This is not slides, not saying a whole lot, but there's potential there for people to move. Okay, and why would they move? Well, let me give a brief digression on hardware. All right, so now I can actually say maybe the only technical things in my talk. They're not going to be that technical. All right, I believe that the hardware platform drives the software abstractions. If you look at the history of programming, every time we have a revolution in hardware, new programming models emerge. Okay, and in retrospect, those programming abstractions look great, but really they're driven by the underlying hardware. All right, so what is changing? Well, there is this slow motion revolution towards accelerators. Okay, so that's GPUs today. We heard some of this talks this morning mentioning other kinds of specialized hardware. These are all coming along. There's going to be a lot more specialization in the hardware. And why is that? Because down at the very fundamental level, Moore's law is ending, power budgets are capped. The only way to get more performance out of the hardware is to specialize. All right, so this is something that's inevitably going to happen. It's only going to increase from where it is today. All right, and this is already happening in the current generation of supercomputers. 95% of the flops are actually in the accelerators. Okay, so why I call this a slow motion revolution? Well, because the users are only coming along behind relatively slowly. Okay, if you look at the number of HPC projects that have actually switched to using GPUs, it's not that high a fraction. Okay, and why is that? Well, because it's expensive to switch, and I'll come back to that in a minute. The trade-off is that this greatly complicates programming, having to deal with these accelerators on top of everything else. You haven't taken anything away, you just added this extra level. But you have the potential to greatly increase your performance. And so I think this is the ground on which any convergence is going to happen, because this is something that basically the HPC people are going to have to deal with, and the big data people are going to have to deal with. And so there's opportunity there for people are going to be forced to make changes, and so that's where they're going to end up meeting. Okay, that's where the convergence will happen, if it happens. All right, here's an observation. So I said the HPC community values performance, and that's how people talk. But if you look at what they actually do, they only value it if it's not too expensive. So really, cost does come back into it. All right, like the fact that they haven't switched to GPUs is just because the software engineering cost is so gigantic. Of adding that in there and finding the people who can do that is a real limiter. All right. And that means that many HPC systems, even though they say they care about performance number one, they're actually far below their potential performance today. All right. Now, the big data community says they value productivity and that cost is king. But actually, when they go to run these things and they're incredibly slow, then you see people hacking, to try to make it faster, okay? And this is a real issue. I mean, it doesn't work for everything the way you would like, okay? And, the real problem, if you want to get, in my opinion, is in current and future data systems in current and future systems is data movement. So it's by far the most expensive part of any computation. It has been for a while. It's going to only get worse. We heard about edge computing today and the pipeline issues there, and that's basically a data movement issue. Okay, that you can't afford to move the data, far away from where you produce it. You need to do the computation nearby. And adding accelerators and all this extra specialization just makes the memory hierarchy, the memory system, much more complicated, increases the problems of data movement and the expense of data movement. And if you want to talk about, what the issue is from a programming point of view, I think that we have very few programming abstractions today for really dealing with the reality of the way machines are built. Okay, so you don't have, I'll finish in just a minute, not much support for locality, for partitioning data, and mapping, and how you, place the data in the compute in the machine. And so just for evidence for this, here are 3 examples. One's a high-performance computing example, one's a big data example, one's a machine learning example. These are things where if you improve the data placement and how you partition the data and break it up, you can get big changes in performance. And part of this is from switching to GPUs, but part of it comes from actually better abstractions. It's a little less in the case of the machine learning example there because they happen to already be on GPUs, but there's actually significant headroom there. And these numbers these potential improvements will only get higher as the accelerators pull away, and improve, okay, from the CPUs. All right, so just last thought. So I think people tend to think, there's this trade-off and that these, big data and HPC systems, these are kind of on some, at the optimal points on some trade-off curve between productivity and performance, but I actually think that there's, a lot of evidence that improved programming models could, move that line quite a bit, okay, and bring them closer together, ultimately. All right, that's all I had to say. Yeah.
We have Fabrizio Petrini from Intel.
Because you're going to talk. Okay, you could leave this slide. It would be perfect.
Oh,
for my own talk. It would be perfect. Actually, if you could leave for a second. The final slide. I mean, we didn't agree this ahead of time. Okay, just that. So the final, very, very last slide. Want to give him the mic? Yes.
Yeah, do you have?
It's right there.
Okay. Can you hear me? Okay, there you go. Okay, so the next talk, if you go, there is another one after this. Yes. Okay. So the talk can you hear me now? Yeah. Well. So the talk that you're going to hear now, and again, I have 10, 15 minutes. How long? 15 minutes. Okay. So it's just to see what we are trying to do to move HPC in that higher corner over there. Okay? Now I can switch to my own slides. Sorry, you have to do twice the amount of work. So in the meantime, I can introduce myself. My name is Fabrizio Petrini, and I work at the Intel Labs in California, in Santa Clara. I'm mostly involved in government projects. I'm going to talk a little bit about 2 projects that I'm involved in. One is DARPA Hive, and the other one is DARPA SDH. So, okay, very good. But before going into the details, let me clarify the point of view and what we are trying to do. So we define ourselves like the lunatic fringe of HPC computing. Okay, we are doing things that are a little bit out of the beaten track. We are exploring technologies, concepts that are not the ones that you will find in commercial computing anytime soon. We are doing mostly this under government projects. Okay, I'm going to talk a little bit about the 2 projects that I've been working on lately, which is DARPA Hive and SDH, and what we are trying to do with these programs. And again, this is just a personal point of view. Don't quote me for anything. I'm just having an informal. Usually there is the slide with the unreadable font. I avoided this because I think it's offensive. Okay? So this is all things that you can find on the web. You can try to Google. There is this big program which is called the ERI program under the MTO. I believe it's more than $1.5 billion. It's a bunch of programs. It's not just one. Within this umbrella, there are two projects that I'm working on. One is Hive and SDH. I'm a copy-I on both of these programs. Hive is a much bigger problem than SDH. So Hive is going for down select, and we have the deadline, as a matter of fact, at the end of this week. There are two teams competing for the down select, one in Intel and one is Qualcomm, and the winner will be announced in a month and a half. So I cannot say much about the program, but I can talk a little bit about the goals of the program, okay? And hopefully, if we get down selected, we'll be able to talk more in detail next year, early next year. Now, what is the problem that we are trying to solve with Hive? It's mostly a big data problem. We are trying to attack the fundamental limitation to scaling that we have right now on big data problem, large data sets, okay? And I think Alex had a very good comment because the hardware is designed and somehow influences the hardware, the software abstractions, okay? So we are trying to put hardware not just to get performance, but we are exploring novel concepts for addressing programmability issues that exist in these systems. So think about, we want to build an exascale system, or maybe an exabyte or a petabyte, whatever is the right term, system, but with the same ease of use that you would have on an x86 box today, okay? And the target for us is doing things in the hundreds of terabytes or petabytes. And we are trying to achieve these goals by using a lot of aggressive technologies. So we are talking about new memory technology that will be capable of working at peak performance with fine-grained accesses and random access granularity. We are looking about networks that have orders, and I emphasize the plural, orders of magnitude more bandwidth and usable bandwidth that you would see, for example, on an exascale system in the same time frame. Okay, and in order to do that, we are exploring very aggressive networking packaging technologies. We are also looking at new ways of building hardware. So for example, we're now on an HPC system. You have MPI, which is very successful because MPI has a very clear cost model. So whatever you do locally is okay, whatever you do remotely, cost plus infinity, don't do it. Okay, and that's, in my view, the success of MPI. So we are trying to remove all these boundaries in performance in a way to build a seamless system, for example, by having hardware that will transform in single-digit nanoseconds a memory request in a packet that goes directly into the network. So there is no software stack or anything else. So the system, from a programmer perspective, is going to look like an x86 system that you have today, with the only difference that you're working on petabytes of data. So this is the essence of this program. And in order to do that, we have a lot of innovation, not just performance, but in mechanisms for communication, for having a global shared memory rather than a distributed memory, and also to get performance. An exercise that comes with this project is we have also a very large team of people, about 40 people, that are working on a large body of applications that have been given to us by DARPA that represent various issues of DoD customers. And what we see is that we have people working on these problems. Sometimes there are not even parallel versions of these problems. They come with a Python script, okay? And we have these people coding this application in standard x86 and then doing the final step, moving to this system over here. And what we see is that thanks to this new design, we are able to address many of the limitations that are in existing systems so that the path to performance is very, very straightforward. So you take pretty much the software that you have now, and you have to tweak a few things. You are not bound by mapping and locality issues that you have in a conventional system, just because we are using a network which has very high connectivity. So the number of links on each node is very, very high. So you have a network where everything is just a couple of hops away. So the latency is very low. The bandwidth is very high. And again, this is not what you see in a conventional system. And this makes programming at scale much, much easier. Okay? And again, the idea is to solve these problems rather than in years, in minutes or less, just because the design is such that we are addressing these problems from the get-go, from the design perspective. Now, what are the impeding future development, blah, blah, blah? This is the question that was in the list of questions that we had to answer. Obviously, I didn't answer all of them because we don't have time, and also because I answered those questions that I think that I have something to say. So there are two things that we see happening. So the first thing is that we are going to build, in the next few years, a system that will look more flat in terms of resources. Okay? Right now, there are a lot of what I call rough edges that limit the way you can use these machines. For example, if every time you have to use an HPC machine, and going through the MPI route is usually very painful, and not everybody can afford that. We define this as the PhD route. So if you have a PhD working on this, then you can do it. But in general, this is not viable for a commercial computing environment. Okay, so this is something that we are trying to address. And one way of doing this is this novel concept of global shared memory. From a performance point of view, and this is a little bit of a stretch, it's not like this, but we are trying to build something which is much closer to a PRAM than an existing computer, okay? So you'll be able to access the whole address space, potentially petabytes, everything is, I don't know, not very far in terms of latency, and you have very high bandwidth that will allow you to move large data transfers, to make large data transfers with very little complexity in your code, okay? Other things that we have in this design is a new mechanism for mapping data, new mechanism for doing load balancing. Because when you enter into this type of problems, you have major load balancing issues. For example, if you work with social network graphs. So we have new methods that are in the hardware design that takes care of these things. So you can solve load balancing issues in logarithmic time for very complex data sets. And this is the part that is a big data. So the other part, which is a little bit of a smaller part that we see coming, and this is the SDH program. So you can Google that. The goal of the DARPA SDH program is to address fundamental issues in dense compute acceleration. Okay, so these two things are separate. So Hive is mostly a backplane that addresses scalability issues. And SDH, the goal of SDH is to build a coarse grain accelerator for AI and machine learning applications. So while Hive is pretty much on the arrival line, so we are coming up with the design next week, and we are waiting for the green light if this happens to build such a system. SDH instead is more on the ramping up phase, is more on the exploratory area. But what we see here is the use of spatial data flow computing. There are the usual players that you would expect. There is NVIDIA, there is us, there is Qualcomm, there are others. And there are a lot of universities involved with this in the architectural design. So this is the other aspect. So it's kind of complementary. So the first program is more addressing the scalability. The other program is addressing the dense compute part. And in particular, concept that will allow you to do dense compute, possibly with the orders of magnitude more power efficiency, and addressing the limitations of the Moore's law, and also doing specialization, which is something that you mentioned before, which is a way of getting more performance out of the systems. Software issues. I mean, what I was trying to say before is the software complexity in today's system is somehow a cause of the lack of truly scalable systems. So basically, we are in this situation just because the systems corner you to do things in a certain way, right? And this is the way that the whole thing evolved because it was driven by commercial drivers. So, but with this program, and obviously this is part of the intervention of the government, we are trying to break the mold and do something new which is very aggressive, which is very high risk. So we have very high risk of failure in this type of programs because we're using technology which is really, really advanced. But also high reward because from what we have seen, we can somehow bridge the HPC and the data world if successful, because we're going to keep the same level of complexity that you have right now on your laptop, okay? So if you can run it on a threaded machine, there you go, okay? So this thing, it's running on a petabyte of data, right? And we've already done it in various type of experiments. So we have seen, obviously it's not a scientific proof, 2 minutes. And, but what we've seen is that we have been able, we don't have the hardware, we have our own simulator. We know that we can take existing application and with literally minor changes, tweak them to get performance at scale. That said, there is always an advantage in developing what has been defined as communication avoidance algorithm. There is a lot of work at UC Berkeley on this area, for example, in other universities. Something that we are also involved is the development of new streaming algorithms. So, for example, something that we have seen is that we are moving more and more from forensic analysis to real-time analysis, and this requires new algorithms. This is also another area where there are many low-hanging fruits in the sense that, for example, we have our experiences. We have people working on certain algorithms, and they change the math behind these algorithms, and they have been able to get a major performance improvement just because nobody did that before. Okay, so this is an area which is ripe for new innovation, I believe. And let me see how much do I have. So, research agenda. This can be my last slide. The new frontier for the architectural design for what we see of the next few years. Obviously, you don't see that in the open domain yet. It's something that happens mostly inside the research centers of the companies and happens in some universities like the ones that I mentioned that are involved in this government program. But what is going to happen in the next few years is this battle working on the spatial computing concepts and specialized machine for getting energy efficiency and okay. And there is, so this is the same sound that I have on my wake-up call in the morning. So for me, it gives me, it has a subliminal message, right? So it's you could have chosen something else. It would have been much better. And then there is the something that has been addressed in the DoD space in this PGAS world is now becoming back because we are somehow providing the mechanisms in hardware that they are enabling this type of models. And I believe that that will lead to a reevaluation of a number of algorithms and solutions in that space. Okay? Thank you.
Next, we have Raghu Ramakrishnan from Microsoft Intelligence.
Okay. You have a question?
While we're doing the change, I was also told some of you have not officially registered and signed in. And so that's the desk up there. You don't have a
Okay. So my talk is basically going to pick up where Alex left off, and I agree with most of what he said. I'm going to approach it from a different perspective, though. So the bottom line is data is becoming ubiquitous, telemetry, sensing, and therefore collection of data is just exploding, right? And these numbers speak to this. If you look at the volume of data people are talking about, the unit is a zettabyte, okay? Exabytes, that's the unit of how you count data moving across the internet per day. And the key issue here, in my opinion, is going to become how to manage the data in a way where you can ensure responsible use. A simple example, if you look at GDPR, how many of you have heard of GDPR? So rules like this are now in effect beyond Europe, in Australia, in California, in Canada, right? Pretty much any large enterprise that has sensitive data has to comply. The cost of compliance is high. And that has the effect of making it more and more difficult to justify unique, bespoke technology silos that touch data. Okay? Second, the cloud. The bottom line is I'm blown away by the pace at which even sectors like finance have been moving to the cloud. I never thought it would be this fast. And what that has meant is many of the pieces of software we hoisted into the cloud by putting into VMs, we are now busily blowing up and rebuilding. Let me speak with humility. I'm a database guy, right? We've been doing parallel for a long time. All of that technology is obsolete, right? It pains me to say this. We screwed up, okay? So we're paying the price for it because if you look at MPP, tens of nodes, parallel database, that's so yesterday, okay? Alex said, jobs that run on 10,000 nodes, this happens in HPC. Well, I have production jobs running, single jobs running on 10,000 nodes. If something goes wrong, a pager goes off, right? Scale out, right? Daily, just the internal big data systems that we run, it's not even Azure. The daily I/O is about 1 exabyte, right? The cluster size is about 50,000 nodes. The smallest is probably 40,000 nodes. So these are large numbers. And in the cloud, the thing that is forcing us to rebuild software, the old stuff runs. But if you want to run in a way where you take advantage of this world, its cost efficiencies, its architectural possibilities, you have to recognize it's elastic. That means you can acquire and give up resources at will. That means your underlying management of state in your application has to be prepared to have parts of the computation just go away. The idea of hitting restart when one piece of your computation fails, that's gone with the wind. If that's the way you do it, well, look at the positive side. You have a great new research agenda in front of you. Okay? Everything, core databases, it hurts me to say this. If I look at transactional processing, whether it's Azure, SQL DB, Hyperscale, or whether it's Aurora, it doesn't matter. We are figuring out how to scale this. If you look at big data query processing, we're looking at how to scale this, right? And scaling does not simply mean partitioning. That's a prerequisite, true. Separating your raw data from the compute is a prerequisite, true. But fundamentally, your application state, the part that you cannot afford to lose for a database guy, that's quorum, okay? The write-ahead log. How do you deal with these coordination points in a world of scale-out and partitioning, in a world of memory hierarchies? This is hard, and I'm building up to something. These are things that take decades to get right. If you're doing all of this, as you are undoubtedly in the HPC world, well, the cost of shifting isn't going to get any less the longer you wait, okay? And the main point I want to leave you with is, it's not a matter of opinion, it's a matter of brutal economic fact. There is a certain train that's leaving the station that has left the station. The database guys, we were late, but we kind of hung on to the last car and we're trying to get on there and catch up. I would suggest that maybe that's what we should do for HPC as well. Okay, AI. I'm a data guy. All this AI stuff ultimately is about data, right? That's oversimplifying it. But truth is, data is a central part of what has sparked the deep learning revolution, machine learning in general. And that means, a very important point, you cannot think of the stack that Jim Couros drew as a process stack. It's a software stack. In practice, all the layers of that stack, feature generation, data cleaning, machine model cross-validation, eventually scoring. It's an interactive, iterative loop. And throughout that process, you need to manage your data. You need to secure access. You need to make sure that you can trace provenance of the things you learn, all the way from feature generation through to model building and scoring. These are hard things to get around, okay? So the question for HPC is, how do you align with all this? If you're building supercomputers standalone, yes, performance is awesome for certain kinds of workloads. But can you afford not to get on the bandwagon with respect to all of these other dimensions? I don't know. And when you look at the cloud increasingly, it's the edge. In fact, by far, the greater amount of data will be generated on the edge, right? A lot of the processing will happen on the edge, right? Where the edge is everything from moats to small stacks of computers, right? And so this is my money slide. There's a whole lot more, but this is my money slide. The reality of data is that it's becoming very diverse. And the one common thing is data use, security, provenance. These are becoming harder and harder to deal with, especially since the analytic trend is the old notion that you put everything in your SQL Server or Oracle database. It's no longer holding true. It's an ecosystem. People want to bring a diversity of tools to the table, whether it's Spark, whether it's HPC, whether it's machine learning. There's this backplane of data. And you're doing all these things with it. And no one individual or company controls any of it. By the way, open is a big, big thing here. Microsoft is now, quote unquote, an open company. Yes, we bought GitHub, right? But beyond that, we contributed 150,000 lines of Yarn code in the latest release of Yarn. We were the release masters, right? This is a place where, if you look at what's happening, unless you have a vision of how you're going to be able to work as a part of the larger ecosystem, you're going to have a tough time fitting in, right? If you look, I'm sorry, oops, yeah. And if you look at cloud and edge, I mean, I hesitated not to put a question mark or quotes here, but I figured, what the heck, I'll say it. I don't mean to say it's going to be performing on par with a modern supercomputer. No, that's not my intent. My point, though, is that's where the economics are. That's where the data increasingly is. And if you want to play, if you want to dance at this party, hey, there's an opportunity. How do you get your algorithms to work in a world of elastic, state separated from compute, containerized cloud? If you can get to all of those things I talked about, which are all technical mountains you need to climb, it's exciting, right? It's also a challenge. I don't really know how to do it, right? But that's the thing I wanted to put out there. Another, I'm really flabbergasted that there hasn't been more of a move towards open in this community, right? It would seem that it's well set for open. For whatever reason, historically, anyway, I would like to urge that you reconsider that. I'll stop with this slide. So this is, when you think about it, the old world of a database, a data warehouse was you brought all of your data from a variety of operational systems into one giant database and wrote SQL on it, and you made database people like me very, very happy. Okay? Now, that's not the case anymore. You bring your data into an underlying HDFS or cloud store. That essentially means your data can be sharded and stored in files that can hold enormous amounts of data and deliver them at high bandwidth to your computer, okay? Like I said, clusters of 50,000 nodes are what we operate on today. Clusters of several thousand nodes are common out there, okay, on-prem or in the cloud. On top of that abstraction of HDFS files, you have various other abstractions that are layered by the software involved. So graph processing software, Giraffe, stores graphs, right? Mongo stores key value documents. Virtually every relational database stores, of course, tables, right? So each of those has metadata. That's one layer above. And all of these different engines are being composed by applications that go end to end, right? And the pattern of bringing data in from those sensors on the edge through an event broker like a Kafka into the cloud, doing ELT streaming processing along the way, then doing big honking analytic workloads, this is common. And as part of that analytic workload, you have machine learning. And as others have pointed out, the underlying hardware is heterogeneous up the wazoo. FPGA arrays, GPU farms, regular old VMs of every stripe, and a typical job or a pipeline composes all of these. You rarely get something done end to end using just one piece of the puzzle in this world. Okay? That's standard operating procedure. So given all of this, there is a Lego-like pattern that's emerged, a RISC architecture, if you will, for the software. There's an underlying file system. There's scheduling algorithms. If you take Yarn and if you take the schedulers in HPC, there's a lot in common. But one of the things I'll point out, Yarn, we recently open sourced something called Yarn Federation. In part, it allows you to take many small clusters and from a jobs perspective, view it as a single job. But let me point to something else. Each subcluster could be very different. One could be a GPU cluster. One could be a regular old collection of VMs. Yet another could be tied to some specialized hardware, right? For, say, an SAP proprietary stack, right? And a single job could ask for a composition of these resources to get something done, right? How do you take advantage of these kinds of building blocks to build your specialized HPC simulation software, for example, while getting performance, which, while maybe not as good as a bespoke Cray, can be good enough and give to you some of the advantages of the other commodity pieces you'll be building on. As a database guy again, database machines, this is a lesson we learned a couple of decades ago, right? We got killed. Now maybe that picture changes with Moore's law kind of slowing and with all of these specialized hardware approaches taking off. Is there room for an HPC machine world, a database machine world again? Maybe. But I would argue that it's still going to be somewhere in this world of massively federated clouds because of the elasticity and the scale they bring to market, right? Thomas Watson, many years ago in the 50s, someone asked him, how many of these mainframes do you think you're going to sell? He said, oh, 5. Oh, wait a minute, maybe 6. And everyone laughed at him like crazy. Today, I think the public clouds are probably the 6 computers he was thinking about, and he's having a good old laugh at our expense. So, thank you.
Okay, finally, we have Fred Streitz from Livermore. Yeah.
Stairs are challenging. All right, is that right? All right. So it's good to follow Raghu because I come from a completely different world, and it's useful to see how all the rest of the world views computing. Because it's humbling to see the scale and scope of the enormous amount of data processing that is done out in the commercial world, which completely dwarfs what I'm going to talk about in number. I would argue perhaps not in importance, but in number certainly. So I work at one of the nation's security laboratories, and we come from this, here. We come at this from a very different viewpoint. We come unabashedly from the high-performance computing viewpoint. And so I'm going to take a little bit of a step back, and I know that this is obvious to those of you here because that's why you're here. But we lived in a world where working very closely with experimentalists, we built some exquisite simulation codes that delivered results that we could believe in, and that's a point I'm going to come back to several times because it's really important when you're making consequential decisions with something like a computer simulation that you actually believe the result. And that doesn't happen accidentally. Actually, you know, as Warren alluded to earlier, it's a team science, right? It requires a lot of experiment that's done to support model and model to support experiment. You know, at a place like Lawrence Livermore, those aren't separate camps. Those are always the same camp. We're trying to answer a problem, and you answer the problem by using both experiment and simulation. This has worked very well for decades now. But we have this opportunity now to use a different technique, and this the explosion of machine learning and artificial intelligence techniques on the market, which, you know, people ask me, well, why is it that's important now? And, you know, and it's not because Moore's law is ending. It's actually because Moore's law happened that we have that. Because really, I think that the enormous value now of machine learning in much of the worlds that I live in, certainly in science, in the science world, is because we have computers that are powerful enough that you no longer have to do toy models. I mean, you know, neural nets have been around, for a very long time, but they were computer science problems, right? Or they were this kind of stuff you would do on computing that was available at the time were toy models. You know, one layer, two layer, a couple layer. Now we can talk about, you know, deep neural nets that are hundreds of layers deep with hundreds of thousands or millions of parameters that are being optimized. That's a computing problem. That's a real computing problem, and we can only imagine doing that because we have computers now that can just do that. And of course, the flip side of that is all the data that's available. It takes an enormous amount of data to make these systems, neural systems, usable. And we also have access, as many people have said now, to just shocking quantities of data. So this becomes a very viable technique, and it really is a third element to how we view the world. And what I mean by that is, if you think about what you do in an experiment, ultimately, an experiment is the way that we query nature. It's the way we ask nature, what is it doing? And we get an answer back. And I was formerly, I was actually trained as an experimentalist, so I can say this. You know, you always get an answer back. It's not always the answer you wanted, and it's not often the answer that you thought you were getting for a number of reasons. But you know, you do an experiment, you measure the temperature, and you get a number back. Simulation is different. Simulation is how we query our models. We want to ask our models what they're doing, and you know, unless your code actually crashes, very much like an experiment, you run it, you get an answer. You know, it gets to the end, something happened, and then you have to figure out whether it actually did what you said it was going to do or not. And that go back and forth, as I mentioned before, but machine learning and artificial intelligence, and those are different, but data analytics, quite broadly, is how we query data. And interestingly, and it took me a while to really wrap my head around this as a scientist, that's independent of the other two. You query the data, and it has nothing to do necessarily with what nature did, nor does it have anything to do with your model. It's simply what the data is, and you get to query that. And that gives you a different portal into which you view the world. And these are three very different viewpoints, but taken together, you can explore systems that are much richer than we can explore just with equations. So, you know, as a physicist by training, I mean, I was, you know, trained to believe you can write an equation for almost everything. And it turns out that's really not true. There's lots of things you can't write equations for, but you still have data for. And that's really, in my mind, the power of machine learning in conjunction with these other techniques, is it allows you to build sophisticated and believable models that do things like decision-making and process control and things for which there are no equations. You know, medicine falls in that category. Okay. So we're doing a lot of this, you know, inside the laboratory, and I apologize, there's a slide that dropped here, so I'm going to talk through it and jump to the next one. So inside the laboratory, for instance, we're using this to help understand NIF, the National Ignition Facility, which many of you know we have at Lawrence Livermore. It's a 3 football field sized laser, which we do some inordinately expensive and complicated experiments. And we do simulations of those, and they don't always agree. In fact, you know, they don't always agree. Let's just leave it at that. So what we have recently started doing, to great effect actually, is to take the hundreds and hundreds of experiments that we have already done that are well cataloged, and the thousands of simulations that have been run that are well cataloged, and you actually do machine learning on both of those. And it turns out that if you combine those two, the simulations that by themselves were not entirely predictive can be made more predictive by using machine learning, which has been trained on what the experiment actually said. So you think of that, I mean, you know, anyone who has worked with a simulation that needs to match with an experiment, you usually leave some fudge factor. There's always some knob you can twiddle. Well, this is essentially a way of using machine learning to twiddle the knob for you. And it of course, doesn't tell you what the knob was, And we'll get back to that at the very end. I mean, that's one of the problems with machine learning. But it does tell you that there was a knob, and here's the better answer. And so you can take your simulation that was partially perfect, and with machine learning, actually make it substantially more predictive. That's very powerful. But that's inside the lab. I'm going to talk a little bit now about, and Warren alluded to this earlier, about a collaboration that we're in with the National Cancer Institute to sort of extend the scope of machine learning and and I'm going to talk through an example of how we're using machine learning with predictive simulation to try to access a problem that we couldn't actually otherwise do, and how we think that this is very powerful together. And it's going to talk about this investigating RAS protein. So this is back to a slide which Warren showed you earlier. I'm not going to talk through the biology. He's better suited to do that than I am. However, I will. He didn't go through the slide here, so I'm going to highlight 2 important points because that sort of is the jumping off point for the entire project. As he said, the RAS protein has an oncogenic mutation so the RAS protein is responsible for cell growth. That's what it does. It starts a signaling cascade from a membrane down to the nucleus that at the end says divide, and the cell grows. And usually that's a triggered phenomenon, and we can't go into, I won't go all the details, but the bottom line is it's supposed to happen once and very infrequently. But there's an oncogenic mutation that gets stuck in the on state. So once it gets triggered on, it just continues to signal grow, 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 grow. And those are these very fast-moving cancers for which there are no cure right now. It's not true that all pancreatic cancer is a death sentence. Turns out only about 93% of them are, and that's these cancers, the RAS cancers. There are other pancreatic cancers, and some of those are curable. This cancer, however, is not. We don't know how to stop it. So what do we know? And this is the important part. We don't know a lot of things, but we do know that it localizes to the plasma membrane. So here's the cell membrane. It lives on the membrane. It can be found out in the cytosol, but it doesn't actually do anything there, and that's actually really important. Scientists have been able to isolate it and put it in solution, but they can't make it do the next thing, which is bind to RAF, and that's the next thing we know, is the first step in the cascade is binding this RAF kinase. Okay, what's not known is why do you have to be on the membrane to make that happen? It's known that that's true, but we don't know why. So, as a physicist and a molecular dynamicist at heart, I said, that's, okay, protein on a membrane? I don't know about the rest of biology, but that I think we should be able to get a handle on. It just seems like a simulation we need to do. So, we're going to do a very large-scale simulation. Now, here's the problem, and Warren alluded to this also. The scale of biology is complicated. Because you have things like proteins and lipids, and those are happening at scales that I understand, atoms and molecules, nanometers and nanoseconds and things like that. But cells are much bigger than that. I mean, those are microns and fractions of a millimeter, and they operate on much longer time scales, milliseconds, fractions of a second. And that may seem like a short time, but to me, that's near eternity. So you have to come up with something different. And what we did, and this is more the supercomputing as opposed to the machine learning part, but we had to, wrong way. We had to incorporate 2-scale models to make this work. We needed to be able to work at a continuum scale to capture the scale at which biology is happening, but we actually want to understand what's happening at the protein level, so we need to be able to dive into molecular scale. So this is a true multi-scale modeling capability because we're going to be doing both at the same time. And what we're going to do here is we're going to use a machine learning algorithm to pick where we're going to go. So it guides the choice of our fine-scale simulations. And this was actually, everything I'm going to show you now was the initial set of science runs that were done on the Sierra computer, which is the little sister to Summit. It's also a very large computer, and it was actually dedicated just Friday to much fanfare. So what does that look like? This is a bunch of RAS proteins. Notice that the proteins here are represented just as little spheres because we're at a continuum scale, so there's no structure here. There is structure, however, in the lipid. So this is an 8-component lipid. I can go into details about that, but this is one particular component of the lipid, and what you're watching is the concentration of each lipid as a function of time while the RAS molecules diffuse on the surface and how they're affecting it. And that's one of the things we're trying to understand. And Warren was so bold as to actually show you some of the equations that go into this. It's a bunch of thermodynamics we have to parameterize in order to make this all work. Now, the thing is that we want to be able to dive in and look at particular pieces of that, but we can't afford to look at all the pieces, obviously. If we could do the whole thing at molecular resolution, we just would. But not even on Oak Ridge's computer could we do that. So that's simply beyond the pale. So well, here's where we introduce machine learning. We're going to look at every region of that space, and it's there are hundreds of parameters that are used that are involved in defining each little space. We're going to create a reduced order model of that because we can't deal with hundreds of parameters. So we're going to learn from a bunch of simulations a reduced order model of the space of all the lipids and all the RAS proteins sitting on top of it. Then we're going to map every region into that reduced order model, and we're going to see how they clump. And the bottom line is we're going to define interesting as people who are isolated in that reduced order space. So I know that's a little abstract, so I hope that makes sense to people. But the point is that a square like this, that's partial dark blue, partial light blue, and this one's about the same amount of partial dark blue and partial light blue. You imagine we get mapped to a very, very similar spot. In fact, two possible parameters, and this is not what we do, but just to help you visualize that, is you can imagine, playing it again. Imagine just a two-dimensional plot that's amount of blue on one axis and amount of yellow on the other one, let's say. And then you can imagine remapping everything here onto a spot that's measuring how much blue and how much yellow. Everyone's going to clump, and every once in a while you're going to have somebody that's way out. And we're going to use that distance, and Euclidean distance in this reduced order space as a measure of what's interesting. And we can now rank every square there by how interesting it is, and now we can take the top fraction of them. So that's what we do. We're going to pick an interesting region. In fact, we pick more than one, but we picked like the first like third of the list. But nevertheless, we pick an interesting region, and now we're going to take from that continuum model, we have to create a fine scale model. So we're going to, knowing what all the concentrations are, we're going to create lipid positions. We have to insert RAS proteins and run the system a little bit. And all this is done automatically, by the way. I'm not doing this. The computer is doing this. The computer knows how to start the simulation. And then it does that. So it generates the position. And now we're looking at specific full detailed simulations of the RAS proteins on the lipid membrane. That represents the detailed simulation of one patch out of the other simulation. Of course, we can't do this just once because you can imagine this is a one-to-many sort of mapping from concentration to actual lipids. So we actually do this about 100 times for each one of these. So in fact, at the end of the day, when we were running this across the entire machine, we're running tens of thousands of these fine-scale simulations, each of which is a very large simulation, by the way. It's using hundreds of nodes on the machine, but we have quite a few nodes on the machine. So running the entire machine, we were running both the large-scale simulation and tens of thousands of small-scale simulations all in concert talking to each other. So, and finally, the statistics we feed back, the information we get from that fine-scale model is fed back into the continuum model to continually improve the fidelity of the coarse-grained model so that they're always in thermodynamic consistency. So that's just an example of how you can imagine what I would call a workflow, and that's really the concept I want to leave you with, is this idea of this is, in my mind, the workflow of the future. This is doing high-performance computing, very high-level simulation across very large computers, but we're not using the computer to do a single calculation. We've actually broken the computer up in many, many different pieces, in fact, in ways that IBM hadn't quite, I think, anticipated that we were going to cut the computer up, and that was entertaining. I can talk about that over dinner. To use both the large-scale simulation, fine-scale simulation, machine learning, all going on at the same time with the machine learning directing the simulation. And this was the comment that was made earlier about using machine learning to help you make the decision of what the next best thing to do is. And the next thing we're trying to do is really take that to a meta level. So now imagine taking a step back and looking at the large-scale simulation with all the little simulations underneath it. That's only one. I could imagine wanting to do hundreds of those in order to address the problem I'm trying to address. And now I want to use machine learning to tell me what's the next best campaign to do, and then with those answers, what's the next best campaign to do. And that will also guide experiments as well. So that's where I think the future of computing is. Thank you.
You've all been sitting tight on your questions. So I'm Chetan Baru. I'm going to moderate the Q&A part of this panel. So let's see, we have all our speakers here. And I can just talk on this, right? Yeah. I have a long list of questions, no problem, to keep them busy till when? 1:50. I mean, yeah, 1:50, right? 15 minutes? However, I suspect, I know at least Barry had one question. So I suspect some of you have questions. So let's see. Does the audience already have any questions for our panelists? Yes, Rance. Oh, you have to be on the mic, otherwise I'm forced to repeat what you said, which won't be so good.
Yeah, this is Rance Cleveland from the National Science Foundation. So I was intrigued by discussions that some of you, or points that some of you made about hardware. And in particular, one of the things that's intrigued me about the development in accelerators, for instance, is that some of the accelerator developers are abandoning digital and doing their acceleration in analog. And I'm wondering what implications this will have for programming these systems.
Question to Intel, I don't know. It has to go green.
Okay. I'm probably not the best person to answer your question, but there are projects where they do, for example, these neural network implementations on chip. I'm sure you're familiar with some of these projects, right? They show promise of major performance improvements for specific applications, and they are along the lines of building specialized devices for special applications, right? Something that I can tell is that from a processor design point of view, we are developing technologies that allow to build chips that will glue together in a single node different type of technologies. So you can have in a single chip the classical conventional processor, and next to it there could be a neural network. And this is something that you can find on the web. It's called EMIB. I mean, what is available, it's called EMIB. And it's a way of gluing together different types of IPs in a single socket, for example. So the two things are not exclusive. But again, I'm not, I can point you to people that know better.
So not being a hardware person, I can take a quick stab at it based on my conversations with various hardware people. We pay a big price in energy for being digital. It's actually surprising how much energy goes into all the thresholding mechanisms to make sure that we get the right bit at the right time, in circuits. So going to analog is a way to potentially save quite a bit of power, and that's the name of the game in hardware. I think the issues are ones around robustness. I mean, so where are we going to, if we could live with unreliable hardware, the hardware companies could build, much lower power devices than they do today. But we don't have a software stack that really can deal with that. And so I think that's where, that's an interesting problem, and one there's not a lot of work on it right now, but potentially, something worth looking into for sure.
Okay. Any other from the panel? If not, let's see. Next question, and please do state where you're from. Hang on. Wait for the mic to get to you.
Okay. Barry Schneider from NIST. So, I mean, what I heard from Fabrizio was something, it's like the great dream, right? If it comes true. And there are, in some senses, contradictions between what you're talking about and what at least Alex and Raghu talked about. So I'm trying to understand, what is the economic cost going to be of what you're hoping to achieve?
Oh, I will answer with a joke, okay? So it's processors are like sausages. You shouldn't watch while they're being made. Okay, I mean, it's a Bismarck quote, it's not but with laws, right? So the idea is when you develop these new technologies, for example, in order to get to these targets of performance and programmability, you have to solve a series of hurdles in the design. The memory chip needs to be done in a different way, the network needs to be done in a different way, the Encore needs to be done yet in a different way. So what happens is that in this process, we are developing new technologies as soon as this technology become available, I can tell you, it's really nanoseconds. As soon as they smell that we have something working, this gets into products, into cell phones, into computers, is new design. So the project that we have may or may not be successful. But in this process, in this path, we are developing so much technology, so many ideas, that even if the project, for example, is still at the very beginning, we already have some major breakthroughs that are moving into production systems, okay? So you're not going to see Hive when you see some type of memory that is much smaller, much lower power, and much more energy efficient. It's part of this project. So the business model, in fact, if it wasn't for these government projects, these things wouldn't happen, right? Because the companies are more short-term. So they are accelerating a little bit, as I was defining before, crazy things.
Maybe I'll ask a quick follow-up to that. So, so some of the things that you're seeing in the DARPA-style project, when you say that there are offshoots of that which will appear in, say, production systems, is what you said. How do you think in terms of production systems as big HPC acquisitions or any other server versus what you're selling to the cloud? Do you make any distinction between what kinds of things you're developing that go into the clouds versus non-cloud?
It's becoming blurred. The distinction is becoming blurred.
Sorry?
It's becoming not well defined, okay? So before it was
blurred.
HPC or the cloud. Now there are people that from the HPC wants to go to cloud and vice versa. So for example, there are people that are considering Gordon Bell submissions on the cloud, just to give you an idea.
So actually, let's talk a little bit more about it, because as the session was going on today, I felt like maybe there aren't such people. I felt like there was a separation happening between the things that we were trying to ask, how does the big data and HPC merge? So what examples are you seeing where people are trying to do Gordon Bell kinds of runs in the cloud? Are you able to talk about anything?
I mean,
maybe not specific, but in general?
Not specifically, but there are people that are seriously considering of using some of this big cloud, because the reasoning is what we heard before, right? So basically, your machine has already exascale class machines in a sense, right? You have machines with 50,000 nodes or whatever.
Not machines, clusters.
Whatever is the right term, right? Yes. But they are very big.
The networking implications are profound, right?
Yeah, but if you find something that is not that is not very demanding in terms of computation, is more on the compute side, then maybe you can do it.
I think that's a broad statement. I'm not quite sure how far that's true. But what I see here is this. Networking, just like other kinds of hardware, it's getting progressively better and better and better. And with the kind of relatively cheap memories we are seeing, with the combinations of networking we are seeing, perhaps the distinction between two machines that are connected and a multi-core machine with two cores, maybe that is beginning to blur, right? At the end of the day, there's a hierarchy in distances as much as there is a corresponding hierarchy in memories. But if we don't think in a very fundamental way about how to partition our raw data, derived data, program state across both horizontally and vertically in this hierarchy, and if you don't design algorithms that fundamentally architect for partial failure and partial restart, then we don't take full advantage. This is essentially what it is.
Well,
so I would...
Yeah. Tony has a question. Sorry, was there another response?
No, I was just going to add a quick comment about, because I think Alex had it right, that Alex made the comment earlier that ultimately HPC simulators are lazy in the sense that they want performance, but as long as it's not too much work. But there needs to be a substantial benefit. So I think that accelerated computers are here to stay for the simple reason that the amount of work it takes to get programming onto them, which is not small, winds up being smaller than it was because of the interfaces between. For instance, you look at Summit and Sierra. The reason the jury's still out on those machines because they're brand new, but I think that they will wind up being very valuable machines in a way that earlier heterogeneous machines, like for instance Roadrunner, It was not, and one of the reasons is because of the ease of being able to use all the varying components. So they're simply much easier to access on this machine. Those interfaces are getting better and better, and so you can imagine putting more different types of accelerators. And once you've already gotten programmers used to breaking their models up so they're going to use the various accelerators, well, they'll use the other accelerators, whatever they have available, as long as the performance is there. And the performance is not discountable anymore, right? It's a huge amount of performance. So the effort will be taken.
Okay, we'll give one last question to Tony. We will have a breakout session tomorrow, so we can discuss a whole lot of this. So, Tony, if you can make your question quick and the answers even quicker.
Question very quick. Listening to Raghu, it didn't seem to me there was much of a scope for academic computer scientists playing in the world of zettabytes and 50,000 core clusters. And what role do you see for the academic community and, other than training people to work for industry?
So I would actually not agree with that, Tony. When I look back to my time in academia and contrast it with today, right, the absolute scale doesn't matter. The ratios of the volumes of data, what's available relative to the state of the art, to push the state of the art, that's what matters. And I would argue that today, academics have access to a wider, larger variety of data than ever before. In terms of resources, right? With the cloud, you have access to way more capacity than before for a wide range of research endeavors, right? In terms of software, with open source, right? We're running production systems based on Postgres, based on Hadoop, based on Spark, based on Livy, based on GitHub, up and down the scale. This is unprecedented. Yes, there are zettabytes. That's not the point, right? There are some areas where there is still a structural disadvantage. For example, if you're relying upon A/B testing based on millions of visitors coming to a website, sure, it's harder to do that. But that's where you build relationships through internships that then become partnerships. You're well aware of all this, right? So I would say this is a perfectly wonderful time for academia to jump all in.
All right, on that note, let's thank the panel.
Latest set of slides, because I gave Wendy a brand new set earlier today. Is this on? Yeah.
Do you know if it's? Do you want to?
Are you gonna? Do I?
Grab this laptop, which I rudely lifted.
We have to disentangle this.
Oh, okay, so you want me to change yours?
Yeah. I'm not going to use this one. The speakers will use it.
Okay.
Are you going to run the slides or I?
Everyone else is running them. Where is the slide? Oh, it's right here. Let me just switch out his presentation real quick.
Just grab it.
Okay. Yeah, just copy
Which
the
is the
desktop.
one move them forward? This one?
Yes, let me take them up.
Okay.
I'll move it to the workshop folder.
Okay. We're going to just go. We're going to go by the heel. Yeah. Yeah. Not yet. Okay, hi. Okay, so this panel is on hardware challenges and opportunities. I'm Barry Schneider from NIST. You heard that before. Here's the list of our panelists, and we're gonna keep the order of the speakers as it is on this slide. So Pete, you'll be first. Who's not paying attention? So it'll be Pete, Bill, Carl, Arjun, and Rangan. We had a number of telecons where we tried to frame some questions. I'm not going to read them all. You can read the slides for yourself. Please take a minute and look at it. We try to frame the discussion. I'll let the panelists, talk for themselves. But these are some of the issues that we discussed. And Bill Gropp also added a few things at a late date, which I hope I incorporated successfully. But let me just turn it over to the first speaker. So I'm going to turn it over to Bill. To Pete. You're second, Bill. Bill, don't fight. You're second. You don't have any slides, right? So you don't need anything.
Or I'll be in trouble. There we go. That'll work. Yeah? Okay. So there's a famous Austrian philosopher who said, let's start at the beginning. It's a very good place to start. So we're going to start down at quantum. I don't have any slides. I'm just going to talk a little bit about sort of what's happening in this machine learning space with hardware. So there's been a tremendous amount of excitement around quantum computing. I think we're far enough along that is it okay to be a quantum denier? Can I say that there is quantum happening? It's just not man-made. For machine learning, for big data, I think it's going to be quite a while before we see quantum being able to make a lot of advancements here. It's a wonderful place, and I'm excited about it, and I'm seeing some of the research. We have folks at Argonne working on it. But when it comes to very large data sets and the things that we're seeing in machine learning, I'm still trying to map out how that could work, especially as you imagine this picture that we drew earlier of learning on one side and inference on the other. And so on the learning side, it's about massive data, which means funneling, possibly exabytes or, larger into something to do learning, and then getting models that you want to ship and move out. So that's going to be a while in terms of this sort of convergence when it comes to machine learning. But there are other technologies that are sort of out there that are worth exploring. Neuromorphic is a very interesting space, but its primary advantage at this point is in its power, its low power. In terms of being able to compute something faster or in some other space, less price, some other density, it has some advantages, but really power is the main advantage. So we can imagine making progress in this space for inference, but it seems like maybe it's not the right solution yet, although we're still looking. And we have a neuromorphic, Intel's neuromorphic Loki at Argonne, and we've been exploring that and running stuff through there. But it's, again, it's a little bit far out there. Someone did mention analog chips. Mythic is one of these companies. There are a couple others that are driving memory chips essentially in an analog way, and looking at phase change memory and flash and other things, and saying, okay, well, these are really sort of, think of these as analog devices. We can get and do some computation even in the device. So I think the
interface on that will be, someone asked about the interface, will probably be very similar to what we see now. But again, its big benefit is going to be in density and power. And so there are some things that will change in our space, in our landscape, in that space. But primarily, most of our horsepower over the next few years in this space will come from GPUs, FPGAs. Fabrizio mentioned sort of coarser-grained data flow and specialized machine learning hardware. I went to Hot Chips this year, and it is just remarkable how many student projects can turn out a new chip. In one project in particular, between the end of their PhD and starting as an assistant professor at a university, the company had already been sold and made money, was sold, and he was starting as assistant professor. So this idea of very fluid, low-level chip design, there are, as you know, dozens of companies in this space now making new machine learning hardware, making new accelerators at for the market. And this is where hundreds of millions of dollars are being invested. So in the DOE, in NSF, we invest in computer science research. Right now, we cannot compete with the VC investments in chip design and low-level machine learning hardware because the drivers there are so large. We have so many wonderful startups working in that space. So what happens to us, right? Where do we end up? Well, we end up with a sort of a super bloom, a springtime, there's lots of chips that will be out in the next year and a half or two. Argonne already has its sights. I can't tell you which ones we're working on buying, but we have our sights on a couple already. And it will then usher in this phase, that same thing that happened in parallel computing, where we had a period of time where we had many diverse architectures, distributed shared memory, interesting vectors, other things, and then it sort of sorted out. So right now, that's the beginning of where we are today, is we have some long shots, neuromorphic, quantum, analog devices that can help with machine learning. We have the near term, which are these mostly CMOS-based devices that are GPUs, FPGAs, specialized arrangements for machine learning hardware, low precision, small matrix flops, these sorts of things. And now we have this big middle section that we need to conquer with respect to the infrastructure. And it was already asked several times today about that and heterogeneity. And I think that is one of the huge challenges for us. And let me wrap up and say that a couple things. One is that it's often the case when we want, in computer science, when we want to go and explore something really hard and big, that we'll hear, well, which application is driving that? And it's a good question. But I would also flip this around and say, okay, so which application drove the development of Python? And which application drove the development of TensorFlow? Right? Or CUDA? Right? So there are a number of things that in the middleware section, whether it's new languages or new frameworks or new data transfer methods, that is really fundamental computer science that we will need programs and effort into that will use these new low-level components that we're getting. And that fundamental computer science won't be tied directly to an astrophysics simulation. It will be an effort to build the abstractions, to build the models and the tool chains that can solve several application domains simultaneously. And that's, again, it's a hard thing to sell to program managers, but given where we are with where hardware is coming up and we have machine learning, every one of the talks, whether it's molecular dynamics or astronomy, merging those and finding that common infrastructure is, for big data, is a huge challenge for us. One last thing is I'll talk about the flexibility of our systems. So in the HPC space, we have been tremendously successful by fielding incredibly large machines by narrowing choice. We just make it hard. So we make it hard to use by simplifying and narrowing what you can do on the supercomputer. So it means, okay, here's the kind of job we expect you to run. It's going to be MPI, it's going to be launched with this launcher, it's going to use these libraries. If you show up and say, okay, that's great, I have a Docker container, and I wanted to run it across your entire machine. Well, there are centers that are now doing that, right? But that's something that has been against our philosophy for many years, this idea that the software has to be extremely flexible, overly flexible, that it has to allow every combination. And about 6 months or more ago, I was at a meeting, a DOE meeting, where at one of the discussions, someone suggested to do continuous integration with their supercomputer. Now that sounds like a fantastic idea. This is where, automatically when I check something into GitHub at the right time, a job gets spawned, it gets run on the supercomputer, it gets run with various size data sets. Those data sets then determine if the modification I've made is a good one and it's actually both performant and gives the right answer, and it comes back and it might even send me or my boss an email that says, Pete's code worked. The resistance to even something simple like that for continuous integration was amazing, because it pushes these buttons of automatically launching programs, of containers, of open websites where code gets run and pulled down. And so the community, the HPC community, to really address high-performance computing and this machine learning and edge and big data, we'll have to change our notion of what flexibility is. And we'll have to allow people to bring their own OS, bring their own software, bring their own components, and run flexibly, linking together 3 or 4 different pieces in their software. And then we'll see this sort of growth that we expect. And my time is up. All right. And there's no questions till the end? Is that how it's working? All right. Thanks.
Thank you. Sounds good. You might hear a little bit different story than Pete just gave you from me. So I'll make it good for a good panel. Okay, so I'm from NCSA and operate Blue Waters. So I first want to tell you some of the places I'm going to show you a little bit of data about what goes on Blue Waters. And you can read about that in these books, and that's where they're coming from. So not anything about Blue Waters except it's a universal research instrument. The flexibility is the thing that makes it such a universal instrument. And our definition of what we do is to make science teams productive. That doesn't mean that we have ever told a science team, don't run your workload or your job or your code on Blue Waters. We figure out how to make that work on Blue Waters, and I'll show you some of those results. And it's universal in a sense. If you look at the workload of who uses it, you see almost all types of science and research disciplines. You also see most of the algorithmic methodologies that you might find. These are Phil's dwarfs, and there's only one little area, unstructured grids, that we haven't found examples. This is going back into our workload study that we published in the end of 2016 there. But basically a pretty diverse set of algorithms and methods, and the little arrows are meant to point to things that might be associated also with AI, deep learning, big data. So some progress. We've been in service now for about 5 years. The first year we were in service,
you only had traditional modeling and simulation going on the system. They were pre-chosen, co-designed projects that actually were identified in 2009. So they did some data simulation, however, they were all traditional modeling and simulation. In 2017, in the report I just referenced, you see that 34% of our science teams identify as being data intensive, which was the term we asked them to use for data analysis or things like that. But actually, 8% identified as using machine learning methodologies. And many of our big projects are doing all their processing on Blue Waters rather than breaking it up. So these were ones that we identified, oops, I should point up there, as things that we could speed up the production to the insight, even if their parallel part of their workload was highly efficient, their other parts were not, so we brought them together. This year, in the report that we're going to release in a couple weeks, 48% of our teams identify as data intensive, 11% as machine learning, and that's our term. You could use AI in those as well. And almost all these projects are combining techniques with also modeling and simulation. We have more things that are combining than just say I'm an AI project or a big data project. So that's been the progress of the ability to have a flexible machine with a flexible operating environment in the software stack that allows to bring, say, we support containers, we support different workload schedulers, we support Python, we support all those things that you might find in the more AI-oriented type development environments. So, a little exercise. Spend 30 seconds, and this is about 9 or 10 application teams, different fields of science, how big their files are in total, how many files they have, average file size. Just write down or annotate which ones you think are data analytical, AI type things, and which ones are more traditional machine learning. I'll give you a hint, they're about half and half. So can you tell just by looking at these characteristics of their data, which ones are which? So here they are. So my point is, from the way the teams are using the system, from their data, you really can't tell which methodologies they're using one versus the other. And that may be the same, I'm sure it's the same if you look at kind of the profiling of what goes on a node, an application base. Some of these are data analytics. You know, this is a thing from CERN, but a lot of these here, we can't tell a priori just by looking at the characteristics which ones are which. That's why the flexibility of systems to be able to have fewer bottlenecks is important. Here's another example. The question is it possible to design deeper and more accurate neural nets with larger training sets and also reduce time to training? So this is one that's been published. It has to do with the LIGO experiment and finding gravitational waves. And you see two curves here. This ran on Blue Waters of scaling the number of GPUs. But this is not individual jobs. This is one single use, and it's exchanging data across those nodes. So it's a traditional way. It's using MPI along with machine learning methodologies in terms of the individual tasks. But this is a mix of AI-type applications with scaled MPI-type, the technologies that would go into scaling, modeling things, and that's their efficiency at the moment, but it's the first time it was ever done. So I think that we need as we look at trends, I think that we're doing ourselves a disservice to say, oh, I have an HPC machine, and I have an AI machine, or I have a big data machine. I use this term, high-performance computing and data analysis. Somebody else could use something else. But the idea is that, and my final message is going to be, the architecture is not really the deterministic thing about convergence. We already have convergence. I showed you the data about how many activities and science teams are using converged methods. And my point is, we've already converged based on the hardware, we all can get better and hardware can get better, but it's the methodology, the approach, the software that is going to make the difference to make it easier and easier to have these converged workloads. So the hardware requirements are pretty much overlapping between the three types of things we're talking about today, and providing a productive overall environment that is flexible and balanced is an important characteristic, and being able to reduce that time to solution regardless of whether it's a big simulation or a ton of data or a ton of jobs or high throughput computing. As I said, almost all of our projects have a combination of all those things together. So I pose a definition of what a supercomputing is, HPCDA machine or whatever. It's a system that can bring to bear all the resources of that system to a single application when needed. That won't be always, but it occurs reasonably often. The majority of the use will be smaller scale, down to single nodes. A system that is very efficient at being computationally intensive and parallel, both for traditional modeling, but also for the expansion of AI in machine learning. A system where the I/O, storage, and networking are never the bottlenecks. I mean the internal networking as well as the external networking. That is well balanced. So they should never be bottlenecks across the whole system or have one weakness that says, no, I cannot effectively run my task here. And the system doesn't have to be the cheapest in each one of those cases that we're talking about. It needs to support the range of science that we have, because all the ranges of science have large problems, be they in the AI space or in the simulation space. So it doesn't have to be the cheapest for each type. It has to be the most cost-effective for the sum of all those types that you're supporting, that your mission requires. So before I go on, I'll say there's, in my view, much more challenge in the software environment than in the hardware environment in terms of going forward. But this is the hardware panel, so I'll just keep myself to hardware. Everybody always wants more, so we always want faster. We always want better. We want more bandwidth. We want more bytes. That's going to go on. And even though Moore's Law is not going forward at the rate it was before, we're still searching for more in every aspect. I don't care what type of discipline or method you're using. Higher operations per second for general purpose processors benefits all the segments, but specialized processors are benefiting some of the segments. The challenge of how many types of things can move to accelerators and we've even tried a number that don't move well without a tremendous amount of effort, but some do. Improved capabilities of mixed precision. We have some modeling simulation, large-scale codes that are using mixed precision or reduced precision, and that's perfectly fine. They validated that that works. And they have to benefit the time to solution for the teams, but all those are characteristics of that we'll see in the next generation systems. Higher memory bandwidth, again, benefits all areas. That's just not memory bandwidth, but also the latency to memory, how long it takes to get your operations into your processor, things like that, are increasingly important for all these segments, so there's not much difference there. And better shared subsystems. So where we see most of our contention in the systems like Blue Waters is in the shared resources, be that the interconnect or the file system, the shared storage. And that's where we are finding opportunities to improve, but also B, they're not the low-hanging fruit opportunities to improve like you would find in some per node-based things. So faster, smarter metadata operations in a much different way. Better traffic management on the interconnects. So for example, on Blue Waters, it does a very good job of avoiding or helping with congestion across applications, and we use topology-aware scheduling for the messaging, and that's basically made everybody have their own dedicated share of the system without contention across that. But on the I/O side, none of that applies to messaging for I/O, as you want to send one piece of data to the storage system. That's still produces congestion in the interconnect. And resilience and recovery to decrease disruption. Right now, in a number of cases, when things start to go into recovery mode, there's a 75% chance that a second error will be generated before it finishes because recovery mode was never optimized. And that will impact mostly the ability for applications to complete successfully. So, some of you know me, I'm not going to leave without making a comment about cost and cost performance. So I don't think any architectural discussion is able to be completed without some sensitivity to talking about the cost of the choices being made. And that's an equally important component to deploying or ownership or whatever cost you have. A flop per watt is not the only cost, so you can't just say that that's my cost of ownership. When we deployed Blue Waters, general purpose node and an accelerated node were about the same price. Today, you can probably get 6 or more general purpose nodes for every one accelerated node. Now, you have more accelerators in them. I agree, you may have 2 or 4, whatever that ratio is. But just the cost of the accelerators themselves have risen quite dramatically. So we can't say, this is better, I get better speed up over here with my accelerators, my GPUs, without also saying what it's going to cost me to get that speed up. Memory is the same way. We want memory bandwidth, latency. You look at the 2 factors in memory cost, at least now. One is HBM is more costly than people projected, so therefore systems cost more. And the other is that to get an adequate amount of memory bandwidth, you have to go to the biggest size DIMMs in most cases, and you're basically over provisioning capacity to get the bandwidth the same as you do in your disk storage systems to get the bandwidth. And that's because the manufacturers are not making the smallest size DIMMs. So these things are adding to the cost of the system without necessarily being recognized in the architectural solutions. So finally, to answer the questions, for the first one, my answer is it's already happened. It's happened across many areas, and we should just acknowledge that it's happened, and now how do we make it better and more ubiquitous? One size fits all. I would first say one size fits all is not the right description because it kind of implies lowest common denominator. But yes, there are already many proofs of existence that well-balanced system architectures can be used very effectively on AI, big data, traditional modeling simulation, and they can do all those at the same time in a very efficient manner, but what matters is flexibility in the architecture and time to insight. How much convergence is actually possible? I think all of it. Now, I'm not talking about the edge computing Pete talked about when in the first session. I'm talking about when things need a fair amount of resource in a certain place. But rather to talk about all these different things separately, I would look to see if we can't combine the requirements of these fields and say, okay, what are the requirements for the systems and what types of support can systems give in these requirements term rather than just a buzzword term. Homogeneity, yes, we will have much more of that. We have to deal with it. We can't hide this from the science teams necessarily the way we had before, where things were much more automated. So somehow we have to figure out how to fund science teams to have a more sustainable method of moving into the heterogeneous environment because in the academic space, there's a little bit of a cultural difference in the academic space. Most people don't, I would say the vast majority of people doing the code development are either graduate students or academics who are doing their science. And the only way that they'll migrate to something new is if they can get provably more science out of that or an advantage over their peers. So the time scales, the methodology, motivation may be different than being directed, okay, go move to this. And finally, how to make machine learning and AI fit the simulation for productivity. I believe it's already happening and it's accelerating. If you can't take the difference between when we started and this year and next year, we'll have a higher percentage. I believe software features make this easier for new developers on laptops. We have to get some of that software environment into the supercomputers, like containers that are already there, like Python that's already there, TensorFlow, that at least many places are now supporting. But I think also we have to go back and see what the development environments are for the machine learning AI environments and see how we can make it an easier step forward. And also, that one example is not the only one, but what people have been happy with on single nodes or on laptop computing or whatever, no matter how many GPUs they have in there. Eventually, I believe that they're going to get to the point where they have to start scaling out as well as scaling up. And we have to be able to accommodate that in order to keep them being able to solve the larger problems that they want to. So with that, thank you very much. I have no idea if I was on time or not. So.
Okay. Am I live? So, no, that's good. Yeah, that's good. So my name is Carl Schultz. I'm from the University of Texas. And I was just going to, I'll probably be short so we can spend more time in the panel. But I just wanted to highlight kind of one motivating discussion point that came up in some of our calls with Barry. That sort of has to do with, at least what I thought was an interesting observation about sort of the difference in terms of development point of view to access new hardware from if you're a traditional person who's developing, HPC applications solving PDEs, for example, compared to AI machine learning type of application environment. So just to kind of highlight that, I thought I'd start with thinking about the traditional computational science application folks. And I have to admit, I come from that background, so I know that space fairly well and have sort of transitioned to doing stuff in AI. But, it's been mentioned a couple of times, and I think Pete did a nice job when talking about when we build supercomputers, we have been doing it for a long time, and we sort of have a notion of what they should look like and what types of applications that they support in advance, right? We kind of provide up front, for the most part, a command line environment, all roads leading through a resource manager, focusing on distributed memory programming with MPI, supporting a number of different threading libraries for accelerators, asking our code teams to use CUDA. That's sort of the type of environment that we provide. And the one thing that also I think is interesting is to think about the fact that the folks who are writing some of the big multi-physics codes, like we heard an examples from Livermore, they put a tremendous amount of manpower years into developing those codes, maintaining them, validating them, and verifying them, which is very important it's important in AI as well, but really important when we're trying to make predictions about computational science programs. And they put a huge amount of effort. And so one thing as a result is when a new machine comes up and it has some new snazzy bit of hardware, it takes some time to actually be able to get that code running on that hardware. And as was mentioned before, there's sort of this trade-off as to, well, am I going to jump in and update it fast enough to take advantage of the hardware? Am I going to kind of wait to see, is this hardware really going to take off? And people sort of treat this as really just a priority trade-off, basically, just a cost of how much time they're going to put into it. But because of this, their codes have a much longer lifespan. 20 years is certainly not out of the norm. And they have gone through many generations of supercomputing systems already, and they have seen quite a shift in hardware. And they have all been burned by it, myself and many people in this room included. So one of the things that we try to do to accommodate this, of course, is we do get some economy of scale through optimization of tools. So, every new system that comes out has some sort of optimized numerical library. We optimize MPI, we optimize BLAS, I/O, et cetera. We try to do the best we can, and we try to leverage a lot of common infrastructure. But compared to the machine learning domain, I would say that, we're speaking in broad terms here, that every application is still much more like a unique, beautiful little flower. They all have their own little warts. They have a science team associated with them. They're written in different compiled languages, and they need to be tuned onto a new system. So, the point here is that because of this investment in the code itself, the source code, they have some experience in what to do to get onto a new system. And when we think about, how do we have sort of a convergence of supporting AI on the kinds of HPC systems that we've been building for a while, one of the humps that I think we have to get over is how to get the software ecosystem optimized on this hardware. And the high-level takeaway here is that in the traditional computational science area, they've kind of been beaten down into doing this. They may not want to, but they're willing to do it. And I think this is different than the AI folks who really kind of just want to go about their business of getting their data on the system, doing some training, and getting some results. So we'll contrast that with the next slide here, is contrasting with machine learning and AI, which I think Pete commented this morning that there are a number of frameworks that are used, but I would actually argue that compared to what we do in traditional physics-based simulation, it is much, much smaller number of software stacks. In fact, this I'm going to argue is an encouraging thing, that they really rely much more on shared common software ecosystem. They have a lot of the same needs. That's why we're here. We're talking about the need for high bandwidth memory, GPUs, trying to leverage burst buffers, needing more memory and I/O capability. There's a lot of similar types of requirements to actually move to larger and larger systems, but they really want to use a common set of software. And I think compared to investing in the source code, what I tend to think of on the AI side is that people are really more invested in data, right? And in some people, some cases, the company owning the data, that's where the real IP is. But in other cases, when you say, oh, I do machine learning, a lot of what that means in terms of your bag of tricks is that you know how to do data preparation. We haven't really talked a lot about that. That's not necessarily a big HPC item, but we shouldn't discount the fact that 80 to 90% of the work in machine learning is data cleanup, that you have experience with algorithm selection, that you have experience with training and cross-validation, right? When people are getting degrees and going out and getting hired by the Ubers of the world, this is probably more of the questions they're asking. They're not asking them, hey, have you coded CUDA? What's your familiarity with multi-core, CPUs? What threading libraries have you used? It's more about the software ecosystem and what's your favorite gradient boosted tree implementation, stuff like that. So I kind of see this as perhaps an opportunity when thinking about convergence, in the sense that, as these new machines are stood up, and if we, from the HPC side of things, really take a coordinated effort to support machine learning in a more optimized fashion, we can focus on a relatively small number of software ecosystems and actually get them on-ramped faster. Because if TensorFlow and the scikits and all the other small number of things work out of the box, for the most part, people are happy. They don't care. They don't even know necessarily what the back-end hardware is. So I see that as a positive opportunity. And it was mentioned, of course, earlier, that they're not necessarily going to know MPI, and that's been my experience. And I did hear that MPI was hard. I learned that today. Although I have to say, I find buying a Christmas gift for my wife much harder than doing MPI, but I guess I may not be the norm in that case. But anyway, there are expectations, and the point here is it's all relative. And when we think about certainly the machine learning side of things, there are experts who are certainly going to be fine running the command line, running TensorFlow, but there's another swath of the community that they have different expectations, and command line is not it for them. And so I think developing in addition to just optimizing the software, developing an environment that more matches to what they're used to on their laptop, like Jupyter notebooks and the like, that can go a long way into sort of helping have both types of workloads running on the same system. And the other final thing just to mention is, if we have all the software running great, that's good. If we can sort of make the user environment be a little bit more akin to what they're used to, that's good. But we also can't shortchange the data exchange issues. And I realized I misspelled exchange. But I'm doing machine learning these days with my role with the medical school, which is relatively new at UT. And, we could have the greatest supercomputer in the world, but if I can't get HIPAA data on it, it's irrelevant to me, right? So, being able to support the kinds of data sets that are important for an open science community is good. And also, as mentioned earlier today, the workflow. it's not necessarily the case very often that all I'm going to do is just do big training on a big HPC system, right? If I'm really doing something in production, if I'm going to tie it to edge computing like Pete was talking about, that implies that there's other things upstream and downstream of the supercomputer that are done to really facilitate this. You know, and in certain cases, to be honest, in the HPC world, we don't normally like to support those kinds of things. So we have to be a little bit more proactive. And with that, I will just end. There was an XKCD slide this morning. I felt that we needed another one. This is the token machine learning slide talking about taking your data and throwing some linear algebra and having something awesome coming out. And the only point, you know, I was trying to argue here is that, you know, if we can also add these new hardware technologies, if we can do that in the context that people are familiar with in terms of running their machine learning workloads, then it can be just as good as shuffling the bits around here. So with that, I will stop. Thank you, and we'll move on.
Yeah.
So just hang on to it. Hello, my name is Arjun Shankar. I run the data group, the Advanced Data and Workflow group at the OLCF, the Oak Ridge Leadership Computing Facility. And we are where a lot of the action is happening right now. We are getting Summit rolled out, and many references and mentions of Summit. It is has the highest numbers, LINPACK numbers today in the world. The June list puts Summit and Sierra right on top there. And this topic, since I run the data group at one of our leading HPC facilities, this topic is very near to my heart. So I'm glad we are discussing this at great length, and obviously there's more to come. So I am not going to spend too much time talking about Summit. There's been a lot of press there, and you can read a lot about it on our website. All I'll say is when Raghu said the cloud plus the edge is the new supercomputer, I think Fred and I did a double take. We thought Summit and Sierra are the new supercomputers, so don't do this to us. You know? But as many of you, I won't talk a lot about our allocation programs and how we offer it up. But as you know, we are part of DOE's flagship program to provide computing resources for discovery science. And ORNL, as an Office of Science laboratory, is all about providing this for research, for efforts, proposals that are up to the mark world over. So it's not just limited to the U.S. The expectation for free use of the resources that you publish and share your results. So some of these are just a few examples of flagship applications that we put out there to sort of support our case that it is the smartest supercomputer, and of course that's the buzz on a computer being able to do HPC as well as analytics and AI, and that's where we get a smart supercomputer from. The applications, there are many. These are just some that line up well with some of our biggest challenges of our time, combating cancer, predicting fusion energy, looking into high energy physics data, thinking about the next generation of materials. But there are several others, and some of them make it to this list, but that there are several large campaigns and large-scale simulation and analysis runs that already have pretensions to being AI and analytics and big data, and here's sort of a sampling of them. So I'll just what I'm going to try and do is to sort of project going forward from what we've known about Titan, and which was the fastest U.S. supercomputer until Summit and Sierra in the June top 500 list. And Titan's been around for quite a while, and is still operating and still on the list at right up there, getting long in the tooth, of course, and we plan to run it through into 2019. But the comparison and the evolution of the Titan capabilities to Summit gives us some clues about the future, and that's the case I'm going to make and try to look ahead. So you'll notice. So here are some of the statistics. A few key things to notice are the reduction in the number of nodes by a factor of 4, but each node now is a much fatter node and has an increase by a factor of about 40, which essentially suggests the sort of 10x increase from one generation of these leadership class supercomputers to the next. There's something you'll observe is that there's a sort of factor order of magnitude increase in the memory per node, and there are new hardware characteristics like non-volatile memory in the node. And overall, when you combine the additional DDR, HBM, and NVMe, we're looking at about 10 petabytes across the Summit system. Just for your information, since we're on an architecture panel here, the system interconnect is a fat tree architecture, and it's a non-blocking fat tree. Tremendous increases in bisection bandwidth, but what's really nice to note here is the relatively modest increase in power consumption, and that's of course a big deal. There's a tremendous amount of dollars go into the infrastructure. So what I thought I'd do is just sort of open up the box a little further and look into the design of a high-level design of the Titan node and compare it with Summit. And we're going to try and sort of project out and try to look for trends and see where things work well and what we might see in the future. But essentially, you can see that there was just one GPU at the time, and even at that time, the idea to move to the GPU was the sort of extraordinary increase in computing compared to Jaguar, with a modest increase in power. So the story of GPUs that started then in prior to 2013 when we were planning and designing it was obviously without deep learning in mind. It was to observe that it had all these similarities to this high velocity vectorized like math that we could do for our science applications. We weren't thinking analytics at the time. But the power envelope only increased a little bit. So the bet on GPUs as a heterogeneous aid was not, of course, the first. Roadrunner and Lanel had some heterogeneous computing before us. But that betting at that scale for 18,000 nodes was, of course, a shot in the arm for NVIDIA at the time, and helped along this whole industry in many ways, we'd like to think. And many of the leading supercomputing centers around the world are moving to using these heterogeneous coprocessors and accelerators for their science at better energy envelopes. So that bet by the Department of Energy has really gotten support over time. So fast forward or come to the present right now, we have the Summit architecture here, which, so at the highest level, you have 6 of these GPUs. There are 2 IBM P9 processors, 22 cores each, with a significant increase in the DRAM, sort of factor of 8 or so, you'll see, compared to the one AMD Opteron here. And a tremendous increase in the, in the high bandwidth memory per GPU. What we found in Titan over the years was that the applications performed best and had the best speed up experience when they kept a lot of their memory within their GPU, the DDR there. And so we emphasized that we had a fair bit of high bandwidth HBM associated with the GPU. Also, with the NVLink technology, you have sort of a greater opportunity for GPUs to work across other GPUs on the same node and essentially move towards almost a kind of a coherence across what memory they can see. I'm clicking the wrong thing here. IBM has introduced some technology where the GPU can also, in a somewhat coherent way, access the DDR RAM on the node as well. That's connected to the CPU. So from a sheer cycle standpoint, the order of magnitude increase comes from the sort of 7x speed up from the current Volta GPUs to the Keplers of Titan, and the increase in memory very directly and tremendous. This CPU, of course, we are at Moore's law boundaries, but have 22 cores here as opposed to 16 cores in the Opteron. So I'm just sort of trying to put down these data points here for you to look at to see from a broader trend perspective, we are seeing a greater enrichment, if you will, of the memory hierarchy close to the compute cores. This is a little in contrast with the idea of moving computing to data, which makes a lot of sense when you're collecting data from observational sources and you want to move computing to the edge. This sort of suggests that when you need computing at the acme, at the leadership edge, you do want to strengthen and enrich the data hierarchy. The network interconnects have sort of grown, but again, not at the same sort of commensurate rate that we did increase the memory footprint. What's an interesting architectural feature of this node, and am I coming to my 12-minute mark? Okay, so this may, I'll just finish with one slide after this. What's interesting about this has been the node local storage, the SSD storage. And this has been a surprisingly beneficial outcome for applications that that need to go through the data sets and pipeline the data from the center-wide file system to read and reread the whole data for every epoch of the deep learning training phase. So pulling the data close and iterating over it in a systematic way has been a great boon to the deep learning community. It was an unexpected surprise in many ways for us. So we've just, I'll just say that we've found that these Summit nodes are for all those memory and processor improvements and the interconnect improvements and the connectivity improvements within the node have given us the 10x scale up. But we find that that connection between the CPUs and the GPUs are helping the traditional analytics codes. The principal component analysis, which is sort of memory dependent, benefits from the increased amount of memory. Support vector machines are slightly more complicated. They require the CPU and memory interchange. They don't see as many speed ups because you have to go between the CPU and the memory. K nearest neighbors are heavily communication dependent. They benefit from the communication networks at a relatively steady rate. So we have found that this particular fat node architecture is interestingly helping a class of simulation applications as well as analytics applications. It goes a little bit to what I think Bill said, that convergence is already happening. So finally, last slide. I think if we project forward, we agree that heterogeneity in different forms is in our future. Whether it is these data flow concepts or GPU accelerator that are close to these nodes, especially for HPC. The deep learning sort of wave is going to continue to support the growth of these GPU class accelerators, as well as FPGAs and so on. But ultimately, these two communities, I think, will converge when we shine a closer light on the direction of the data at different stages of the hierarchy, as well as at different points in the process of discovery, whether it's a simulation write or a data analytics read. We can address more of that by sort of filling this data hierarchy. A gap for us, I think, is the interleaving of traditional HPC and data analytics in sort of tight succession. We see these as being treated as different phases of discovery, and how these applications will interleave better and work at the same time. We find there aren't as many as those applications today. And this is not particularly a new concept, but it's something that's we really need for this convergence, I think. And finally, the way the compute elements in the network mesh with where data is stored is going to really dictate how quickly this convergence happens. Thank you.
Control level, yeah. All right. Loud, clear? Okay, good. So I'm Rangan Sukumar, and I'm an AI researcher by training. Learned all the HPC that I could while I was at Oak Ridge National Laboratory. And right now I'm in the CTO's office at Cray, trying to figure out and plan how we're going to implement convergence of HPC and big data at Cray supercomputers. So what I'm going to do today is stay true to my training and bring the bias of a data scientist towards what HPC means to us and so forth. And so when we had these discussions around what is this panel about and so forth, and it was about hardware and so forth, we said, what is the goal of convergence? What do we want to do at the end of the day when we say we've achieved convergence? We kind of put together a bunch of constraints and try to optimize that in the role that I'm in, trying to figure out what is the hardware that I build that does the following. We want to be able to maximize the performance per dollar. That means when paying $1, I want to be able to pack as much flops as I can. When you think about the big data world, and I think Alex brought it up, several other people brought it up, it's about the dollar to insight. I want to get performance at the best value I can. At the same time, I think Bill brought up in the previous talk, where operating costs matter. Power per node matters. Power for the system matters. Downtime matters. Human resources matter that support the operating costs and so forth. I also want to make sure I don't get too weird with my architecture, because if I get too creative about my architecture, then I have to bring up the community up to speed to be able to program that weird architecture, which means that inversely proportional relationship has to be constrained by a budget. And then it's about, we've fallen into this trap of tuning systems towards benchmarks. So we want to try and minimize that benchmark performance. It has to be maximized, I think, but we want it to be at a particular scale factor. So what I mean by that is you want a system that's 50x better than your previous system. So you're trying to do that goal. The last one is even more interesting because you have hundreds of users, and out of the hundreds of users, you're trying to figure out how do I build a system where my app-to-app performance variation is also minimized, right? And it's particularly less than a value that you can accept and live with. So what I'm going to project in the next few slides and argue for and against is that the real success of convergence is about integrating flexibility with heterogeneity. And I'm going to talk about some of the early experiences doing it. So every slide that at least talk of convergence should have the slide from Jack Dongora's paper in 2015. The point I want to make here is that it's not just about hardware at the lowest level. It's about all these other dimensions before you actually achieve performance. It's about thinking about how do you launch jobs that are HPC versus big data? What is your access policy? And I think somebody mentioned about, how do you launch an on-demand job on a machine that's primarily meant for people that can run 20% of the machine kind of scale jobs. When you think about programming models, completely different. Languages and tools, preferred options versus what's available free for you to download and start using. Everything matters, right? And so if today you were to do this exercise by yourself and you think about how am I going to build a machine, given what I know, given the roadmap of all my hardware vendors and the architecture designs that is possible with those hardware, if you were in the data science world, you would say, I want the fattest node possible. I don't care about precision. I want lots of RAM. And I would love to have as much ASICs that do specific things for me, both for training and the inferencing of those machines. I would love to have persistent storage that talks across nodes. And I would like to make sure that all these ASICs are optimizable during runtime, which means I compile code in a convenient environment like a laptop. That compiled code automatically runs on this big machine when I get to do that. On the HPC side of things, you're looking for high precision. You're looking for vector extensions like the good old days. You'd love to have as many GPUs and CPUs as possible with high bandwidth memory. You want to integrate I/O over the memory hierarchy, and you're OK with static code optimization. So given this trend, right, so when you try to compare what the requirements were, so I ended up talking both to the HPC customers and the commercial customers at Cray, and I kind of see there is the dichotomy between the two worlds. And there is opportunity for convergence, and I'll eventually get to it. So you think about the purpose of why we need two ecosystems in the first place. The primary use case for scientific computing is about solving equations versus you're searching the data or searching for nature or searching for the experimental result that you want to find and so forth. You start thinking about what are the different ways in which you program it. You have to somehow find a balance between what you know with parallelism versus what you know about distributed computing. The expectation is that you'd be able to strong scale, which is you add more processors, you get better performance, versus it's about feasibility over here. Just give me a scale-out solution that will actually work. Versus if you go all the way down, you're starting to look through my access model. What is the design strength of one versus the other and so forth. And then as you keep going down, you also start seeing the kind of patterns that you're trying to look for when you're running workloads and so forth. In the next slide, I'm going to talk about one more level of detail where if you're trying to run a workload that's HPC versus you're trying to run a workload that's typical of what happens on the cloud, you want to think about that as enterprise computing. Everything changes, right? So the way you think about data as vectors, matrices, and tensors gives you an expectation on concurrency of how you access an element A of ijk versus at any given time, you're looking for a small set of parameters that can be there in memory. It's get lost. You can get it back anytime you want. Versus when you're doing a computation, you always want the data to be there for you. When you have workloads in academic situations where every model you train has to go through this order n squared process of cross-validation. In the enterprise world, I think Raghu brought it up, it's good enough if it's A/B tested. It's good enough if my model works for the two use cases that I'm interested in, and I want to just move based on behaviors. The ETL word. So when you think about ETL in the enterprise community world, you're starting to think about, have this big file. I'm going to take all these small pieces of the big file, which is probably a single row, process that single row, convert it to some other format, and use some tool to discover. Whereas the scientific world, you're thinking about computations that take an entire data set, that maps to one point in a different space, and for every point, you're going through the entire data set that you have over here. So it's like saying, I'm interested in computing an n by n through an n by n space, and that takes a lot more compute than you would with the file transformations and so forth. When you're searching, with the traditional world, you have query languages that do summaries and aggregates, versus when you're searching in the scientific world, you're looking for properties, you're looking for periodicity, you're looking for self-similarity, you're looking for anomalies and so forth. And the last one I often joke by saying, scientists typically don't have a big data problem. They have a small budget problem. And it's curiosity-driven. And so it kind of gives you a different flavor of how you approach workloads. So getting into the big gorilla in the room, AI, right? So when you think about AI itself, where science and enterprise is differing is that the models that are being trained and published by hyperscalers is being used a lot. The assumption is that transfer learning is going to work, and therefore, if I'm able to have a model that's pre-trained and just have new data, I can run a bunch of things. Or I can just start using services that's made available to me via the cloud. Versus in the science domain, we see a lot more time is spent on formulating the problem than actually training and running the problem. And the baseline that makes sure that the model is actually working is, with enterprise world, you have to beat a human. That's kind of your baseline. You beat somebody at chess, you beat somebody at Go, you beat somebody in a game that was played several years ago. Versus in the scientific world, you're trying to beat theory that's 300 years old or 400 years old and so forth. That's a much bigger challenge than you would want to take on. The figure of merit is about interpretability and feasibility. The previous panel talked about it. And in terms of enterprise computing, it's all about time to accuracy. Can I train the biggest, best model in the time I need to make money? And the other pattern I'm starting to observe is that I hear this I/O issues starting with in the scientific enterprise world, and then there's I/O issues in the commercial enterprise world. And they're slightly different, and this is how. So if you think about the use cases like ImageNet and so forth, you have kilobytes of small sample data, millions of them, and then you have about 10,000 categories that those samples are labeled across. Versus in the scientific world, you have gigabytes of data, you've got thousands of samples, and a few categories, but a much bigger problem because now your feature space is just exploding combinatorially and searching small categories in these huge spaces of data. So you need to figure out what kind of patterns can you search, what motives do you need to be able to search those, and so forth. And so what I'm going to walk through the next few slides is what have we been doing at Cray to address this convergence, right? So for people that might know, in 2012, Eureka GX was announced, which was basically saying, if I take HPC hardware, take the interconnect, take the high-performance processors, put them into a cluster, and then run the open source analytics that's offered on the cloud, what happens? And I think there was somebody that mentioned what happened. It was 2 to 3x better than commodity hardware. So that was not good enough for people to adopt and run with. And then the AI buzz hit in. So the NVIDIA's P100s came in, the NVLinks came in, and so forth. So we had to understand what the differences are between having those kinds of specific networking technologies versus going with commodity and so forth. And then what happened was our experience with the software stack that we learned in the big data space. We were able to now offer that to scale on the supercomputers. So Eureka XC was a product that basically took the software stack that we put on the GX back on an XC. So which means now you were able to run what was running in about 64 nodes over here to about how many ever you can afford to run it on. And now that we know how to do that, all our clusters will also have Eureka CS, which is basically the same software stack that runs across the board. So what did we learn? So I want to first give you the optimistic view of things. So the opportunity of taking what HPC gives to what the cloud computing already offers is huge. So far, most of the efforts, I would say, has been in taking what cloud offers and trying to put it on HPC hardware with 2 to 3x, but then there's a lot more things you can do by going the opposite direction. So first problem of interest, graphs. I think somebody mentioned 1 trillion triples in the morning. We ran 1 trillion triple data sets better than Oracle and AnswerGraph did. We did it an order of magnitude faster on a Cray and one of the XC machines using the Cray graph engine. So it handles 1,000 times bigger data sets at 100 times better speed up, even on semantic queries, as well as graph theoretic queries like PageRank and betweenness and whatnot and so forth. With matrix methods, these are results both from Oak Ridge and NERSC, where by replacing what Spark does with an MPI layer, you're able to do anywhere between 2 to 26x better, depending on the type of data and the type of algorithm. With deep learning, we were very proud, and this is going to segue into my next slide, very proud that we were the first ones to run deep learning on 2,000 plus GPUs at CSCS, and we were able to achieve 95% scalability efficiency. And this is where all the optimism I have about convergence of big data and HPC kind of blurs, because this is what happens in the AI world. So 2 years ago, ImageNet took about 352 GPUs and 2 days to train with a 90% scalability efficiency on an open commodity style cluster. And as you look at different companies, some of them are hardware, some of them are pure software optimizers. So what happened was Facebook themselves figured out a large batch algorithmic technique that went from 2 days to 1 hour. Power AI, and this is similar to the experiment that Arjun was mentioning, is it took 50 minutes to do it on 256 GPUs using Power DDL. And as you keep going, specialized hardware, TensorFlow, and then specialized software that happened. And then eventually, what happened was the cloud is able to run the exact same workload in 18 minutes in 128 GPUs. And what's worse is it costs only $40 now. This entire thing happened in a year and a half, right? And so the good and the bad news is, as long as you keep your computers hungry and satisfied by filling in as much I/O as possible, feeding in as much data as possible, you're good. But then the bad news is that just putting in more data is not going to help you any further, because in another experiment that Baidu did, for every model that they trained, they always found that beyond a particular size, that model was not good enough. So which way is it going to go is still a market risk, and we're not seeing enough scale-first thinking that will take us forward. So with that, I'm just going to give you a glimpse of what's coming. So we're thinking about how do we build systems that are generic in nature, that are flexible and heterogeneous, that don't give you a vendor lock-in, and you're able to grow in multiple dimensions as you're doing it. And so if you think about missing pieces as to what all happens, the conclusive takeaway is convergence is not all about hardware. And we did this exercise of figuring out if we started with hardware, and we actually tried implementing a few workflows, and you had the memory hierarchy this way, and you saw that cut across, and we figured out what were the major tools that are production ready today that are more white spaces than what's available to fill those boxes. So until we fill all these boxes, I don't think convergence can be very productive going forward. So with that, I wanted to conclude my talk saying the future system is going to have general purpose like flexibility, which is saying it'll look like commodity from an architecture perspective, but it'll have custom processors. The way you manage, the way you do the interaction with it, it's just going to be very, very seamless compared to what cloud does and so forth. You're going to have high-performance interconnects, but you won't know that you're having them. You won't have the trouble of having to program them. It's going to be a unified software stack that understands both worlds, and it'll be offering them as microservices. And so the ultimate buzzword, again, is that how would you design systems now, given that you have workflows that you have to optimize and not just codes towards that goal? So with that, I'll conclude it, and thank you for listening.
So to be provocative, do we really need one system, or do we need two systems? Would we serve the communities better with specialized HPC and specialized data hardware?
I'll go. So I think I'm trying to show some examples about where the same science teams are using both methods or all three methods at the same time to meet their science goals that become more complicated. And what we've seen traditionally, and maybe the places that said, oh, I only want to run one type of application on my supercomputer, those teams spend an awful lot of time moving their data someplace else to run in a different mode, a different algorithm, sometimes on the order of months. So by converging and having the ability to do different types of methodologies on the same system saves months of research time before they get their insight. In fact, we've had cases where it cuts the length of time to their insight by a factor of 6 or 10. And that's because we converge their workflows of all different types, their methodologies onto the same system, so they're not moving petabytes of data that take months to do. So at least from that point of view, I think it makes a lot of sense. If you only have one type of thing you're doing completely differently, like trying to operate driverless cars, maybe you don't have to. But in the case of a lot of the science that we see, the integrated methods and the benefits, productivity benefits of not having to move data from specialized system to specialized system has a tremendous amount of motivation.
Just one other point is, I think it would be a fantastic graph a couple years from now to be able to understand how many cycles are used, sort of machine learning versus what classical. If you look at Bill's chart, right, and how many, we have only had these tools available over the last several years. Now, of course, a applied mathematicians and statistics will tell us we've been always doing it. But you know, so it's been pretty disruptive and quite a rapid change to adopt these methods. So 5 years from now, will we see, you know, 80% of the apps spending large fractions of their time doing some sort of estimation? Or I mean, it's for me, I'm still astounded at where it crops up, even in classical molecular dynamics, which, you know, I just think, well, how in the world can that work? But there's a guy at UChicago doing this very successfully. It's remarkable.
So, Kirsten, do you feel we are forcing the issue? Because it seems a little, it's sort of inevitable almost. You know, like in our systems, we see the different kinds of workloads being done. If you think that big data is only for the cloud, I think you will hear an argument from Raghu that HPC is being done in the cloud. So there's a certain convergence that's happening somewhat broadly. Now, if we think of big data being located in different places and defined as sort of spread and distributed and collected from different places, then we have to ask ourselves whether what we're doing on it is HPC. And so then you're right, it won't, those two things are separate.
So I would
okay.
Yeah. Go ahead. Now, I was going to just give a response. If you want to think about the timeline and you're thinking from an investment perspective, I would say the journey of being able to adopt HPC from the AI world has a lot more to mature, right? And so I would wait a year and a half to see what settles down before I say there's one system that's going to do it all. So it's not happened yet. I think it needs that kind of time.
Well, from NIST. Thank you for many insight from the HPC. And my question to you is, we talk about the MPI, OpenMP, and so on, and those are old technology and so on. Question to you is, like, with your new scientists into your centers, do people really adopting like big data, AI? Just want to see the trend that you see in your center to see if people kind of like getting away from the the MPI and OpenMP instead of like getting kind of adopting the big data paradigm, you know, the stack and so on into the high performance computing.
So I'll start, and I'm going to sort of be a proxy for Dan behind you, representing Supercomputing Center at the University of Texas. I think one of the things, I suspect other centers are the same way, that you see is that kind of along the first question is because supercomputing centers are having to support the traditional workloads, but also big data workloads and AI workloads, that sort of there's been a natural requirement that those supercomputing center staffs are having to hire people who have those kinds of backgrounds as well. One, so that they know how to architect the software and help design the hardware when they're standing up systems, but two, to be able to support those people and get them up and running. And it's very important, as you know, to be able to speak the language with the people who are using your system. And so I think in the last few years, we've definitely seen, sort of this growth in having AI expertise on your HPC staff.
Okay. We probably only have time for a couple of more questions. Yeah. You want to use this? Here. Be my guest.
Hi, Henry Kautz from National Science Foundation. So we've seen in the last few years that there's been a lot of work where you can take a deep neural net trained on a big system and then approximate it, simplify it, go to ultra-low precision arithmetic and run it on an Arduino and then deploy it massively. And I just was wondering, is that kind of work making any impact in the high-performance computing world in terms of thinking about maybe looking at other kinds of hardware that could you do some of that training also with ultra-simplified hardware stacks?
I'll kind of take that question, right? So I would say, as the first question about has HPC made the impact, the answer is yes, right? And I would say that because every processor company that's coming out with a new inferencing chip uses some technology, some method, some algorithm that was actually developed using HPC methods a long time ago, figuring out how do you do multiplies with two sub-precision numbers, right? And then how do you keep track of that? How do you reduce sparsity algebraic matrices, then put that into code? So if you think about how these inferencing chips are already working, they're already leveraging a lot of research that was put into the math, the algorithms, and the hardware itself. And in terms of what's happening in the processor world, I would say the world is going back to model parallelism, the ones that HPC is really, really used to. Right? So you're going to have a lot of small chips that are packed into the die and so forth. And so you're going to start seeing this emergence of, I'm doing data parallelism now where my model is replicated on every node and every GPU system I've got, but then my chips are going to be so efficient, even at low precision, but I have to split my model into multiple sections. Very classic HPC use case, a very classic HPC problem that we've been solving for several years. So it's coming back.
So Peter, you got one last question?
Hi, Peter Lister, NIH. So I guess it's clear over time that scientific computing, thinking of the previous talk where there was enterprise computing and scientific computing evolved from big iron over to big data. In terms of enterprise computing and industry, have they evolved the other way in some large sense? For example, can you get high performance switch computing available out of industry? Can you just dial it up in Amazon, AWS, and is there a market for it?
There is a market for that, and I think Amazon and Azure and others are marching down that path. A lot of what's sort of interesting about a lot of the way deep learning for AI purposes is used at large scale is for training. The expectation is that what comes out of it is a sort of predictive model or an inferencing model. And so companies that need to do that training, for instance, would want to use the resources available to them in the cloud when it's available. But I think it does come down to cost. I think I'm, take what Raghu's sort of cautionary points quite seriously. Azure and Amazon and Facebook and others can, because they have a very clear sort of enterprise business, profit-making business, they can invest in improving their core technologies to the point where it can start competing with, the best HPC solutions. But that still may not be cost-effective for the science enterprise. So I think that's where there may be that, from that perspective, there may not be convergence for a while, because we think that what the national labs are, for instance, taking on are remarkably cost-effective for the science outcomes we produce. And how to marry that with what the enterprise is trying to get out of doing machine learning in the cloud, that divide that's going to be a divide that's going to be there for a long time.
I'll just point out that there is actually, for what you call scientific computing or modeling simulation, there are companies that have very large internal resources, that it is a business just for that. It doesn't rely on deep learning or AI precisely. It's been going on for a long time. Some of those companies then come to Blue Waters and burst to do something that they couldn't do before, and then that drives what their investment is internally for their proprietary work. So there are a number of private corporations that you don't see on lists that are very well invested in that.
And
one last
comment. Just to follow up on the networking piece, which is that in high-performance computing, again, one of the things that we do very well is we restrict the use cases and then make that really fast. And so almost all high-performance computing has been, for the networking, has been focused on, minuscule, few instruction latency and the biggest bandwidth possible. In the cloud space, flexibility is very important. And so software-defined networks are a part of Amazon, Azure, and these others. Microsoft puts FPGAs on the board at the point of the NIC connecting so that they can be more flexible in what they do. And in HPC space, we have not adopted that kind of flexibility yet, and we will have trouble doing the kinds of things that the rest of the community wants to do until we adopt that.
Okay, let's thank the panel.
So good afternoon. I want to thank everyone for staying for the best session of the day. This is entitled Modes of Operation, Challenges and Opportunities, and I'll tell you why we did this. So first of all, I'm Sandy Landsberg, and I'm with the Department of Defense High Performance Computing Modernization Program. I'm the acting director of it. And my colleague, Laura Biven, is here from the Department of Energy Office of Science, and we organized this panel. So one of the things I want to bring up, I heard a comment today, DoD High Performance Computing Modernization Program. We've been around 25 years. I was asked the question again today, aren't you guys done with modernizing? No, now is the best time ever to be an HPC. Because we started doing what a lot of other folks did, starting traditional HPC, numeric-based simulation of physics. We solve large-scale aircraft problems. We solve submarine design. We look at helicopter aerodynamics. We look at basic turbulence, the whole range. But now, my management in the Pentagon, guys who are two-star SESs in general, are coming to us, the HPC modernization program, and say, hey, you guys are really smart with those big computers. Can you do this for AI? Can you do this for machine learning? Can you bring it to the tactical edge? Oh, and by the way, those really slick codes you have that can do aircraft design, can you make it easier to use so that my engineer who has no training can use it? That's really the origin of this panel, is that HPC is adapting and changing. And the way we use HPC has to adapt and change. And it's not just the traditional supercomputer centers. It's going to heavily involve cloud. It's the workflow. It's the end-to-end solutions out there. So we came up with a bunch of questions here, and it's all in small print. But the first one, so again, I have a very large-scale supercomputing centers. I have 5 of them spread across the entire United States. They run traditional batch mode. Now I'm supposed to support a large number of users in AI and machine learning who have distributed diverse workflows and workloads. They're not going to want to operate in batch. I need to adapt and change. So that's one of the questions we put to our panelists is, how do we change to support these data-intensive applications? The other one I touched upon is, again, we used to do 3D simulation. You ran it for 3 months, you do one simulation. Now they want to do rapid analysis of alternatives out there. They want to go and do the entire spectrum. I'll give you a DoD example. We build aircraft. We build submarines. We do this, once a generation. Do you know a submarine typically lasts about 50 years? Our goal, though, is to capture what were the design options? How did they do the analysis? How did they do those trade-offs before it was ever built? Can we apply simulation and capture all of that? Now, let's say we do go with the design. I'm going to go flip to helicopters at the moment. The Army was upgrading one of its helicopters. It was in the middle of test and evaluation, full-scale test and evaluation. They realized the rotor blades were having a stall issue. Boeing engineers and Army engineers went back and used our high-fidelity tools to go and redesign the rotor blades. They implemented it, and it worked, and they went right back to full-scale test and evaluation. That's the kind of changes we're bringing about. But it's a very distributed workflow out there. And so, again, we really need to go and change and accommodate that. It's not just the hardware, it's the software, it's the network, and it's the people. The next one about new users. Our panel here, I really enjoyed. By the way, we broke the mold. We didn't go alphabetical. We did it intelligently. So there is an order to this. I'll just say, my organization, we support about 3,000 to 4,000 users. Traditional physics-based. Now I open it up to AI machine learning. I'm going to double, triple, quadruple my number of users. Same thing here, looking at TAC or looking at NERSC. NERSC, best line ever, petascale for the people. That's what I am too. We're trying to deliver large-scale capabilities to the people out there, but our community is going to be, again, doubling and tripling. How do we take this into account? By the way, we do procurements every year. I buy large-scale HPC systems. My previous measure was utilization. It was all, I had to have 95% utilization. I don't think that's the right measure. I have not shown that number in the last 2 years. Someone brought up new metrics, and I forget who one of the earlier speakers today. We need new metrics, and we need to understand the requirements so we can do smart procurements out there. And I didn't get back to it. I personally believe, yes, I'm a supercomputer center. I need to interact with cloud. Absolutely, positively. I need seamless interfaces. Rangan's talk, your last slide I loved. It was about seamless interfaces between HPC, between the various architectures, between cloud, et cetera. That's what we need. So in the last one, I want to bring this up. In the NITRD HACC working group, for instance, we have a number of us who work in basic R&D. We also have a number of people who have large-scale supercomputing centers, infrastructure and applications. So we've asked all of our panelists to look at what changes do you see coming around the corner, both from a research perspective as well as infrastructure and application perspective. What's now and what's 5 years from now. So this is what we hope to get out of our panelists. With that, it is going to be Dan Stanzione from University of Texas at Austin, TAC, Ian Foster, Argonne National Lab, Debbie Bard from NERSC, Lawrence Berkeley National Laboratory, Fernanda Forder from NVIDIA, and Sanjay Pati from Amazon. And as I said, you'll kind of see this natural flow from some kind of supercomputing centers to workflows to working with large-scale data. Ian and Debbie will be a really nice tag team act right now together. Fernanda's going to talk somewhat about requirements. We talked about that a little bit. And then Sanjay's going to talk about some of the streaming analytics. And actually, that's the other part, too. I'm in DoD. One of the things they've challenged me with is, can you do HPC at the tactical edge? So all of the topics we talked about in this, I'm seeing it every day in the DoD. So with that, I want to go introduce Dan Stanzione. Oh.
Thanks, Sandy. Great. Is that all right? Thanks a lot, Sandy. I assume when you said instead of doing alphabetically, you did the panel in order of intelligence. I'm sure I speak for Ian when it's increasing order, starting with me and working your way up as we go through the panel is probably what goes on. So, thanks for the invitation to speak today. Although we're taking a sort of different slice of the questions, when we talk about convergence, I think many of the answers remain the same. So many of these points have been made already, but I will try and do them with more bitter sarcasm than previous speakers. So at least we have that as the value add for what's going to happen here. So let me just do one slide about TAC, because there's actually a relevant thing, and then one slide about the new system, because people ask. But then we'll get to the system at hand. So as mentioned, TAC is a large advanced computing center, much like the DoD centers, much like NERSC in a lot of ways as well. We do have a big supercomputer, but we also have a lot of other systems. And a lot of the reasons for the other systems are not necessarily architectural. They're around modes of use. And part of it is around, things that provide technical challenges in modes of use, but a lot of it, as Sandy mentioned, is what I'm willing to report to a funding agency in terms of how we use them. So we do support about 15 different platforms, and some of them are strictly because of mode and don't really have a significant architectural difference from one to the other. I think Bill was right on the hardware side of that. So, and then we have recently been awarded a new system, and so if I would get asked if I didn't say something about it. So Frontera will be our next system. Stampede 2 was the last. So still a few Intel non-disclosures to deal with and other various non-disclosures, but as you might imagine, we're building around the next generation of Xeon after Skylake. Which I'm not supposed to say the name of. I've decided that the Intel definition of NDA is things that have been on Wikipedia less than 3 years. But 35 to 40 petaflops, 8,000 plus nodes, 1.5 petabytes of RAM, HDR interconnect, more than 50 petabytes of scratch, some fast part of the scratch through Flash and NVMe type storage, all things you expect to see in a large system. In fact, I've argued that the architecture is actually fairly vanilla, and the innovation is in the operations of it at this point, somewhat around modes of computing. We are changing the SKUs we normally use and going for the very highest power processors, the 200 watt plus SKUs that everybody swore we'd never build, and that 130 would be the top forever. But it's not. And although those don't give the most peak flops per watt, if you measure in terms of the specs, our conclusion is that because the more exotic things, people have so much trouble using them, that they give the most effective flops per watt, because recoding for higher clock rate is just not something you have to do. So it has higher clock rate, more cores, higher memory bandwidth per core, more memory capacity per core than any of the other ones we've built. And then there's an NVIDIA subsystem, of course, with single precision, and then lots of things around moving data in and out, workflow, and API, which is more germane to this panel. So with that, let me, given all the, skip most of the examples because we've seen more examples of convergence today, and mine are sort of the same, but I want to make sort of 3 points. So first of all, and we'll call these big data versus HPC, or you can say AI versus HPC mythology. One is that simulation users love to wait longer for their results. And because they really like waiting longer for their results, we've always used batch mode because it's the most awesome way to do simulation. And you know, AI, big data users, of course, are very special and different, and they don't like waiting, so we shouldn't make them wait. So the fact of the matter is, everyone hates batch processing, including most of the users of it. All of our, in fact, if you'd like a data fitting problem, we can find the relationship between the length of our queues and the number of complaint tickets we get. And it's a fairly straightforward, actually it's more of an exponential model. It's not really linear. But tickets go up as queue length goes up. No one wants to wait. Everyone would love to have an infinite capacity system where they can submit and immediately begin running. The reason we use batch is utilization's higher, right? And it's more cost effective. And in fact, we can do lots of things not in batch. And to contrast with some of the points Pete made, because we have a little bit different operating environment in the university space, we've had to deal with some of these non-MPI users and even a bunch of MPI users who want interactive capability. So we've been supporting these modes for a while. We already run Singularity on all the systems. We can take containerized workflows and things like that. But when we tell people who don't want to wait and not go through batch, of course we can do that. We can make a reservation, but then you pay for all the time that's reserved in the reservation shadow for it, so it costs more. And then they're much less interested in that model, although there's still certainly times we use it. The big ones, of course, are hurricanes in the Atlantic, always, and severe storm season where the trucks go out at 4 a.m. and the models have to be done by then, which we used to do via reservation, and now we do via sorting priorities pretty effectively to make sure that their runs are done on time. But batch mode is not an HPC thing. It's not a simulation thing. It's a utilization thing more than anything else, right? And now there are some differences, right? Particularly in the data analytics space, people want their data set resident and to stay resident. So you might have to co-schedule some things like where your storage sits and how that works. But there's no fundamental reason we can or can't do batch mode. And you know, HPC is not really tied to that per se. It's a matter of if NSF gives us $30 million for a system, we're going to report that it's more than 95% utilized. And the way you do that is you run in batch. So in fact, we have another system, Maverick, that is our interactive system that's on demand, and its utilization is more like 60%, but that one is curiously not NSF funded, so I've never had to write a report that says the machine is only 60% used. So it's simply a matter of what you value, right? And if you want to count, hey, reservation time, idle time is use time, it costs more, but it can certainly be done. So I think it's a myth that, you know, HPC users love batch, and so it has to be batch there. It doesn't. We can make reservations in any batch system alive and treat it as interactive if you'd so choose. Second point I'd like to make there, and this is one Bill Kramer made in the last session, is that big data users must move a lot of data, so they must be bound by I/O or memory bandwidth. And simulation users must be bound by compute, so floating point performance is all they care about. Whether you look at almost any performance counter, whether it's cache misses, main memory bandwidth, floating point utilization, file size, as Bill showed, I defy you to tell the difference between a data simulation or AI user just from performance information, unless they've told you that's what they are, or you've looked at the name of their code. And we keep analytics and sampling on the last 10 million jobs that we've run, and there is no quantifiable metric. You could not do a machine learning curve fit that could tell you which are your machine learning jobs on the system, right? There are data-intensive jobs, processing data from the telescopes, completely bound by the FFT. There are simulation-intensive jobs that are completely bound by memory bandwidth, and you can't or file system bandwidth. And that is an algorithmic decision that doesn't really have anything to do with whether you're a simulation user or an AI big data user. It has more to do with the underlying algorithms, which frankly are becoming more and more similar. Another speaker, I think that this was also Bill, mentioned that, you know, the deep learning stuff, at least, is really dense linear algebra, which is what we built HPC to do over the last 50 years, right? You know, perhaps we could come up with some benchmark that measured your ability to solve algebra equations and rank systems and perhaps a list of 500 by them. But, you know, there is not that much even mathematical difference when you get into the other than scale and the way it's applied. And I think as we get more sophisticated in some of these deep learning algorithms, even those mathematical differences are likely to appear when we decide that gradient descent is perhaps not the solution to all problems related to AI, and that we'll use a more sophisticated methodology than we're using in deep learning networks, and start putting in physics constraints into those networks and do other things. The math's going to look a lot more similar too. So you can't tell the difference from statistics, and increasingly I don't think you'll be able to tell the difference from math. So choice of algorithm doesn't have much to do with the system either. You know, system-wise it's the same, whether it's AI, big data, or HPC. And then finally, once you've got things settled on a node, it turns out eventually you won't fit on a node. And we would love to have the silicon photonics that allow us to scale out single memory spaces to very large scales. And that would be a wonderful world. But again, there's a reason we don't do this. And I've had this argument with some of the various startups that come along and say we can do these super low power million-way processors. And you have to explain that even in the HPC community, we don't do parallelism because we like it. We do parallelism because we have to. It's the only cost-effective way to scale, right? Shared memory systems at scale cost more than distributed memory systems, unless you're creating the illusion of shared memory on a distributed memory system, which we can do. But if you have to cross two transceivers and cross a switch ASIC and go down a fiber, you know, it's going to take 800 nanoseconds to do this stuff. And it doesn't matter if that's a machine learning byte or an HPC byte or a simulation byte. It just takes that amount of time. And if you want to do it in any other way, your cost goes up an order of magnitude. And there are plenty of, you know, systems from the 90s. Am I at my 10? So, okay, I will wrap up quickly. See, I told you I was going to skip all the examples. Now I know why. As those were the points I wanted to make. So there really is no difference in what it takes to move a byte, and you're going to have trouble finding a more optimized layer than we built in the last 30 years with MPI, where we focused on how to get the latency out of those networks. So I think many of these distinguishing characteristics are in fact artificial, and it's just a matter of whether or not you're willing to pay for them. So all that said, I think the workload is changing. I think we do have you know, new kinds of folks doing new kinds of things, and I think the most important change we have to adapt to is that their skill sets are different, and they come to us from a different point, right? When we meet a computational physics user, they know what to do, and we give them an account, and we're done. Right? You know, we have to build a good system, we have to make it reliable, but after that, they're going to do great science, and we're going to put it on a slide and take credit for it, and that's how that works in sort of HPC. When they come to us in machine learning, deep learning, data, or new fields that need simulation for that matter, they want more out of us in terms of how much of the workflow we have to interact on. And that's where our staff mix has to change. And so I now have more people who build various kinds of web interfaces to make this stuff easy to use than I have who actually work in the data center with the big systems in terms of the way that we've comprised our staff, because most of our projects, skipping many examples, which look like many other examples where these work together, but many of our projects want a web portal and event-driven data and automated services. So where our focus is, flexible software stack, certainly. You pay a penalty and efficiency for that. Again, you know, we can run these other software stacks. They just have a cost in terms of performance. And so the big changes we've made are, one, put APIs in front of everything that we do to automate things, and two, have more workforce to capture more of that workflow. And I'll stop there. Thanks. That was even the actual last slide.
Our next speaker is Ian Foster from Argonne National Lab at University of Chicago.
Thank you. Okay, here we are, another step along an undefined gradient, up or down, we're not sure. I'm going to use this, let's see, so. Okay, thank you. So I thought I'd talk about something very specific, hopefully different than others. I want to talk about why I think changes in workload mix and this convergence we keep talking about require us to develop a new class of what we might call science cloud services to handle rapidly growing complexity. So this is a picture of Argonne National Lab, which you may or may not know, but I'm going to use it for a reason. So this is, in some ways, what's going on at Argonne in some sense captures what's happening throughout science, I think. I mean, first of all, we have some very interesting facilities here. We have a supercomputer, soon to be exascale. We have a interesting experimental facility that will currently generates gigabytes per second, soon will be terabytes per second. So we've got high-end computing, certainly, but we're also starting to see AI techniques being deployed really throughout the network, all these little dots actually color-coded. So, the APS is actually dozens of beamlines, all of which generating data at enormous speeds. We've got environmental sensors, as we heard from Pete earlier, increasingly smart labs where people are deploying AI methods into their laboratories, and various forms of instruments that are generating data, not perhaps at terabytes per second, but certainly at very high rates and need large amounts of computing. So we face this either opportunity or crisis. Of course, it's an opportunity for me. New instrumentation, as others are saying, data rates, enormous data rates. Neither humans alone nor computers can cope with these vast amounts of data using current methods, and therefore I think we're going to see AI methods becoming ubiquitous throughout science. And of course we've heard about them a lot already today, but I think they're going to become far more prevalent than we even imagine, not only for analyzing data, but for designing experiments, guiding simulations, creating and delivering software ultimately. And this means that we need new classes of system that can manage what is really a vastly increased complexity with dozens, hundreds, thousands perhaps of data sources, AI agents that are processing data from those data sources, and somehow managing the associated data flows and computations from training computations on big HPC systems to smaller computations, inference occurring near the edge. So how are we going to manage this vast complexity? Well, we might say, how does industry do this in perhaps vaguely similar settings? So I can't remember where I got this picture, but this was explaining what you should do if you're dealing with complexity in your e-commerce or other workloads. You first of all work out how to optimize what you're doing. Then you work out how to automate what you're doing, and then finally you outsource whatever you're doing to who? A cloud service provider, typically. And maybe you don't follow quite that order. Maybe you automate and outsource and then optimize later. But the point is you hand off to other entities responsibility for as much as you can of what it is that you're doing. And I apologize, I'm going to put up 2 Amazon slides. I feel embarrassed, given that we have an Amazon person here, but it's maybe worth thinking about what happens when you do something very mundane like buy an edge sensor device, this one, here like an Echo on Amazon. I'm told, at least a few years ago, that interacting with this one web page involves hundreds of services being run on somewhere. You're interacting with a whole series of back-end processes that manage billing and transport and so on and so forth. And this is all possible because Amazon has got access to this powerful set of cloud services that have been designed to basically allow you to outsource, you in this case being the developer of an Amazon e-commerce web page, but it could be someone doing something quite different, outsource and automate large amounts of the activities that you're undertaking in whatever it is that you're doing. So a question we might then ask, and I think we should be asking, is how much of what the complexity we're facing today, we can similarly outsource to, well, some we can outsource to Amazon and Google and Microsoft, and actually quite a bit of it. But, and by the way, I'm not talking here about the computing or the storage. Those are the dull, easy parts. I'm talking about the process aspects of what we do in science. But where do we need additional services that might allow us to similarly reduce complexity in our science processes? And so now I'm going to talk a bit about things we've learned from trying to do that over the last 8 or so years using a system called Globus, but I think the lessons are much broader and can be applied in many other cases. So we started off in 2010 or so saying, well, what if we were going to try and do for science what Amazon and others have done for e-commerce, what are the things that we might start off trying to automate and outsource? And we started off with things like, well, basically identity management and file transfer. Then later on we added things like file sharing, data publication workflows, access control, data discovery. We added APIs so that you could use this as a platform. We added interfaces to most of the storage systems that you encounter in science in settings. And well, where are we today? We found that actually people love this. There's some 12,000 storage systems, mostly in the US, but quite a few overseas, that are Globus enabled, a bit like a store on the Amazon storefront that's Amazon enabled, and that people from either a web service or via an API can drive in terms of transfers, managing sharing, authentication, access control, data publication, and so forth, programmatically, thus handing off responsibility to a third party, in this case, this Globus service that we operate, responsibility for managing the underlying complexity. So I'd like us to think as we think about how operations of HPC and big data and AI systems are going to change as we go forward, think, well, what else could we hand off in this manner so that we can focus in HPC on running big centers, making simulations work, or whatever it is we think is our competitive advantage, while letting someone else handle some of the other aspects. So, and this is, these just to show, this is a slide similar to what Dan put up. Some of the things that people build with these APIs. They build, national scale data publication systems, the data movement within national scale supercomputer infrastructures, infrastructure for managing systems biology data, services that deliver imputations on your 23andMe genome, and many other things beside. These are all things that operate with many nines because they're able to hand off responsibility to a third-party provider. I think I have a few more minutes. 2 minutes. Oh, good. Perfect. So I'm just going to mention, just to get you thinking, we can do more than just manage data transfer. With a new NSF project that's just starting, we're going to look at how you can manage end-to-end workflows with human in the loop and computation and other things by building out another capability that we're provisionally calling Globus Automate. So here we're looking at workflows like this. More new data is received at a scientific instrument. We need to transfer the data somewhere for analysis. You need to initiate some action to analyze it, perhaps move it somewhere, and then ultimately do something like point another instrument at the remote site. So if you think of the work that you're doing as you collect data from sensors, ingest it, process it, retrain models, we're increasingly dealing with more and more complex end-to-end workflows that people spend more and more time struggling with developing. They can write a Jupyter notebook to capture some of them, but that isn't enough if you want things to run reliably any time of day and perhaps on very large scales. That's where we need cloud-hosted automation services. A few credits, thanks to various federal agencies, particularly DOE, NIST, and NSF, and NIH. And just to wrap up, I believe strongly that we need to build AI-based methods are going to become ubiquitous because complexity is growing so rapidly. We need new, what we might call learning systems that integrate many different sorts of resources. And we're not going to be able to make these things run reliably if we keep doing things the way we have for the last 40 years, which is to rely on software that runs on someone's desktop or on someone's workstation or even in a HPC computing center. we need to move to a new modes of automation based around what we might call science cloud services. And I've given a few examples, but I'm sure you can think of many others. Thank you. What? It's okay. This is my seat, actually. I'm going to sit here now. I wanted to be able to comment on the next talk. Sure.
Our next speaker is Debbie Bard from NERSC.
Hello. It's good to be here. What I'm going to be talking about is actually in many ways very similar to what we've heard about today. And I'm going to touch on quite a few of the same themes that we've just heard in the previous two speakers. But there's one element that I really want to focus on that we're facing at NERSC, which I think is it's an aspect of this kind of big data workflow in HPC that's been brought up before a couple of times, but I want to really focus on some of the operational issues that we're seeing at NERSC when we're working with experimental facilities and some of the big data challenges that they have. These background slides, I assure you, are relevant. So in the Department of Energy, there are 17 national labs which encompass 29 user facilities, and there's a lot of different experimental science facilities involved there, including X-ray light sources, nanoscience, nanoscale science research centers, of course, compute facilities, all connected by ESNet. And NERSC is really the production HPC and data facility for the whole of the Office of Science. And what this ultimately means is that we have a lot of scientists using our machines, a lot. We have something like 7,000 users with active accounts in over 750 different projects. So there's 750 different research groups who are using our machines, using our resources, producing, of course, over 2,000 papers a year, which is the number that we're very proud of. But this is a large number, and I think it's fair to say that no two research groups are doing exactly the same kind of problem. And so no two research groups are presenting us with exactly the same kind of computing challenges. But this is not a new situation. NERSC and plenty of other compute facilities have been working with experimental and observational data facilities for a long time. But we're seeing that the number of facilities and the number of scientific research groups that identify as being kind of data science, by some definition of data science, is increasing. And I'll notice that in 2007, about 35% of our projects identified as being sort of data science, which is exactly the same number as NCSA for the same year, which I think is a great coincidence. And curious to see what comes out for us in 2018, whether we're tracking that same kind of proportion. But this is these aren't new challenges. What is new to us is really the scale of the computing challenges that the scientists are bringing to us. And so as mentioned a couple of times already today, what's changing? Well, one of the big things is that experiments are producing more data. The experimental equipment is becoming more sophisticated. The beamlines are becoming more high resolution. We have more data that we have to deal with, and that means more computing that's necessary. Also, there's new modes of operation. Scientists are integrating simulation and data analysis at large scales. The scientific workflows have become much more complex. It's no longer simply taking experimental data, doing an analysis over a period of weeks, and then looking at what the results are, which is more of a sort of simulation-style analysis workflow. There's a lot more that's coming in, largely due to the fact that these new advances in machine learning and tools are available to non-experts. And by non-experts, I mean scientists. Scientists are able to use these techniques in a way that they just couldn't do maybe 5 years ago. And so this is really exciting for the scientists, able to get much more meaning out of their data. But it means that us as computing resources, we have to be able to support this. And of course, there's new memory, storage, and processor and accelerator technologies which are available, which most scientists want to be able to use, but also gives a great opportunity to accelerate these workflows. And we have to think very carefully about how we choose the technologies we use that are going to help out the largest number of our scientists. So with that in mind, those are the kind of elements that we keep in mind when we're designing our systems. If this workshop was happening tomorrow, I could probably put up a slide showing you exactly how we're architecting our newest system, NERSC 9. But that's not yet been announced. That's coming later this week. But our current headline supercomputer is Cori. And we designed into the architecture for Cori, which is about 2 years old now, many aspects that were specifically demanded by our users around data science and around big data analytics. So a couple of examples, virtualization capabilities, real-time and high-throughput workload support in the schedule. I'll talk a bit more about that later. An optimized and scalable analytics software stack. So this is really the only point where I'm going to explicitly talk about machine learning. We've run full-scale, full-machine runs, scientific runs of full-machine Python stacks, full-machine container stacks, full-machine Julia jobs, full-machine machine learning, and AI workloads. We do these kinds of things at scale, and that's something that we've worked really hard on the last few years to be able to enable. But despite our efforts, when we talk to our users, especially users from experimental facilities, they have a lot of pain points that they're coming to us about. And I sort of think of these in two different areas. Some are sort of research questions and computer science research questions, and some are really policy questions that we have to address internally. So some of the research questions is especially around data sets. How do you handle large data sets and the metadata requirements around that? Searching, publishing, and sharing data, scalable analytics software. But then on the policy side, a resilience strategy is something we talk a lot to our experimental facilities about. If you have an experiment that's running at a beamline and you need to be able to process your data in real time to give you feedback on how that experiment is progressing so that you're not wasting your valuable beam time, you cannot tolerate NERSC going out of service in the middle of this. It's something that it's a real struggle for us to try to figure out what's the right solution for this. And that's, for me, a real operations question. And so that's one of the things I wanted to focus on in this panel. How do you handle and make any kind of guarantee for fast turnaround analysis needs? There's a lot of things that we're considering, and I think it would be interesting to hear what the other members of the panel are thinking about this. Also, identity management between experimental facilities and NERSC. And also, how do scientists want to access our systems? How do they want to access their data? There's many different ways they might want to do this, and most of them probably don't want to log in on the command line. So this is something we have to support. So I just want to kind of give a bit of a laundry list of some of the things that we're actively working on. For resiliency planning, there are a number of things operationally you can do to try to avoid downtimes in the first place, including rolling updates if that's possible, automated fault detection, diagnosis, that's a strong research area at the moment. But then resiliency planning also goes in both directions, and so we have to support our experimental partners in making their workloads portable between sites, and that includes portability to the cloud. So how do we support surge computing requirements from running experiments while still supporting our existing workload that all comes through our beautiful batch system? This is a real question for us. How do we have a real-time access for an experiment that needs it immediately? How do we handle the idle nodes that might be sitting around waiting for a real-time job, but the experiment's just not quite up to it yet? So they have to tweak some wires or something. What do we tolerate having idle nodes? How does this impact our metrics and our availability and our uptime and our all the numbers that we have to report to our program managers? And then we want to make it easier to access information and interact with NERSC. And so in common with many other compute facilities, we're designing, or we're working on what we think of as a super facility API, which gives experiments and other scientists access to information, ready information about NERSC's uptime, what queues are available, the kind of information that you have to hunt around a little bit right now to get. And so this idea of a super facility really encompasses a lot here, of which NERSC is just one part, but this is kind of the bigger vision that we're sort of working towards. is connecting experimental facilities, real-time analysis and data management, fast implementations of algorithms, networking for big data science and compute facilities, as well as new mathematical analyses such as machine learning techniques, connecting all these together. And so it's some sort of the wider picture for where we're working towards with the work that we're doing specifically with the experimental facilities. So I mentioned policy questions, and I think that's something that it's really worth thinking quite carefully about here. This isn't something that is just happening outside of our control. A lot of the things that people want to be able to do on HPC, we say no to, or we don't make it easy for them. And so that's something that at NERSC we've been working on, particularly in the last few years, is understanding what the needs are and then trying to figure out how we can accommodate those needs without impacting the rest of our workload. And that's a really tricky balance for us. Fast turnaround access. Is utilization the right metric? What do we want to think about a workflow turnaround time for a metric? And then different sets of users have different access needs, and that's a really important policy question for us. How do we handle identification and authorization? If someone only wants to read the data, do they need to have a full NERSC account? If they just want to have some limited functionality access through a web interface like Jupyter, how do we handle that kind of authentication, especially a user from an experimental facility that doesn't necessarily need to have a NERSC account? So those are the kinds of questions that we're thinking about. I'll skip over how popular Jupyter is. I think that's something everyone agrees with. But a key takeaway is we're talking to our users and we're listening to what they're telling us. And what they're telling us is that they have real requirements around resiliency planning, fast turnaround of compute jobs, new ways of accessing the data compute, and better and more appropriate interfaces to our systems, appropriate for the users, and really policies that prioritize what their needs are. And these are some of the thoughts that we have at NERSC around these areas. Thank you.
Our next speaker is Fernando Porter from NVIDIA.
So first I wanted to say that I hate the word democratizing, but I really had to use it here. I really mean it. So you probably know me from my previous life at Oak Ridge National Lab. I used to be training coordinator at Oak Ridge. And I'm going to tell you how I ended up in a gaming company. So first I'm going to correct that. We're not a gaming company. We're actually a platform company. And there's a real timeline that I'd like to sort of walk you through on how we ended up that way. So how do we end up from games to supercomputers? Well, it turns out that they built these hardware platforms that actually make it very amenable to be used within computing. If you think about what a GPU needs to do, is it just needs to figure out and guess, or calculate, not guess, but calculate what the color of a pixel is. Turns out that's very, very similar to how we deal with data sets, and especially large scientific data sets. You have one operation you need to do over across several points, right? And so, we sort of jumped. We've been actually in healthcare, which is the group I'm in now. We went very naturally from doing imaging for gaming and other sorts of aspects to imaging, for example, for healthcare. So that was a natural jump for us, right? We deal well with graphics. We're going to do graphics within healthcare. So we started doing that back in 2007. And, we went to the sort of typical ultrasound and put GPUs within the typical GE systems, that sort of stuff. And so we're rebuilding images. And then sometime around where you see ImageNet, it's right after, right here. So you have it about 2013-ish timeframe is where things kind of get out of control. So if you know a little bit about the history of how we ended up in supercomputing, was that Titan today, in fact, Titan is 6 years old. So we released Titan today about 6 years ago in 2012. And that procurement process began in 2008. Now, DOE needed more compute. They needed to do it at lower power budgets. There was this extra hardware. They took a chance. And NVIDIA asked DOE, what is it that we need to do? Well, DOE said, well, we need math libraries. Can you put BLAS basically on this GPU? And so NVIDIA went about putting BLAS on the GPU. And, out of a GPU starts coming out research like ITER and other fusion kinds of research, and physics and computational chemistry and the balloons. Titan is released. It's 2012. Everything is great. And right about that time, some folks realized that you can do the same thing and you can apply these same intrinsic libraries to the sorts of frameworks that were being used for deep learning, or they were just building for deep learning. And now we find ourselves in the throes of a deep learning and AI community explosion. And I argued back when I was wearing my ORNL hat that probably wouldn't have happened had they not gone through the process of trying to actually adapt to supercomputing. And so here we are. Here are the GPU accelerator libraries. They took a very long time to listen to the requirements from DOE, listen to the users. If you know what these procurements look like, basically they go out and there's a request for proposals, an RFP, and then you list each of the libraries and the sorts of applications they need to run on the sort of hardware, and then the company is supposed to come back around with a response of like, yes, we can run this on the hardware, and here's what we expect in terms of performance. So we started building these libraries, but it wasn't complete when Titan was released. And it didn't need to be for the procurement to be a success. We just needed to learn more about the other kinds of users that were coming to our center. And so I like to just make a small correction in how I perceive what actually the HPC users that we had cared about. And I would like to propose that it's not actually speed in HPC. There's a very small amount of people that we call hero programmers. They'll edge out all sorts of things out of hardware. They'll use all sorts of intrinsics. But for the vast majority of people, even those that ran at the OLCF, which is known as a facility for those sorts of users that'll inch out everything, even for a vast majority of them, what they really cared about was scientific output. So fast enough was good enough. They really didn't need to edge out everything. They didn't need to scale. They didn't want to scale. They had the only requirement was that they needed to use something like 20% of the machine, and as long as they hit that benchmark, they stopped doing development, basically. And so we needed them to do better than that because we needed them to actually run on the GPUs. We couldn't have these applications continue to run on the CPU only. We really needed them to use the full node of the 20% of the machine. And so, and there's history. It's not like they didn't want to move for no reason whatsoever. Here's 2003. There's an article from Technology, and this person is from Ford Motor Company, and says the next generation of supercomputers will most likely be similar to the last generation of supercomputers built in the early mid-90s, but significantly faster. And that's what people expect, and that's what people have been expecting. Can I just compile and run? And it's still very much within the mind of the folks that are running on supercomputers today, at least running in 2012. Another one was here from Thinking Machines back in '91, saying that the firm announced that it's going to do a pact with IBM and some microsystems to develop a programming standard that will allow the same application written in Fortran to run unmodified on workstations, mainframes, and supercomputers. So same app, I'm just going to compile and run. So I was training coordinator. We see ourselves finding a dip in requests, essentially, for time at Oak Ridge. We started to panic. We couldn't have a machine that we've launched and deployed not being used by the community. So they literally ran to Argonne. That's what happened. They didn't want to deal with the GPUs. And so I created this hackathon event. I thought to myself, I'm a lazy programmer. What would I want? I would want somebody to hold my hand. And so I created these events called hackathons, and I give them 2 mentors per team. And I said, if you bring your application and your team that's developing your application, I will give you 2 extra people to learn how to do it and port that application over 5 days. And we did great. This is what it looked like. We had an average of about 10 teams per event, over 70, 75 people. It was a huge effort. We've collaborated with many centers, including NCSA and CSCS. We've been all over the world. I was in India about a month ago, doing one in India, and it was hugely successful in the number of applications we've been able to support, well over 150. And this all comes back to this very basic level, which is this platform. The libraries are the same no matter what generation of GPU that you're running. And we make sure that that not just works across a generation of GPU, but even different kinds of GPU that you may be running. So for example, when AI took off, car manufacturers came to NVIDIA and said, we like to do the same thing because we want to run all those cool sensors and do all those cool things as the car is running. Their requirements were just slightly different. So our base technology, which is the GPU technology, stays the same. We just created a board that can take all these sensor inputs from all these other little things. Okay, so the base technology stays the same. In other words, our libraries work on that same base technology. We can scale that technology in different ways, say supercomputer like Voltus, Turing, which is our latest, or something like NVIDIA Jetson's Xavier, and all of that works in the same way. And now, sort of coming back and around a circle, now deep learning is being applied to things like drug development, computational chemistry, molecular dynamics, genomics, and all of these other things coming around and sort of circling back as one generation of folks then take on the GPU, they build new tools, those new tools then come back and help another level of development in new sciences. So what's in the future? What we see in the future is more hierarchical parallelism. We see more hierarchical data spaces, whether they're memory or I/O. Summit follows right within that. So Summit was the next procurement for Oak Ridge. Oak Ridge wanted very much to stay within and accelerate with accelerators for their platform. And Summit was the one that was proposed, and so we ended up choosing that for our user community. And now today in Summit, here how it comes all back around in a circle, we can do things like population discovery. So if you want to find out in a disaster area, say in a hurricane, if you're not quite sure what the census update is because it's near census time, you can find out what the density has increased by using satellite data and AI to then impute what the population density might be for a certain location that's been affected. So my takeaway here is that collaboration for NVIDIA was key in understanding the requirements for the users that were running on our platform. This collaboration with the hackathons was something that I need to defend myself on why I left Oak Ridge. A lot of people are saying, you left, they poached you, the industry keeps poaching our people. But I really gained a lot of respect on how much they really were willing to sit down. These tool builders were willing to sit down right next to our developers, not take our word for it. I said, I don't want you to take my word for it on what I feel is important for our users. I want you to see and hear from them too. And some of the things that they found important was really, were really simple things like, if you had just told me what the error meant, I would have figured this out right away, but this is an ambiguous error. I have no idea why it's not compiling. And it could have been something that it was just being more pedantic about the language and the way the language was interpreted, and they didn't want to compile because it thought that it was going to be doing something unsafe. So I'll close with, we're really a platform company. We keep the hardware simple in terms of what we build really just scales out with each generation, scales out in different formats. But really the sauce, the secret sauce that while we like to keep things moving and very easy to move across is really what we're building right now, which is the platform. And how I moved to NVIDIA was really, and the reason why I moved to NVIDIA was they asked me to come over here and do the same thing to the bioinformatics applications and genomics community. So I like to do the same thing and trying to get those requirements for them and see if we can move that whole group forward. So thank you.
One of the questions, because you brought up a number of topics that we haven't talked about so far today, and I think some of the challenges you brought up were with people, having to kind of train people differently, having new interfaces, having to have a highly resilient system, having, I'll call it a surge capability out there, et cetera. So I'd like kind of each person to just kind of tell me what you think your greatest challenge is, I'll say in the next 0 to 3 years. And Dan, I'll start with you.
Good, you started with an easy question, greatest challenge. So I do think the point I ended with is that sort of for research computing centers, I think all of us, users are asking more from us. And that means expanding our range of expertise and being able to pay people to do that in a pretty competitive, well, the stock market has one more week like it's had up till today. Won't be that competitive, but in a pretty competitive landscape, right now, actually retaining and mixing all of those different skill sets that we need to have. And just sort of along with that, sort of explaining what our new role is. I had a bunch of folks from oil and gas who run their HPC centers who said their bosses have come to them and half their bosses were still on the when are we going to completely replace you with the cloud, and the other half is when are we going to completely replace you with quantum. Has already started at Shell, Exxon, Chevron, et cetera. So they're already saying we're going to replace you with quantum in the next year or two, right? You're going to buy a quantum machine, it's going to solve all our problems. So there's just so much misperceptions around what it is that we're being asked to do, and that it's not simply deploying a big piece of hardware and then staffing all that. So,
Ian.
Obviously, the answer is the quantum cloud, I think. No, I think neither here nor there. Yeah. I mean, as the amount of data increases exponentially and the number of people stay constant, we need to be automating at an exponential rate, and that requires us that we change business models, training. We still need people, but the people need to be far more effective. So how do we use automation to make that possible? I think that, and AI. So I think that's a big challenge for science, especially given the constraints that you point out. We're not going to be able to pay people anymore.
So the top two answers I was going to give have just been taken there. Start finding and recruiting and retaining staff who have the skill set is really difficult. Finding the ways of automation that we can maintain this. I'm going to add in there training our users to be able to use our systems. We're going to face, at NERSC in particular, I'm not sure about other centers, but we're facing an increase in the number of people who will be touching our systems in not necessarily via the command line, but perhaps by accessing data. How do we support that many scientists without expanding exponentially the number of consultants we have on staff? So training and figuring out how to train large numbers of scientists to use the systems is something that we're thinking quite hard about.
Fernanda?
So everywhere I've been going to and speaking with folks that have data, and I go in there and I say, so what would you like to do? We want to get in on AI. We want to do deep learning. Great. You have data. Oh yeah, we have tons of data. And is it ready for compute? What does that mean? And so what we're finding is the hardest thing is not really, does data exist? And it's not really, can you write the software? But cobbling up the data is the hardest to overcome right now. It's the highest activation energy requirement.
I mean, there are a lot of challenges, right? AWS evolves at a very fast rate. There are, we started communicating with academic communities, but we need a very much more dedicated stance for that. We have, it's hard to scale up, even though Amazon is big, it's not as big as with other communities. So we have to work hard what is the best way the community can inherit the advancements which is happening there. I'm not telling everything we do it is useful for this community, but there are many things which the community can inherit to accelerate the time to science, right? I mean, we saw in Fermilab cases, we saw in many of the university studies. So I think that the problem, I think, is what is one-to-many mechanism, we can work on together. We work with NSF on this, on several of them. But what are the best one-to-many mechanisms where we can help the community with those advancements happening?
Thank you all. Hold on, Mike. The mic is coming. Thank you.
So if you think about convergence, so there's multiple ways to approach it, right? So since each one of you have access or have run workloads on different kind of architectures, if I were to ask, why can't those be interoperable, and why can't interoperability go towards convergence? What would your answer be? Is it already happening? What would it take to make it happen, and so forth? If I were to design workflows that run on 4 of your machines, and I think, Debbie, you brought up the super facility concept, right? What would it take? What's missing today?
Mm-hmm. Well, I think a lot of the pieces are in place for that. There's always going to be, well, at the moment there are differences in the software, in the system software stack, which means one code that's compiled on one machine won't necessarily run on another machine, but it's not a huge leap to be able to do that. I think what's needed is the political will to make that happen. And from my perspective, I don't think there's a technological barrier to that, especially as the back-end libraries that are really highly optimized to run on the specific hardware. If you compile into one of those back-end libraries and that back-end library exists on a different machine, then your code will even be pretty well optimized to run on a different machine. It's there's more. I think it's more not policy exactly, but there's more. There has to be some kind of driver for that, and I without wanting to leap into that quagmire, I think we're starting to see that with ECP.
I want to say that maybe CERN has already done this. CERN's workload looks just like that, right? They have this really good team that can partner with the local compute resource. They know their data very well. They make it ready for compute. They know who's tier 1, tier 2, tier 3. And so they already do it. And lessons are there. I don't know if there's another place that really has that workload that really requires this yet, but maybe with healthcare it would.
Yeah, I think it depends a little bit on what you mean by interoperable. You know, can we run it all in the same system? I mean, at this point, I think we're pretty close to that, right? Containerization has almost no performance penalty. You know, we can slide in different software environments. We can make these things all run on the same system. Interoperating beyond that is an enormous challenge that may not even make sense. I can tell you, another meeting I was moonlighting at for a couple hours this morning proposed a generic single schema for all research data by which we could query across all fields and do it. And the Microsoft presenter here said, get rid of all schemas for all research data. I know which one I think is closer to being reality. So those two options.
I mean, I would tend to say that the big challenge we face is not making big codes move from one machine to another, which is not that important in my view, but more how do we move from today where you have a few hundred codes to one where we've got maybe thousands, tens of thousands of codes, or certainly different applications of codes, as everyone who currently works on their PC with their processing their instrument data realizes they need to scale to much larger data sets and computers. And I don't know the answer. I guess it's containers, right? But beyond that.
Tony.
It's just that your example of CERN, when I was at CERN, the physicists took over the IT, which used to do some computer science research. And had they done that without the director shielding Tim Berners-Lee, they wouldn't have invented the web because they'd have cancelled the project. Computer science weren't even necessary to do this interoperability.
Okay, I do want to end at 5 o'clock. I really want to thank everyone for staying all day today. G, are you going to talk about the breakout sessions tomorrow for us?
We'll be starting tomorrow at 8:45. There'll be 2 breakout sessions back to back, but we'll be starting welcome and introduction at 8:30. So if you could return here by then, see you tomorrow.
So the breakout sessions are downstairs, I believe, logistically. The rooms are downstairs. There'll be signs pointing us in the right direction, or you can just find
in this room for the welcome. Or?
So the breakout sessions are in room A, B, and J, downstairs. And if you look at your badges, it'll have, yeah, on On your badges, except for the moderators don't have any rooms assigned. You are assigned to one of the breakouts. So look toward the lower left corner of your badge.
Two things on yours.
Yes.
So yeah, the goal of this is really to mix and match because we know we are breaking stovepipes. You're not supposed to sit in one session twice. It's really to mix things up. And if you really don't like the session you're in, you can change. You're all adults, and you can figure this out. I apologize. I forget who said it. It was Jim Caruso. Reports really do matter to all of the federal agencies. Your participation tomorrow is incredibly important. We will have scribes. We're going to go and give an out briefing. And we're going to convert this into a report. And as Jim said, these goes to the highest levels. You have 15 agencies participating between the NITRD, high-end computing, and big data. So your opinions matter to us. So thank you all very much.